Alright, so we'll go over set theory. Okay, so what basically is set theory? So set theory, we have to basically define what a set is. So a set is a collection of well-defined objects. So if you're going to have numbers, let's say numbers less than 10, this is an example of a basic set. Okay, so a set is a collection of well-defined objects. So we're going to call the objects to be members. We can call them elements. So members or elements are contained in a set. So in this case, you can say 1 is a member of that set. You can also say 1 is an element of that set. Okay, so if we said A is the name of a set, we are going to see that we can actually say that A, if you're going to get any element, for example 1, you can say 1 is a member of set A. So we're going to talk more about these as we talk about the notation. But now we've talked about the basic introduction of it. We know what a set is. So we can express a set in what we call, this is called roster form when you see these kind of brackets, the curly brackets. Okay? So under the study of set theory, we're going to look at the different kinds of sets. We're going to look at the sets on the number line where you basically use an interval. Instead of using these brackets, you can use, for example, these brackets 1 to 4. You can use 1 to 4 like that. You can also combine the different kind of brackets like that. So all these are going to be explained later on in this topic. Okay, so don't worry, you basically get to understand what that denotes. Now let's try to break down the set theory notation, beginning with what you already know. Okay, so let me first of all classify the sets according to numbers. So let's talk about the sets of numbers before we proceed and look at the notation. So what are sets of numbers? So we can classify numbers in different categories. Okay, so I'll give you a list of different kinds of numbers we can have, and then give you a chance to try to classify them before I give them names. So we have numbers 1, 2, 3, 4. So these are counting numbers beginning from 1. And then we have numbers that can also be counting, except we include a 0. Okay? Then another set that you can think of is, so let me first of all classify these ones that we have already. The first one is called a set of natural numbers, and then the other set is called a set of all numbers. Okay, so we can proceed actually and move and have other kinds of numbers. So we have what we call integers. So integers include the negative numbers. So you can have negative 1, 0, 1, and 2. Of course, not ending on either sides. So these are called integers. Okay, so integers are represented using a letter Z. Then the other sets of numbers we can look at are what we call rational numbers. So rational numbers are numbers that can be expressed in the form of A over B. So all integers, all the numbers we've talked about so far are rational, in that they can be expressed in the form of A over B. So these numbers would include, in addition to the integers, it's going to include the numbers like fractions, 1 over 2, that's a 1 over 2. So any number that you're able to express in the form of a fraction, A over B, and of course, including the integers, they can also be expressed in this form. Now, except B can never be equal to 0. So another rational number that may interest you is what we call recurring decimals, right? So if you've come across numbers like 0.3 recurring, it implies 0.333 without ending. Okay, so all these are rational numbers for your own information, because there are questions that can ask us to like convert these recurring decimals to a fraction. Whether it's of different numbers at the end, it may be like this, which of course means 0.3 and then 141414 recurring, right? So it can still be expressed in form of a fraction. Now, the other set of possible sets of numbers are what we call irrational numbers. So irrational numbers are numbers that we cannot express in the form of a over b, and these involve these imperfect squares, square roots, right? So root of 2, root of 3, root of 5, and other numbers that you can't find the perfect square, they are all irrational numbers. But they are not the only ones. There are some decimal numbers, numbers like a pi, that you can't express in the form of a over b. So all those are irrational numbers. Okay. Now there's a bigger set which combines all the rational and the irrational numbers. Okay, which is a set we call real numbers. Very common set of numbers. So real numbers is a set of all numbers. I actually like calling them numbers that make sense. Okay, numbers that exist, numbers that are not imaginary, they are called real numbers. So all the rational and irrational combined together give us what we are calling the set of real numbers. So you notice that the set of real numbers consists of all the numbers we've talked about so far: the integers, the odd numbers, the natural numbers. They are all part of real numbers. Now, is this the biggest set of numbers that we have? No. There's what we call complex numbers. So complex numbers is the biggest set of numbers. All real numbers are complex numbers. So real numbers is a subset of complex numbers. Now, what makes complex numbers different or a bigger set is that it involves the imaginary numbers, the I squared. So numbers that you're able to express in the form of a plus ib are all complex numbers. So we've talked about the different sets of numbers and then also their subsets. Okay, now we can break this down actually and go further and classify these numbers into other sets. We can talk about what we call even numbers, we have what we call odd numbers, we have what we call prime numbers. What else do we have? So we have, I can also say we have what we call factors, right? And then we also have what we call multiples. Okay, of course the last two are not sets, I'm just trying to explain them. So what are even numbers? Even numbers are numbers that if you divide by 2 gives a remainder of a 0. So 0 itself is an even number. So 0, 2, 4, 6, 8, and so on and so forth. Odd numbers, numbers that you can divide by. If you divide by 2 gives you a remainder of a 1. Okay? If you divide by 2 gives you a remainder of a 1. So I think we'll start from 1 itself. 1, 3, 5, 7, 9, 11. All these are odd numbers. Now, what are prime numbers? Now, prime numbers are a bit interesting. We call them numbers that you can divide by 1 and itself. 1 and itself. So you find that it's a bit interesting. So we're going to have 1, 3, 5, 7, 11. Now you see that 9 is not a prime number. Now, in fact, it doesn't start from 1. I've messed up there. Prime number is a number that divisible, numbers greater than 1 and divisible by 1 and itself. So 2 is a prime number. So 2, 3, 5, 7, 11. Why are we skipping 9? 9 is not only divisible by 1 and itself because 3 is also a factor. So 11, 13, 15 is not. So 17. So that's a set of prime numbers. Okay? And then factors of course are numbers that you can divide into. So if you say factors of 9, for example, factors of 9 would be 1, 3, 9, right? Itself. And then multiples, if you say the multiples of 9, or let me say multiples of 3, you begin thinking of what numbers I've got 3 as a factor. So 3 itself, 6, 9, 12. So those are the multiples of 3. So I thought this is very important for you to understand as we proceed under a study of set theory, because these are going to be very handy as we proceed. They are going to be used, especially as we begin looking at what we call the set builder notation. Okay, there may be cases where we may describe the set in roster form. X is such that X is a member of, not necessarily a member, let me say X is maybe less than 20, and then X is a member of let's say even numbers or real numbers. So that's why you need to know these symbols, what they stand for. So if I ask you to list such a set, you need to understand, okay, so if we're dealing with X is less than 20 and then X should be a member of real numbers, what does that mean? So what are real numbers? So obviously you know that this is going to be a very big set. You know that real numbers start from negative of infinity to its positive. So we are restricted to go only up to 20, right? So what it means, the set will be from negative infinity all the way up to 20, but 20 is not included. So that would be the interval. Now, trying to break it down to something that is simpler to you, if we say it's a member of natural numbers, it means we're going to list numbers from, natural numbers start from 1, right? 1, 2, all the way up to 19. These are the natural numbers that would qualify to be part of such a set. So I'm going to add some interesting questions that I've already solved under this concept called set builder notation, and I think it's going to be very helpful to help you understand more. Now let's proceed and review some of the notations that we have under set theory. So you're already conversant with the union, the intersection, the universal. You are also conversant with what else are you conversant with? I expect you're conversant with a complement. If we can say a complement, I believe you understand what it means. So I'm just going to explain this again. So a union of a set implies you combine all the elements together. The intersection means you go for the common elements. The universal is all the elements under study. The complement means outside or not contained in a given set, but within the universal set. So what does this mean? What does this mean? Let's look at a practical example. So we can declare our universal set. In this case, we can either use a capital letter E or U. They can still both denote the universal set. So if we are starting the numbers between 0 and let's say all the way up to 10, right? That becomes our universal set. There's going to be cases where the universal set can be declared to be a set of all real numbers. So that's why it was important and necessary for us to look at the sets of numbers before proceeding. Okay? So let's try to limit it to 0 to 10. So they can give you A to be a set of even numbers. Okay? Even numbers. They can give you B to be a set of prime numbers. So you see why it's important for you to know these numbers, right? So before you can actually proceed to determining, let's say, questions like the intersection of A and B, the union, the complement of A intersection B, the complement of A. Okay? So you should be able to list what we have. So let me just move these questions a bit up and then see how we can handle it. Okay, so we'll start by listing A. So set A is containing even numbers. So even numbers are numbers divisible by 2 and gives a remainder of a 0. So 0 itself is an even number, 2, 4, 6, 8, and 10 itself. For B, which is containing the prime numbers, numbers that are greater than 1 and divisible by 1 and itself, 2 is a prime number, 3, 5, 7, what else? 7, 12, 8, no, 9, no, 10, no. So 7 is the biggest prime number. So if you are going to be asked to find the intersection, what are the common elements between the two sets? I can see 2 is the only common element. 2 is the only even number, which is a prime number. A union B means you combine these elements together. So what would it mean? We're going to have 0, 2, 3, 4, 5, 6, 7, 8, 10. And then A intersection B complement, on the other hand, would imply you remove 2 from the universal set. What's a complement of A intersection B? It means the universal set without A intersection B. So if you're going to remove 2 from the universal set, whatever remains is going to be A intersection B complement. For A complement, it implies remove these elements again from the universal. What remains in the universal are going to be the complement of A. It means they are within the universal and outside A. So what are those numbers? So 1, 3, 5, 7, and 9. So I've introduced you to a set notation, and of course I did mention that we can have things like a member of a set, right? So if you're going to say set A is having members 1, 2, 3, you can say 2 is a member of set A. You can say 4 is not, so you cross. 4 is not a member of set A, as we can see, it's not there. Then there are things like the subsets. You can say, of course we're going to talk about subsets, but this is a subset of, okay, these are the two ones we're going to be dealing with. So this generally means a subset, and this means a proper subset. Okay, this is generally a subset, that other means it's a proper subset. Of course we're going to understand what a proper subset is and what just a subset is by definition, and of course by what we're going to look at. Now, a Venn diagram is not something that is new to you. We basically use a Venn diagram to represent details about a set. So in the previous example where I gave you an inverse set, so usually we use this for what we call the finite set. So they are going to be what we call an infinite set. Why am I saying a finite set? A finite set is a set that you're able to count the elements. There are going to be sets that are called infinite that you can't count. Sets like a set of real numbers, that's an infinite set. You can't express it in terms of a Venn diagram. You can't list it all. Now, finite sets are sets like where the universal set is limited. Let's say 0 to 10. You know that these numbers you're able to count them. Okay, so that's a case where we can use a Venn diagram. So the inverse set, the box itself represents the inverse set, meaning that all the elements that are going to be under study will be within the box. Now you can break it more into detail. You can name the inner sets A, B, and C. So what you're going to put there, usually these are the elements that are common in all the three sets, because we can see it as a point of intersection for all the three sets we have. At this point, you can put only elements common between A and B, only elements common between A and C, only elements common between B and C, and then the middle part, of course, all the elements common. Now, you've seen that I've focused more on the elementary form, where we can have set A to have 1, 2, 3, 4. If you are going to have set B containing 2, 4, 7, 8, and then you're going to have set C containing 1, 4, 8, 9. So What this would mean is, if you try to identify the common elements in all the three sets, we can see only 4 is common. 4 is common in all the three sets. So 4 would be the element there. Now you have to put a dot to indicate that 4 is an element. And then if you can look at B and C, I can see 8 is a common element. So a dot and then 8. If you can look at A and C, I can see 1 is common. And then if you can look at A and B, I can see 2 is common. So if I can go into A, what's remaining there? If I move 2 and 4, 1 and 3. So I'm putting a dot to indicate that they are members. For B, of course, you see that we have 7 remaining. For C, you have 9 remaining. So this is basically how you can go about this. So I've actually made a mistake. 1 is already included there. So let's say I added a 0 to that set. It would mean 0 would be. The idea here, I'm trying to show you that you can put more than a single element in a given set. So all the other elements that are within the universal set that are not inside can be outside. So you can see we have 0, 1. So 3 is not. No, 3 is there as well. 4 is there. 5 is not. 6 is not. 7 is not. 8 is. 9 is. So those ones are outside the 3 sets A, B, and C, but within the universal set. So you can indicate them using the Venn diagram in such a way. Now, the other kind of a Venn diagram that we can have is a Venn diagram that deals with numbers. Okay? These may be cases where, for example, you are dealing with focusing on a study of a class. Let's say you are trying to focus on a class of students with options. You may have people who are taking math as a compulsory subject, and then others may be taking civic education, and then others may be taking history. So in this case, you can't say 1, 2, what? No, you can just say, okay, how many students are taking math? 20. How many students are taking civic education? 30. How many students are taking history? 30. How many students are taking both math and civic education? 15. How many students are taking civic education and history? You can say 4, or let's say 10. How many students are taking both math and history? You can say 17. So the basic idea in a question that is set up like this is, in this case, when it comes to a Venn diagram, since you're dealing with how many, you're just going to be putting a single number. If you say 20, it means the 20 students are taking math. Okay? So I'm just trying to give you a picture. In such a case, you don't put a dot, because 20 is not a member, but 20 is a number of math students. But in practice, that's not basically what you do in terms of writing the 20. You don't just write the 20 directly as it is. You have to go for the students who are studying over 3. You start from the center and then until you reach the ends. But I was just trying to give you a picture on how I use a Venn diagram. And I'm going to add a video, a tutorial that's going to explain to you on how you can enter the information in a Venn diagram in an orderly manner. Okay, I just thought I needed to mention as we introduce it. And then we now have what we call power sets. What is a power set? So a power set, of course, makes more sense after you talk about subsets. So let me start with the subsets and then we get back to the power sets. So what is a subset? So a subset is a set contained in another set. Contained in another set. That's what a subset is. So if you're going to say, I'm going to start with the smallest set we can have, consisting of members 1 and 2. So what are the possible sets we can come up with that are contained in A? So an empty set is also a subset. 1 is a subset, and then 2 is a subset. So these sets that I've written there are contained in A. Now, the set itself is also contained in itself. So you notice that in addition to the empty set, the set itself is also a subset, including the cases where you can have minimal elements as well. So you can see that a set containing two members has got 4 subsets. What if we said we had set B containing 0, 1, and 2? What are the possible subsets? So an empty set itself is a subset containing 0, containing 1, containing 2. You can also have a case where you could begin combining. You can have 0 and 1. You can have 0 and 2. You can have, do you have 1 and 2? You can have 1 and 2. And you can have a set itself, 0, 1, and 2. If we come up with all the possible combinations, so 1, 2, 3, 4, 5, 6, 7, and 8. So there are 8. So the formula is 2 to the power n for the number of subsets. Okay, so you can see in a case where you've got 2 to the power 2 is 4, we have got 3 to the power 3 is 8. That's how you find the number of subsets. So a subset is a set that is contained in another set. An empty set and the set itself are also subsets of a given set. Now, under subsets, we have what we call proper and improper subsets. So if I can take you back to an example where we have set A containing members 1 and 2. So let's just list down the subsets. We said an empty set 1, 2, and then 1 and 2. So these subsets that are less than the set itself, they are the ones that we call proper subsets. Proper. They are less than the set itself. Now, the subset which is a set itself, or in short, a subset which is equal to the set, is what we call an improper subset. Okay. So now the symbol for a proper subset is, you can say, if you're going to call this set C, you can say C is, okay, it's a bit confusing. Let me use a different letter. If you can say that is X, you can say X is a proper subset of A, in that all the elements of X are contained in A, but X is also less than what? X is also less than A. That's the interpretation of a proper subset. Now, on the other hand, for the improper subset, you can say we don't have any symbol for an improper subset for your own information. We don't have any symbol. So in such a case, we can just, there's nothing we can do but just say that X. We can just say, if we call it Y, you can just say Y is a subset of A. Now, notice that I can also say that X is a subset of A. It's only necessary if I didn't want to explicitly make a point to say it's a proper. That's when I leave out the dash. But in a general sense, you can say it's a subset by using this symbol. Okay. So this is what we call now proper and improper subsets. So if we are going to get back again, the formula for determining the number of subsets is 2 to the power n. The formula for determining the number of proper subsets is 2 to the power n minus 1. So that one we're removing is the set which is equal to itself. So for a case where we add 4 subsets, the number of proper subsets are 3. For a case where we add 8 subsets, the number of proper subsets were 7. Let me add a bit of some detail under subsets. So I've said, if you're going to have a case where, let me get you back to set A, and then set A is having members 1, 2, 3. If you're going to look at set B, having members 1 and 2. In this case, definitely, we can say B is a proper subset of A, because B has got 1 and 2 contained in set A, but A is bigger than B, right? Okay. Now, if I was going to say B is generally a subset of A, I wouldn't be wrong either. Okay. So the basic idea is the interpretation of this one is that it may either be equal or less than the other set. Okay, so if I'm going to have set C containing the same elements as A, the only way I can express it as a subset would be C is a subset of A. Okay, there's no other way. I can't use this. Okay, so I know some textbooks, some sites would tell you this symbol implies improper. That's not the case. It's just that there's no other way we can actually present it. But the basic idea is that when you see something like this, it denotes two possible cases. Either it may be a proper or an improper. In short, this symbol is a general symbol for a subset. Okay? So I needed to mention that if you're going to compare again set B and A, we can call A to be a superset since that is where B is contained. So A is a superset of set B. B is a subset of A. I thought that is also very important to basically get to mention. And then the other symbol that I wanted to mention is not subset. Okay, if you're trying to indicate that something is not a subset. So if you're going to talk about set X containing 0, 1, you see that 0 is not contained in A. So obviously you can say that X is not a subset of A. So I thought that symbol would also be very useful, very important. And of course, I think this would mean X is not a proper subset, but I think it would make more sense if you draw a dash to say X is not a subset explicitly in any form. Okay. So let's proceed now. Now a power set is very simple and straightforward. So I'll take you back to A. If you're going to say A is having 1, 2, let me add the new member 3. What are the subsets you have? The subsets of A, we have an empty set, we have a set containing 1, we have a set containing 2, we have a set containing 3. We can now have possible combinations 1 and 2, 2 and 3, and then you can have 1 and 3. You can have the set itself 1, 2, and 3. So if I'm going to group these in a set and then open a set and close a set and then add commas. So a power of a set is a set that includes the subset. So a power set is a set of subsets. So if I say the P of A, the power set of A, it is a set containing the subsets of set A. That is what a power set is. Very simple and straightforward. That's why I said it makes more sense by first of all reviewing what subsets are. Okay? So now that you've understood the basic introduction to our set theory, as we proceed and look at other concepts that are going to be easy, as we look at the laws under set theory, as we look at practice questions involving set builder notation, set interval notation, the Venn diagram, and then many more things. We'll proceed, look at, of course, the Surds, binary operations, complex numbers after everything. Okay, thank you very much for watching the introduction. I hope you enjoy your journey as we proceed. Now on D, we are supposed to list down the subset. So a subset is a set containing another set. The number of the subset are given as 2 to the power n, I believe. So if you have got a single element, it's also going to be 2 to the power 1, giving you 2. If you've got 2 elements, it will be 2 to the power 2, gives you 4. If you've got 3 elements, it will give you 8 subsets. So a set itself is a subset of itself, and then an empty set is also a subset of a set. So for A, an empty set, and then the set itself. These are the two subsets we have. So the formula is 2 to the power n. So this is 2. For B, an empty set, and then the set itself, and then we can have A as a set, we can have B as a set, so there are 4 already. And then for C, an empty set, the set itself, 1, 2, and 3, and then we can have a combination of 1 and 2, 2 and 3, 1 and 3. You can also have them individually, 1, 2, 3. So if you try to count them, how many are they? 1, 2, 3, 4, 5, 6, 7, 8. So what are the possible subsets for these? When they ask you to list down what we call proper subsets, the formula is to the power n minus 1. So proper subsets excludes the one, which is the set itself. Okay. Now let's go over the difference of sets. So we need to understand what it means when you say A minus B. I know most of us have been told it's A intersection B complement, and that's the only thing that we know. But what really does it mean when you say A minus B? I think we'll go over that in this video. Okay, so this may be part of a series of set theory as well. So don't be surprised if you're watching it in a longer video. So A minus B means A without B. A without B. So the other way you can actually interpret this is it implies A without the intersection. So without A intersection B. So it's like you remove A intersection B. So it's like, again, you can also put it as A without the intersection with the other set you're subtracting. Equally, if you're going to use a different letter, A minus C, it implies A without the intersection with C. Okay? A without C. That's what it means. Okay? So if you're going to look at the two sets we have in this case, considering our A is having 0, 2, 3, 4, and 6. Now, we have to find A minus B. How do we go about it? So let me try to express that below here. So we have 0, 2, 3, 4, and 6 in A. Now we're subtracting our B, which is having 0, 1, 3, 5, and 7. So the basic idea here is to remove the elements that are in B. So our A is here. So let's identify the common element. So you can see we have 3. 3 is common. What else is common? You can see 0 is common. 1 is not. 5 is not. 7 is not. So these are the two common elements we have. So if we're going to remain with A minus B, it implies only 2, 4, and 6 are going to remain. So 2, 4, and 6 are the elements in A, with the exception of the ones that are in B. So that's what it means when we say A minus B. Now, on the other hand, if you're going to try to find B minus A, it means the elements that are going to remain in B if you're going to remove the ones in A. So that would imply we're going to remain with 0, with 1, 5, and 7. Okay. So you can clearly see that when we're going to say A minus B is not equal to B minus A. They are very different. Okay? So the commutative law, as you'll see later on, is a bit contradicting to this subtraction. Of course, we know from basic mathematics to say division or subtraction is not commutative. 2 minus 3 is not the same as 3 minus 2. Well, let's try to prove now. Can we try to look at the idea how A minus B is the same as A intersection B? The complement. Maybe before that, I can also try to prove, if we're going to find the intersection of A and B in this case, what are the common elements? We saw 0 and 3 are the common elements. So if you're going to try to, you can clearly see that A minus B as well is going to be as good as saying A without the intersection with B. So A would be 0, 2, 3, 4, and 6. And then, of course, remove the intersection, which is having 0 and 3. So we'd get the same answer, which would be 2, 4, and 6 remaining. because 0 and 3, which are part of the intersection, are going to be removed. Okay, so now let's look at the A intersection B complement aspect of it. Okay, so given that the universal set is U, having numbers 0 to 7, how true is it that the intersection B complement is true? So let me begin by looking at don't forget our A minus B is equal to 2, 4, and 6, so I'll leave it there. So if we're going to have a Venn diagram, what region do we call A minus B? So the region that would call A minus B, taking this to be our A and our B, the region A without B would be this part. This is the same part of A with the exception of the one that is part of B. So that would imply we're talking about this region, which is actually the intersection. That's why I'm interpreting it to be A somehow without the intersection with the other set. Okay? Now, imagine they ask you to describe the shaded region. How would you describe it? So you basically describe it as, first of all, it's a region of A with an intersection of a region that is outside B. So outside B implies B complement. So the region we've shaded is, first of all, in A. Not only is it in A, it's also outside B. So that's A intersection B complement as a region in itself. Okay. So we expect to find 2, 4, and 6. Don't forget, A minus B in this case should be 2, 4, and 6. So let's look at A intersection B complement. So our A, we already have it. Now let's try to find our B complement. B complement implies remove the elements that are contained in B from where? We're supposed to remove them from the universal set. So we have 0, 1, 3, 5, and 7. So 0, 1, let me use a different color there. So we have 0, we have 1, we have 3, we have 5, we have 7. What's remaining of our universal set? Remaining with 2, 4, and 6. So those are the elements that are remaining in the universal set. So that's our B complement if we're going to remove the elements contained in B. So what intersection do we have between the two sets, A and B complement? So all the 2, 4, and 6 are contained there. So therefore, the intersection of A with B complement is definitely going to be 2, 4, and 6, which verifies that A minus B is equal to A intersection B complement, even as we showed on the Venn diagram. Okay, so that's it about the difference of sets. De Morgan's laws. So this is where we're going to begin looking at the laws under set theory. Okay, so we've already seen how we basically get to work with roster form. We understand the notations of intersection and union. So we first De Morgan's law, as we can see. Consider a case where you have A intersection B in brackets and then you have a complement outside. So what will basically happen is we expect the notation in between to change from intersection to union. And then we expect that set A becomes complement and B complement as well. So you might guess what the other De Morgan's law tells us. So if you look at the De Morgan law, where you have a union, what do you expect? So obviously you expect that it will become now intersection in between. Okay, so these are the two De Morgan's law that will guide us as we get to look at set theory. Considering a case where you have A complements, union B, and then a complement outside. So we expect the same to apply. So we'll see that where we have A, it will now become just A. Where we have union becomes the intersection, and our B will become its complement. Okay, so I'm applying De Morgan's law to simplify this. But the two De Morgan's laws are the first one and the second one. Those are the two De Morgan's law that they can ask you to state, and of course get to prove. I'll explain later on how we get to confirm, but understand that those are the two De Morgan's laws that you need to understand under set theory. Of course, for the sake of proving, we can look at one example. I'll look at the first one. We have A intersection B complement, right? So we've seen that it gives us A complement union what? B complement. So you can prove this by shading. How? So what does A intersection B mean? So if you have two sets using a Venn diagram, and then this is your A, that is your B, the intersection of B is the region in between there. That's what? That's an intersection. So our label that is A intersection B. Now, A intersection B complement will now be the region outside that. So if you draw the same set, what do you expect? You expect that your A and B, like that. So your complement will be the entire region except A intersection B. That is what you have. Only the region outside A intersection B has been shaded. That is for the left hand side. Now let's look at the right hand side. The right hand side is dealing with A complement union B. So what you do here is, of course, you're considering the two sets again. Okay. So these are set A and B respectively. So it's need for us to deal with. So we've already talked about what, of course, we understand these are inverse sets. We've already talked about what the complement is. It means the set outside the given set. So we'll take our left one to be A complement, the other one to be B complement. And then we'll put a union in between there. What does it mean? So A complement means shade the region outside the A. Everything outside A represents A complement. And then the other set we are shading B complement. Everything outside B qualifies to be, so I've shaded the inner. Okay, like that. So now union means that you combine the two regions together. So if you combine whatever we've done in our final result, this is now A and B union. So now we're now saying this is now the union of A complement with B complement. So if you combine the regions together, if you observe these two diagrams, what is going to remain unshaded? So I'll shade first of all A complement. Since union means that you combine them, I'll shade first of all A complement. So what is my A complement? It's the region outside A. That is my A complement. And then I'll shade my B complement outside B. So outside B. So we're noticing that there's only a single region that is unshaded, which is in between, right? Which is A intersection B. So if you look at this, which was now on the right hand side, A complement union B complement, and then A intersection B complement. So we are saying that the result is what? Is one and the same. So we've proven by shading to say the left hand side is basically equal to the right hand side. Okay? And that has introduced us to the idea of now what? Shading sets. So your last exercise is now, I want you to now to prove the other De Morgan's law, which is A union B complement is equal to A complement intersection B complement. Prove by shading. That is your exercise. In this video, we'll just talk about associative laws. Okay. So what exactly are associative laws? So understand what that means. But before that, I'll begin with something so simple, commutative law on set theory. So this is very simple. So you understand that multiplication, addition are commutative, right? A plus B is the same as B plus A. That implies 2 plus 4 is the same as 4 plus 2. That is commutativeness of addition. It applies to multiplication as well. 2 times 4 is the same as 4 times 2. Of course, you understand that 2 minus 4 is not equal to 4 minus 2. So what is that? This is negative 2. That is 2. So negative is not commutative. So commutative laws under sets consider two sets. If you say intersection B, it is the same as B intersection A. There is no difference. Okay. So even union, if you say A union B, it is the same as B union A. That is what we are now calling a what? Commutative laws. Okay, very important to understand that. What else do we need to understand? Now, the other thing that we need to understand is I did mention, of course, earlier on in the series to say A minus B is not equal to B minus A. So, of course, subtraction is not commutative. Now, talking about associative laws, which is very important now. So, associativeness is more like commutative, except it deals with 3 sets. So, if you have A intersection B intersection C, okay. So, you understand that mathematically, we deal with binary operations. So, you only deal with 2 things at a time. You can't find the intersection of A, B, and C at the same time. No. You begin with 2 sets of your choice. So, what you begin with is what we put in the brackets. So, in this case, we begin with B intersection C. Now, these associative laws tells us it doesn't matter what you start with. You can decide to start with the intersection of A and B and then intersect it with C. It is still the same. If you want to remember this easily, think of a case where you're dealing with additions of 3 numbers. You can't add them at the same time. You'd have to begin with 2 numbers first of all. If you have 2 plus 4 plus 7, and then of course the same 2 plus 4 plus 7, you can't add them at the same time. You have to start with 2. So if you start with these 2 numbers, or you start with the first 2 numbers, it is still the same. So what is, in this case, you have 2 plus 4 plus 7 is 11. The other side, 6 plus 7. 11 plus 2 is 13. 6 plus 7 is also 13. So you've seen that it doesn't matter what you start with. Remember, Bodmer's tells us start with what is in the brackets. So this is basically the argument that is made by associative laws. Very simple and straightforward. So the same concept applies to union. So if you start with a union of B with C and then unionize with A, it is still the same with starting with A union B and then with union of C. So it's just a matter of understanding the aspect of putting brackets. That is what associative law deals with. So now in terms of proving this, let me try to give you an idea on how you can basically get to deal with this. A union B union C. So let's say we have, okay, let me deal with intersection. I'll give you A intersection B intersection C. Let's say we had the set A made up of even numbers less than 10, 2, 4, 6, 8, and then set P made up of the odd numbers. That is 1, 3, 5, 7, 9. So now this is going to be a very, very bad example. Let me just come up with an imaginary set B so that we can have 2, 5, 6, 9, right? So at least we have intersection now. So what this means is what I'm having on the left hand side, I'm having set A. So now my set A, I'll write it as it is. We have 2, 4, 6, and 8. So I'll write now intersection. Now we need to find the intersection of B and C. B intersection C now. Now B intersection C is what? B intersection C now requires us to combine the elements between B and C. Now this reminds me that I don't have C in my example. So let's say we have 1, 3, let's say what else, 4, 6, and 9, right? So B intersection C. B intersection C, now a common elements between B and C. We have, okay, what do we have? I can see 6 is common and 9 is common. So 6, 9. Is there anything else? No, that's all, 6 and 9. Now, if you look at the two sets, what do we expect to have? The only common element is 6. So that's our answer. So what has dictated our order is the brackets. So on the other side, if you have A intersection B, there's a requirement that I'm supposed to begin with that. So A intersection B, what is common between A and B? I can say 2, 6. And then intersection C. So I'll put my C as it is, 1, 3, 4, 6, and 9, right? And then the other result now is also 6. So what is mattering now is the order of what you basically get to deal with. So usually the way we get to present all this is, you would begin first of all by indicating your left hand side. I'm just trying to show you the formal way of presenting your answer in an assessment. And then you can preferably start with now with what is in the brackets. Show clearly your B intersection C is equal to this. And then on the next stage now you can now continue with A intersection B intersection C. So since you have your A, write your A and then intersect it with the B intersection C that you found there. And then your answer will be found. Then go to the right hand side, do the same, begin by finding what is in the brackets and then show. That is basically how you get to deal with associative laws. Very, very simple and straightforward. Let's talk about distributive laws. What are the two distributive laws? So I like finding ways and means to make it easier for my students to remember these things. So distributive means you are distributing something, right? So multiplication is an example of distribution when you have brackets. Consider a case where you have x and then you have y plus z in the brackets. So I believe we understand that we can multiply x with y and then we maintain the sign in between and then again multiply x with z, which will be x z. We understand that simple. So that is distributive law in itself. Okay? So now this means that in a case where you have 2 with maybe let's say 4 plus 7. Okay, let me work with simpler numbers to just make things easier. Let's say 3 plus 4. This is as good as saying 2 times 3. And then again I'll say 2 multiplied by 4. I'm just applying the same concept that I did with the letters there on top. So I can proceed and simplify it. What we have 3 plus 4 in the brackets is 7. The other side 2 times 3 is 6. 2 times 4 is 8. 2 times 7 is 14. 6 plus 8 is also 14. So you can clearly see that the distribution is true. Now we can apply this to now set theory. So the basic idea is what we are trying to consider is where we have the x there, there is multiplication there. So you are multiplying x with y and then x with z. Okay. So we'll apply that now to set theory. So now consider a case where you have an intersection outside and then inside the two sets you have union. So distributive will have a combination of these signs. So we'll consider the one that is outside as multiplication, right? So consider that to be A times B. So intersection as a multiplication. So have A intersection B. Now remember, if we go back to where we had x multiplying with y plus z, we said after you multiply x and y, you maintain the sign in between, which was a plus. So equally you maintain the union in between. And then again we'll go back to what is outside, which is more like a multiplication. A multiplied by c, which is A intersection c. It's as good as that. Opt for that as a opt to remember. Now consider a case where you have a union outside and then an intersection inside. Are you willing to try that one out? Okay, so we'll take our union which is outside as a multiplication. So A multiplied by B, and then we'll maintain the sign that is in between there, which is intersection. And then we'll basically go on and put A union C. So these are the two distributive laws. I've tried explaining using multiplication and addition to help you understand. So it's just a matter of understanding what happens under multiplication, then it will be easy for you to basically get to deal with all this. Okay? So proving or confirming this, in a case where they give you a question, they ask you to confirm, all you'd have to do is begin with your left hand side. Okay? State your left hand side is equal to the A intersection B union C, as we can see. And then of course, remember your board mass tells you start with what is in the bracket. So of course, clearly show that you're finding B union C first of all. And then get to indicate what is in set A. Or what I mean is call back the question, which is now the left hand side. A intersection B union C. And then now show your set A, intersect it with what you had found in B union C, and then show your answer. And then on the right hand side, again do the same. What would just now, you can begin with your A intersection B, and then find A intersection C, and then get to find their union. You get the same answer. That's how basically you get to prove the distributive laws, just like we did under associative laws. Very simple concept, right? Cool. We'll talk about more laws under set theory. Some simple things that you'd just have to understand. Okay, this is just like this is like a game for you. I hope you're enjoying, by the way, what you've done so far, because math is very interesting. So A intersection A. This is as simple as A. When you're intersecting a set with itself, what is common is itself. Not so simple, right? So equally when you say you combine a set with itself, union of a set with itself, it's the set itself. Nothing will change. Okay? So this is as good as you're thinking of a set with two elements, 2 and 3. Whenever you intersect it, whenever you find the union, the answer will still be 2, 3. Okay? So those are called idempotent rows. Okay? The other thing is, look at this. Something interesting as well. If you have a set, and then you're intersecting it with an empty set, what's the answer? What's the answer? Look at set A with an element, with two elements, 2, 3, and then you have an empty set. What's the intersection between the two sets? Is there anything common? So it's an empty set. That's an identity law. You can also think of A being intersected with the universal set. The universal set is made up of everything. So consider a case, I like using a Venn diagram to explain this one. So what do you think first of all is the answer there before I tell you the answer? So if you have set A, set B, and then this is the Venn diagram, of course, that's a universal set, right? So set A is, this will just actually teach you how you find the union, the intersection of a set. So I'll shade set A, and then I'll draw the other lines now horizontally to shade the universal set. So where the lines are meeting, where the two lines, the horizontal and the vertical, are meeting, that's a point of intersection. So we'll clearly observe that it's only set A that is common, right? Set A is common. So when you are trying to find the intersection between a set and the universal set, the set itself is already part of the universal set. So that is a common point. Okay? Now a case where you're trying to combine any set with a universal set. So the inverse set, like I've said, already consists of everything. So A is already part of the inverse set. So combining any set with the inverse set, you can't get anything greater than the inverse set. Okay? You need to understand all that. Is there anything else that I never talked about? So everything else we talked about. We talked about associative laws and many more laws under set theory. So with this basic introduction, now we can watch the next video now, which is going to like talk about some practice questions under what we've covered so far, before you proceed on and learn about set builder notation and set interval notation. Let's talk about disjoint sets. What's disjoint, or what are disjoint sets? So disjoint sets is a case where you're going to have two sets within the same universal set, and then these sets don't have an intersection. Okay, take this to be the Venn diagram, and then you've got A and B, and then there is no intersection. So disjoint set, it implies there is no intersection. So we can therefore say the intersection of two sets is an empty set. Okay, that's how it appears. So after this, you're going to have a lesson on the aspect of simplifying sets, given that two sets are disjoint sets. So each time you're taught disjoint sets, just know that the intersection of the two sets are going to be an empty set. Okay. So the common one that common question you're usually given is find the union between the complements of the two sets. So if you're going to look at A complement, it means the region outside A, right? Now if you're going to also try to find the B complement, it would mean the region that is outside what? It's outside B. So at the end of it all, you notice that the entire universal set is going to be shaded. So the union of the complements of two disjoint sets implies it will be what? It will be the universal set. And of course, if we can apply De Morgan's law to that, we know that it can become A intersection B complement. So since you know that the intersection of A and B with disjoint set is an empty set, so the complement of an empty set is basically the universal set. Okay, so that's it about disjoint sets. A specifically says if A is a subset of B, so A is a subset of B, it means A is contained in B. Simplify A intersection B complement, and then the other one that. So I'll start with the first one, which is A intersection B complement. So let's try to come up with a Venn diagram to help us simplify this. So for A to be a subset of B, it means it's contained in B. So I'll draw a small set to represent A, and then contained in another set, of course taking an assumption that this was a proper subset. So that's going to be B, and then this is A. So what are we taught now? So we are taught to find A intersection B complement. In other terms, A without B, because A intersection B complement, for any information, implies it's A minus B. So A without B. So is there any region where we can have A without B? The fact that A is contained in B, it's impossible. So I believe it's an empty set. The other way you can handle this is by shading, first of all, B complement. So I'll shade B complement. B complement is the region outside B. Okay. So notice that it's basically just outside B, and then we have to shade A as well. If we shade A, so is there any intersection between A and B complement? Not at all. If it stands, A is a subset of B. So therefore, this is an empty set. And then we can answer the other part. The other part says we have to find A intersection B union A. So A intersection B union A. I think this one we can even answer without even the Venn diagram. So B union A means you've combined B with A. Now the fact that you've combined B with A and then you're looking for the intersection, since A is part of this part and is part of itself, I think A is a common part. Okay, I think even if it's not a subset, I think that would still stand. So that would be equal to A. If we're to picture this on the Venn diagram, we have B and then we have A contained there. Okay, now if we are to shade B union A, B union A means you shade both B and A. Now you are trying to find an intersection with A, so shade A, so it will only be A as the answer. Okay, now if we're to look at the next one, now here we're taught disjoint sets. Disjoint sets are sets that don't have an intersection. So if you say A and B are disjoint, it means this is the way the i's are going to be shown in a Venn diagram. Okay, that's what it means. So we have to simplify what we have. So in this case, A intersection B, I think that is straightforward. The fact that these are disjoint sets, it means their intersection is obviously going to be an empty set for the first one. And then for B, says A union B. A union B. So A union B means you shade both A with B. So I think that has got nothing to do with, you can't simplify it beyond that, because the fact is every time you're looking at A union B, you have to combine them separately. So when you say A union B, it stands as it is. You can't simplify that beyond that. And then A intersection B complement. So A intersection B complement, it means you shade outside A intersection B. You're interested in the region outside the intersection. Now the intersection is empty. The intersection is empty. So the complement of an empty set is the universal. In other terms, if you're saying intersection B is empty, if you are to shade any part of this universal set, you're going to shade the entire region, because the all universal set is outside the intersection. In short, there's no intersection. So therefore, the complement of the intersection is the universal. And then the last one is A complement union B complement. So this one is equally going to be the universal set. I can show you using the Venn diagram. Let's shade A complement. A complement means you shade the region outside A. So this is the region outside A. So the only part that is not shaded is A itself. Now, if you now combine it with B complement, it means you are now going to shade the region outside B. So at the end of it all, you notice that we've shaded the entire universal set. So when you combine the complements of two disjoint sets, it gives you the universal set. Okay. Now, if you've studied your De Morgan's law, you're able to see the fact that A intersection B complement is equal to A complement union B complement, and that's why the answer is basically the same. Okay, so we're now on C. C is asking us to simplify these in their simplest form. So I'll start with the first one, which is A union B intersection A union B complement. Okay, so this one, we're looking at the intersection. We're looking at the intersection. So if I check this part and this part, what do you think is common? Well, I can see that A union is common in both sides. So I'll pull it out. And then in the first one, what's going to remain after I factorize that, we're going to remain with B. And then we'll get the sign in between intersection, and the other one will remain with B complement. So this is just trying to use factorization, but in the actual sense, I'm trying to apply distributive law. Okay? So what's an intersection between a set and a complement? So one thing that you need to know is the complement deals with this outside part of a set. So if you're going to look for the intersection between a set and this complement, it's either you're within a set or you're outside. It's either you're within B or you're part of the B complement. So therefore, there can never be an intersection between a set and this complement. So therefore, this is A union, an empty set. Combining a set with an empty set is basically just that set, so that's A. That's how you handle the first one. Now we have 2. For 2 we have x intersection y complement union x minus y, and then in the brackets complement. We have to simplify this. So let's start by distributing the complement. So the complement that is outside can be distributed. So by De Morgan's law, this part which is having a complement, the complement would disappear. It will just remain now x intersection y, because the complement of a complement is a complement, so the union becomes the intersection. And then x minus y, there we know that x minus y is x intersection y complement. Now after we distribute this complement, it's going to be there. On the next step, we can have x intersection y, and then intersection, distributing the complement, x becomes x complement, the intersection becomes union, and then we now end up with y. Okay, so is there anything we can do to simplify this to make it look easier? So what we're looking for is we're looking for the intersection between x intersection y and x complement combined with y. Yeah, so the best way to simplify this is by using the Venn diagram, right? Let's try to come up with a Venn diagram. So let's say we have our x and then our y, x and y. So I'll use green to shade the x intersection y, so that's this region. Now the other part requires us to x complement, means you are interested in the region outside x. Okay, so that would involve everything outside x, including part of, let me even use a different color so that it makes more sense. So I'll start by shading x complement using let me use black. So this is x complement. Okay, region outside set x. Now in addition to that, the other thing we have is we are combining it with y, since it says x complement union y. So if I were to shade y, it means I'll still use black. So that's going to involve this part as well, that is y. In fact, I'm supposed to use a different color so that we picture what we're trying to see. So let me use black. So if we use black, this is the way it's going to come out. If I'm to shade y, this is going to be the way it's going to come out. Now we're interested in the common region. So you notice that the common region where the green lines are meeting with the black lines is the intersection of the two sets. So therefore, in other terms, what we are saying is x intersection y is also contained in that set. Why is it so? I think the one way we can actually think of it is the fact that this is the union of the two sets. It means y is completely included. Now the fact that y is completely included, and we're trying to find the intersection with the x intersection y, which is this part, is equally contained in y. So therefore, that's why that region is the common region between these two sets, and therefore this is a simplified form of that expression. Okay, so we have a question, question 3. This is one of those questions where if you look at it, you're like, this question is simple, but as you try to approach it, you see that, okay, it's actually a bit involving than I thought. But anyway, this question is still simple, so feel free to pause the video and just try it out. Okay, so we are taught to illustrate the information given on a Venn diagram. So the question says TG5 has 80 students, 55 take ECN, 56 take BBA, 50 take development, 48 take ECN, which is economics, and BBA, and then 42 take, 44 take that, 13 do not take any. So without any further delay, I can just put 13. they don't take anything. And then I can start from the center. Every time you have to start from the center. Now you notice that in this question we are not given the students who take all the 3 courses, and that's why we're asked on B to determine that. But that is a very essential number that helps us to fill in the Venn diagram. So therefore we use the letter X to denote students who take all the 3 courses. And then we'll go to the parts where we have students who are taking 2 courses. So 48 take ECN and BBA. So that will be 48. Now it's supposed to be without X. We have to remove the number of take all 3. And then we have to check the next one, 42 take ECN and development. So that is 42 without X as well. And then finally we have BBA and development, which is 44. So that has to be 44 without the X. Okay, that's one way you're supposed to approach it. Now, when it comes to where we're given the number of students who take only a single course, we have to remove these regions which are part of the intersection. Okay, so for example, if we focus on ECN, it means we have to remove all these students. Okay, so how do we do that? So for ECN, let's add whatever is part of it. So we have 48. So let me add that. So 48. Let me actually just use the space down there. So we have 48 minus X plus 42 minus X. So let's add that. So 48, this is a 0. 48 plus 42 is going to be a 90. So this is going to be 90 minus X. Now we're supposed to subtract this from 55 because we are taught 55 students take ECN. So 55, we have to remove the intersection, which is 90 minus X. So that would give us 55 minus 90 will give us a negative 35, and then minus X will be positive X because we're distributing the negative. So that will be 55 minus 90 and then plus X. So you end up with, if you start with X, you end up with X minus 35. So for ECN, you have X minus 35. And then for BBN, you have to apply the same concept. So for BBA, we can add as well. So for BBA, we have 48. So if you check BBA, this means we are focusing on this part. Okay, so what do we have there? So we have 48 minus X and then plus X plus 44 minus what? Minus X. Now you notice that this part is equal to 0. 48 plus 44 is a 92. So I have a 92 minus X. So the number of BBA students were 56, so I have to remove 56 minus 92 minus X. So I end up with 56 minus 92 plus X. So that would going to give us, subtract, you're going to get X minus 56, right? Because 56 minus 92 is equal to 36, negative 36. And then the last one, which is development, we are told 50 take development. So we're supposed to remove this part now. Okay. So what we have? So we have X plus 42 minus X and then plus 44 minus X. So 44 plus 42, okay, that's going to be 86 and then minus X, because that and this will subtract to give us a 0, so we're just going for negative X. And then we can equally subtract as well. So from the 50 students that take development, we're going to remove 86 minus x. So 50 minus 86 is going to be negative 86, and then plus x, so which is as good as x minus 56. So we've now computed everything that we needed to deal with under this case. So therefore we can now go on and find the value of x to help us deal with everything we have. So let me just scroll down. So we're told we had 80 students in total, don't forget that. Okay, so let me start. So we're going to add everything together, and we're supposed to equate it to 80. So let's be careful now we compute. So we have 13 and then plus x minus 35 and then plus 48 minus x plus x plus 42 minus x. So far where I've reached is I've reached this part. I've covered the whole part of ECN. Okay, so we can now go to development. We have x minus 36 and then 44 minus x and then x minus 36. All this is supposed to be equal to 80. So let's be careful now we compute there. So let's start with the numbers. We have 13, negative 85, 48, 42, negative 86, 44, negative 86. So we can say we have 13 minus 35 plus 48 plus 42 minus 36 minus 36 plus 44. So that's equal to a 40. So I found a 40. So 40. And then for the x minus x is a 0, x minus x is a 0, x minus x is a 0, so just remain with plus x, should be equal to 80, and then therefore x becomes 40. Okay, so if we are right in our calculations, then x, which is 40, is the total number of students who took all 3 courses. Okay, so x is equal to 40. So you can actually get to fill in the table by substituting in the value of 40 we have. So that part we have x minus 35, so 40 minus 35 is a 5, 48 minus 40 is 8, 40 minus 56 is a 4, 44 minus 4 minus 40 is a 4, that's a 4, that's a 2. Okay, so we should be able to get the answer. So if you try to add the what we have there, so I'll say 13 plus 5 plus 8 plus 2 plus 40, and then plus 4 plus 4 plus 4, so that gives me 80. So if you try to add all these numbers, you're supposed to get 80, which I have. So we're done. find the number of students who took exactly one course. So that would be 5 plus 4 plus, so 5 plus 4 plus 4. So that's 5 plus 8, which should be 13. Okay, 5 plus 8 is 13. So that's how you're supposed to answer question 3. You can apply the same concept to answer question 4. Okay, so you notice that question 4 is very related to the previous question. So basically we use the Venn diagram to simplify the work to help us understand things faster. Now equally here we are told to find the number of people who are using all the 3 methods. Every other information has been given, so let's use y this time around. Okay, we use y, so y will be all the 3 methods. Now we are told a survey was conducted on 70 consumers, so 70 is the total. The result came out as follows: 56 smoked, 56 sniffed, 50 chewed. In addition, 48 smoked and sniffed, 42 smoked and chewed. Okay, so we'll go for both first of all. So we are told 44 sniffed and chewed. Sniffed and chewed, so this part, that's 44. So 44, we have to remove the y. And then 42 smoked and chewed. So 42, we have to remove the y. And then smoked and sniffed, 48. Okay. So now we have to now go into what we are told. So we are told 56 smoked, 56 sniffed, and then 50 chewed. So those are not the actual values we're supposed to put there. We're supposed to subtract from them. So I'll start with smoked. If I look at smoked, I have to focus on this region. Okay. So let's focus there. So we have 42 minus y plus y plus 48 minus y. So negative y plus y is a 0. You remain with a negative y. 42 plus 48. So you know that 2 can be there, it can give us, so that is going to give us a 90. So because 42 plus 48 is a 90. So we're supposed to subtract that from 56. Now 56, we remove this common region. So 56 minus 90 is a 34. So that's a negative 34. And then plus y. So we can remove the 56 and just put y minus 34. So apply the same concepts. You can go to sniffed. Sniffed, we are told there were also 56. Now we have to add everything else that involves sniffed. So that means we are interested in this region. That's within green. So 48 minus y plus y, 44 minus y. So get negative y there. Now we have 48 plus 44. That's a 92. So we're supposed to subtract that from 56. So you understand, if you distribute the negative, you're going to get 56 minus 92 plus y. And then 56 minus 92 is a negative 86. So y minus 56. Y minus 56. And then finally the last part, which is having 50 for chewed. So don't forget that is should. I've just erased that. So 42 minus y plus y plus 44 minus y. So get the minus y, and then again we now have again 42 plus 44, which is 86. We have to remove this from the 50. So 50 minus 86 is a negative 86 plus y. So equally there we have y minus 56. So y minus 56. Were we given any number of people? We are not taking any of the three. Obviously not, because all these were consumers. So we are not given anything about none. So therefore, to find the value of y, we have to just equate to the total, which is 70. So combine everything. So y minus 34 plus 42 minus y plus 48 minus y. So we are done everything in smoked. And then y minus 36 plus 44 minus y, and then plus y minus 36 equal to 70. Numbers we have negative 34, 42, and then 48. So I'm actually punching out on the calculator. And then minus 56 plus 44, and then minus 56 again. So that's a 28 equal to 70. Now the y value. So y minus y is a 0, y minus y is a 0, y minus y is a 0. So it just remains plus y. So therefore y becomes 70 minus 28. So 42. So if that is okay, if we plug in, so if you're confident what we've done is right, then y becomes the answer. So 42 is the answer. Now you can actually try to prove it by substituting. Wherever we add y, we can put a 42. So there, 42 minus 42 minus 34, that would be an 8. So that would mean that there we had 0. 44 minus 42, that would mean that gives us a 2. 48 minus y would imply we had a 6. That would mean we had a 6, because, yeah, 6. And then 42 minus 56, that's also a 6. So if we add all these, we're supposed to get a 70, because the y value is 42. So we can actually try. So I have 8 plus 6 plus 2 plus 6 plus 6. Let me do that again. 8 plus 6 plus 2 plus 6 plus 6 plus 42, 70. So this is okay. This is okay. That's how you are supposed to answer question 4. So we continue now from question 2a. So we are now under a part where we're required to now like shade. So the first one is asking us to shade b minus c. B minus c. So what does b minus c imply? So b minus c means b without c. Okay, that's what you need to know. B without c. So let's start with the first one and see how we're going to handle it. Okay, so let's identify region B. This is all B. Now we have to remove C. So where is C? C is this region. So we have to remove it from B. What's going to remain of B? So it means if we are to shade B, it's going to be this region. So notice that I'm not shading any part. I understand that B goes as far as this point, but because this part is part of C, I can't shade it. That's what it means to be B without C. Okay. Of course, I want to explain if the question was even like B without A union C, you would have to identify the region from the other side. That means would go as far as unshading the part of A, because it's also not supposed to be included in such a case. Okay, but I hope you get the idea of subtraction. And then on the other diagram, we've got B. Now I have to remove C. This whole part is B. Now we don't have to shade C, so only shade B with the exception of C. So we have to make sure we don't shade any part of C, but only B. That's what it means. So we are done for the first part. Now the next one, we are told to shade A intersection B intersection C complement. So I like interpreting these questions as, why it is B intersection C complement, you understand it means B minus C. I think it's faster that way. Or the alternative way would be to distribute the complement. Since we are told we have B intersection C complement, and then we've got a complement outside, we can actually get to introduce it. We can distribute it how? B becomes B complement, intersection becomes union, C complement becomes C. So B complement union C if you want, and then you intersect it with A. But I would prefer the other form, which is by knowing that B intersection C complement is as good as B minus C. So we already shaded B minus C previously. We saw that from the first diagram. This was the region B without C. On the other diagram, it was all around C. Now we are interested, in this case we're now interested in its complement, meaning that we should not shade it. That's what the complement means, we should not shade it. So therefore, if we're not going to shade that region, what's going to be shaded would be everything else. Okay, so we are not going to shade the region which is B without C. That's on the first diagram. And then we're interested now in the intersection of this part with A. So let's shade A. This is A. So the part where the green lines and the red lines are intersecting is the point of intersection. Everything else has to be removed. So first of all, you know, the answer obviously is going to be within A, but then it has to be a point of intersection with the region which is outside B without C. So you can see there's still a part where there are only green lines, which is this part. Okay, because obviously we know that part was B minus C, right? So that's our area of interest. That's how you do it. Then for the other one, if we are to shade now the region outside the B minus C, because what is shaded here is B minus C. Now if you say it's complement, it means we shade the region outside of it. Now the region outside of that point, when we're interested in the region that is outside B minus C and also in A. So obviously if we are to find the complement of that region, which is also in A, find that we are going to shade this region, because if you check where A is, this is A. So if we're going to be interested in the region of A, which is outside the shaded region, then obviously we know what's going to come out is only this part will not be shaded. You'll see. So what I mean by that is the result therefore will be this part and this part. That's the region of A, which is outside B minus C. So that's the answer on this other diagram. And then we're now on the last one. The last one is asking us to determine the intersection of C with A minus B complement. So what is A minus B? It means A without B. This is B. So I have to remove it from A. What remains of A is this part. Now, the fact that we're saying the complement of A without B, or A minus B, it means we're now interested in the region that is not shaded. So our interest is in the region that is not shaded, because we are saying A minus B complement. What we've shaded is A minus B. Now if we introduce a complement, it means we're now talking about the region outside what we've shaded, which is A minus B complement. So the region of the region which we've shaded, which is outside, the region outside what we've shaded is going to be A minus B complement. Now we should intersect that region with C. So therefore, the region which is outside what we've shaded and within C is going to be this part. First of all, it is outside A minus B, which qualifies A minus B complement, and then it is also within C. So that is our answer. So that is C intersected with. The other way we would interpret this is it's the same as C and then minus A minus B. It means remove A minus B from C. Now you know that A minus B is the region of A without B, which would obviously end up this region. Now you have to remove it from C. That's what remains. If we are to look at the other diagram, A minus B, or A without B, we know this is all B. So A without B, obviously. What have I done? Yeah, so A without B is obviously this part. That's a part without B. A without B. Now we have to remove that region from C. So you notice that there's no intersection. There's no intersection. So therefore, all of C will be the answer in that case. All of C will be shaded. So this is how you handle the shading. There's a more complex video, a more detailed video about the shading. You can check it out. So now on the other hand, we're asked now to describe the shaded region. So if you are to look at this part, analyze that region, you notice that A, this is B, and then you notice that this is also A. So you can just simply describe that region to be common between A and B, right? Without any part removed. So it's purely A intersection B. If you look at the other diagram, I can see that X is shaded but I can see that the part of y is removed, so I can just say that is x without y, because part of z is already there. So what is x minus y? Simple, right?
In this video, we're going to go over set theory just by looking at a practice question that requires us to shade the given set. So we've been given a Venn diagram, then we're required to shade A intersection B and many more questions. So we'll start with that. So we have our A intersection B there. So what does that mean? That requires us to shade the region that is common between A and B. So if you are to shade that region, what you're going to have is this part, because that is the region that is part of both A and what? And B. So you look at the point where they are intersecting. So basically this is their intersection point, because this region is part of B, it's also part of what? It's also part of A. Okay, so that is how you get to answer the first one. Then moving on to the second part of the question, it is requiring us to shade A intersection B union C. So I'll write that A intersection B union C. So whenever you're simplifying a set, basically the simplest way of approaching it is by starting with what's in the brackets. So if you look at what's in the brackets there, we are trying to combine B together with what? Together with C. So I'll shade the entire region of B union C. So it would require us to shade the entire region of B. So that is our B. Then we also shade what? The region that is part of C. That's what it means when we say union of B and C. Okay. So now we have our B union C. So we need to find the intersection with A. So let's try to shade A now. I'll use a different color so that we see where they're going to be intersecting. I'll use a blue. So if you shade A, this is A. Okay. So we shaded A. So now if you look at this, we are trying to find the intersection between B union C, which we've shaded in yellow, then A, which we've shaded in blue. So the point of intersection, meaning that where you can see both colors, that is our region that is supposed to shade. So in summary, if you are to draw this, what you're going to have is something like that. You have A, B, and what? And our C. So I'll write that is our A, that is our B, and our C. So what region is having both colors? So if you look at the diagram that we have, it's basically this region. Okay. So you can even shade it. So it's basically this region. The region part of A, which is also part of B union C. That is the intersection region. So basically that is what you're supposed to shade. Okay, let's move on to the third one. So if you look at the third part, it is C minus A intersection B. That is our third question. So we have C minus A intersection B. So we need to understand that this is the same as what? Remember we said if you have A minus B, basically this is equivalent to A intersection B complement, because you're trying to talk about the region that is part of A and not in what? Not part of B. So you exclude the intersection of the two. So C minus A intersection B is basically going to be C intersection A intersection B what? Complement. If you want to understand it better, what we can do is we can shade it. So if we have the three sets A, B, and C, okay, let's say that's what we have. So we have our A, we have our B, we then have our C there. Okay, so C minus A intersection B, it means that we are interested in the region that is part of C. And what is our C in this case? What region is part of C? So this is the region that is part of C. This is the entire region of C. Now we are trying to exclude the part that is part of the intersection of B, A and B. So which one is the intersection of A and B? So the intersection region is this one. So we exclude that part. That is the region that we are excluding. So what we are going to remain with is basically just this part, because we're looking at the part of C excluding A intersection B. So the intersection is what I've shaded in red. So the green part is what we are interested in. So if you want to present it in a different way, you can also say basically it's region of C intersection with what? The region outside A intersection B complement. So if you talk about A intersection B complement, it's a region outside the red part. So this is A intersection B complement. So now we want to find the intersection with C, which will still come out to be what? This region that we've shaded in green. Okay, so that is why we're saying this is equivalent to that part. So now let's try to represent it on the Venn diagram. In summary, what we've said. So basically what we have is, in fact, I've actually even answered the question. Let me just show what I did. So what we have is, we are saying we have our A, we have our B, and our C. So when we say C minus A intersection B, it means that the region of C without the intersection of A and B. And remember we've said for our intersection is basically the intersection of A and B is this region. So we are excluding that from C, meaning that what we are going to remain with is the region that I'm going to shade in a different color here. So what we are going to remain with is this part. We are only excluding the intersection of what? A and B. Okay. So you've shaded C minus A intersection B. Okay. So that is how you approach it. If you want, you can also change a form. You approach it using that form where you say shade C, then intersect it with A intersection B complement. You're still going to come up with the same solution for that part. Let's try to move on. Let's try to look at the fourth one. We see what we're going to shade. So if you look at B minus C, this one is direct. This one is straightforward. So looking at this kind of Venn diagram where we have A, B, and C in such a way, you have your A, you have your B, and your C. So B minus C means a region of B without what? Without C. So we are required to shade B without C. So we're only going to shade the region of B without C. So remember, this is a part of this is part of C. So we are going to exclude it. We are going to exclude this part, which is C. We are only interested in the region of B without it. So what we are going to shade is the entire region of B except the region of B, which is also part of C, because it's saying B minus C. Okay, that's easy. That's easy. So what about if you said C minus B? When they say C minus B, it requires you to shade the region part of C, excluding that which is part of B. Okay, because we are saying that is basically C intersection what? B complement, meaning that you're only interested in the region that is part of C and outside your B. Okay, so we are on this one. So we have A intersection, B intersection, C complement there. So how do you get to shade this one? So what you can do is you can try to simplify what you have first of all. So you have A intersection. So from De Morgan's law, this can become, you distribute the complement. You're going to have B complement union C. So a complement of a complement is basically what? They'll cancel out. The intersection becomes the union, then the B becomes the complement. So basically that is the simplified form of the statement that we have. So let's try to shade that. So looking at the sets that we have our A, we have our B, we also have our what? Our C there. So you have your A, you have your B, and your C. So you want to shade the intersection of A with B complement union C. So the approach that we're trying to use is first of all by shading A, then you come and shade. So let's start with first of all with what's in the brackets. Let's shade B complement combined with C. So B complement, we're interested in the region outside what? We're interested in the region outside B. Let me even put the Venn diagram around. Okay, so that's what we have there. So now, this is our inverse set, by the way. This is our inverse set. So now what are we trying to do? We're trying to shade B complement union C. So which one is our B complement? It's a region outside B. So I'll use a different color for that. I'll use I can use red for B complement. So B complement, region outside B. So every part outside B. So not outside B, outside B. So notice that I'm not shading anything within B. I'm just shading outside B. So now it's supposed to be combined. So union tells you to say combine. So I can continue by shading every region that is part of C. I can even use I'll use the same color since it's the same set. B complement union C. So I'll shade every entire part of C. So this is going to include a certain part of B. Okay. So that region is shaded. Why is it shaded? It is shaded because it is part of C. We are saying the union. Okay, so we have B complement unionized with C. That's what we have. The entire region that we've shaded. This is all B complement unionized with C. So now we need to find its intersection with A. So let's shade A. I can use green for A. So this is our A. Okay. So now our solution is going to be where you are seeing both green and red. And what region is that? So it's basically this region. Okay. So that's the region that we are interested in. So what is the region that we are interested in? And we can even shade it. So let's try to come up with our separate Venn diagram somewhere. Surround. So what we have is we are saying we have our A, we have our B, we also have our C there. So we have our A, our B, and our C. So what region is shaded? It's only this region. Okay. This region is also shaded. Even this part is shaded. Okay. So it's only a small part of the A which is not shaded. So basically, that is our solution there. The other approach that you can use is by looking at it as you have your A. You're trying to find its intersection with B intersection C complement. So what would you say? You know that what is in the brackets there. Let's try to use that approach. We try to see what we're going to have. So we have our A intersection B. So B intersection C complement, if you can remember, is what? It's the same as B minus what? B minus C complement. So what is your B minus C? Basically, if you talk about B minus C, you are trying to talk about the region what? What region are you talking about? The region of B without what? Without C. So if you have this part, your A, your B, and your C. So what region of B minus C do we have in this case? So the region of B without C means that you exclude this part of C, exclude it, then you only shade the remaining part of B. But then that's not the region that we are interested in. So if we are going to shade B minus C, we are going to shade this part. Okay, that is our B minus C in this case. Now we are not interested in B minus C, we are interested in what? In its complement. So what does it mean? We're supposed to shade the region outside that. So let's try to shade outside that part because we are interested in its complement. So what we're going to have is this outside that. So this part. So we're not only going to shade B minus C because we're interested in what? In its complement. Okay. So now we are trying to intersect it with what? We're intersecting it with our A. So let's shade A. So if you shade your A, so now I said where the lines are meeting, basically that's where you have your A. So equally you've seen that it's only this part of A that is excluded. Only this region is excluded. So basically we're going to shade this region, which is going to give us what we have on our right. So whichever method you work with, you're still going to have the same solution. Okay. Let's try to look at the final one. So for the final part of the question, what we have is we have A complement intersection B minus C. So this one is straightforward. We can just draw what we have. So we have A, we have our B, and we have our C there. So this is our A, that is our B, and that is our C. If you want, you can even draw. Okay. So this is our universal set. So we're trying to shade B minus C. So I will shade B minus C using a different color. So for B minus C, it means region of B without C. So remember, this entire region is part of C. So we are trying to exclude it from B. So our B minus C is just going to be that region of B without what? Without C. Then for our complement, we're going to use a different color, meaning that we're interested in the region outside what? Outside A. So we're not going to shade in A, we're only going to shade outside it. Let me even use a green there. Okay. So outside A. So notice that this region outside A is this part. Okay, because this is where our A is passing. So outside that, that is what we are going to what? To shade. Okay. So now, where exactly are the colors meeting? So if you look at where they are meeting, it's basically which part? So it's basically this part. This is where these lines are what? Are meeting. So that is our region of our interest. The region that is outside A and part of B minus what? B minus C. So in summary, what we're saying is it's this part. If you try to show it clearly, what you have is so if you look at the approach that I've been working with, it requires you to have a draft, then you get to have your final solution that your lecturer is in need of. So it's basically just this part, and that is your shading. Okay, so that's it for this video. Thank you very much for watching. Check out the next video that is going to answer the same, shade the same sets that we have on a different diagram that is going to come out like this, where you have your C inside there. So here what you have is you have your A, you have your B, then you have your C. So we're going to shade the same ones in the next video. Make sure you check it out. Thank you very much.
In this video, I'm just going to introduce you to set builder notation. So what is set builder notation? So set builder notation is basically just a mathematical shorthand notation of presenting a set. So when you look at this, I'll just explain what they mean. So this symbol, we learned that it stands for a member of. So I'm trying to say X is a member of. Now this symbol Z, it stands for integers. So you know that we have integers, know that we have real numbers, know that we have rational numbers, denoted as Q. Yeah, and of course the other kinds of numbers. So there's a video you're supposed to watch after this, which will deal with sets of numbers. You understand all the different kinds of sets that are there for your assistance with the progress. So now, this other symbol that you're seeing there, which is like a line, that is denotes, it's just the same as such that. So in some textbooks, or it's also okay for you to say X is a member of integers, and then you search that -2 is less than or equal to X less than or equal to 3. I believe you're okay with these brackets are curly brackets. So they can ask you to list the elements of, if they've given you such bit notation, or they can ask you to describe to, or they can ask you the other way around, which is they give you a list and then they ask you to write inside bit notation. So in this case, if they ask me to list, I know what integers are. Integers are negative and positive numbers. So we are saying -2 is less than or equal to X. So -2, -1, 0, 1, 2. I'm ending at 2 because it is less than 3, not less than or equal to 3. So that is how you get to deal with set bit notation. Now, giving you another example, consider a case where you have the same kind of a set. Now let's say you have let's say 2, 4, 6, 8. So if we end there, are you able to describe these? So we're able to see that first of all, X is, these numbers that are there are what? Are even numbers. Okay, we understand what even numbers are. What else can we see? we can see that these numbers are less than what? They are less than 10. So we'll say x is a member of even numbers. There's no symbol for even numbers that I know of. So such that x should also be less than 10. So these two conditions basically describe the numbers that we have there. Even numbers, and then these even numbers are less than 10. So this is set builder notation. Okay? Many things apply. So you can watch the next video now, which now has got about more than 6 examples on the same to help you understand. And of course, the video will be a summary of everything you've learned so far. After watching the next video, you can now feel free to attempt the practice questions on set theory to just test your understanding. And if you have any questions, feel free to get in touch with our tutors. Here we are told the universal set is x is such that x is a member of natural numbers, and then we are told 1 is less than or equal to x, and then x is less than or equal to 20. So we know natural numbers are counting numbers. Now we are told 1 is less than or equal to, so it implies 1 is included, and I said natural numbers start from 1. Okay, so this tells us the fact that 1 is included and 20 is included because of the equal dash on the bottom. So we're going to have numbers 1 to 20 being our universal set. Okay, and then for the other part, we are told for A, we are told x is such that x is equal to 2k. So x is equal to 2k for that part, and then x is less than 20. Okay, x is less than 20. And then we are told k is of course a member of natural numbers, right? So that's the set we are looking at now. How do we handle it? So we know it's going to consist of natural numbers, so it's going to be consist of counting numbers. That's 1. Okay, now it should be in the form of 2k, so x should be in the form of 2k. So k is a natural number, so we'll start with the list we have. The smallest natural number is 1. So to find the x values which are representing members, we'll be substituting our as k. So starting with 1, we're going to have a 2. If you plug in a 2, you're going to have a 4. So you see that it's going to be double. So 3, now 6. The difference of a 2 again, 8, 10, 12, 14, 16. Okay, so we have 16, we have 18, and then we have 20. So we can't exceed 20 because our universal set is only from 1 to 20. So anything beyond that point is not part of the set. So therefore, our members of A include, so in fact we were told x is less than 20. Let me not forget x is less than 20. So this 20 is going to go away. Only the ones that are less than 20, unless if it was saying less than or equal to 20, but it just says less than 20. So set A therefore it's having even numbers from 2, 4, 6, 8, all the way up to 18. So our universal set is having numbers from 1 to 20. So now we have to answer these questions based on what we know. So the first one is asking us to find A complement intersection B complement. So from De Morgan's laws, we know that this is the same as A union B complement. So I feel this is easier to handle because I can just find first of all the union of A with B. So A union B means I combine the elements in A with B. So we have, in B we have 1, in A we have 2, in B we've got 3, and then I will have 4, 6, 8, and then of course 8, we have 10, we have 12. Remember A is having even numbers, so that's why it's 10, 12, 14, 16, 18. Now in B we also have 19 and 20. So let me move this bit to the side. So we have 1, 2, 3, 19, and then of course 20. So we've combined the elements of A with B. In A we have 2, 4, 6, 8, which are 2, 4, 6, 8, 10, 12, 14, 16, 18. And then in B we have 1, 3, 8, 19, and 20. So they are all part and parcel. Okay. So now the idea is to find the complement of each. So complement of this, it implies we remove these ones from the universal set. So what is going to remain of the universal set? If we remove 1, 2, 3, 4, I can see 5 is missing. I can see 7 is missing. I can see 9 is missing. 11, 13, 15, 17. 18 is there, 19 is there, 20 is there. So 5, 7, 9, 11, 13, 15. These are the answers. This is the complement of the union of A with B. Okay? You can still answer it the other way by first of all finding a complement, which means remove the A's from the universal. So if you remove 2, 4, 6, 8, you're going to remain with 1, 3, 5, 7, 9, 11, 13, 15, 17, 19, and I think 20 as well is not part of A. And then B complement, you remove 1, 3, 8, you're going to have 2, 4, 5, 6, 7, 8 is there, 9, 10, I think all the way up to 10, all the way up to what? 18, since 19 and 20 are there. So this is going to be in the order of 11, then 17 and 18. So if you try to find the common elements, you can see 5 is common, 7 is common, 9 is common, 11 is common. So 13 is of course there, 15 is of course common as well, so is 17. So 5, 7, 9, 11, 13, 15, and 17, which is too matches up with our answer. So whatever is easy for you, go for it. And then for part 2, we are told to find A union B. So always start with what is in the brackets to make things easier for yourself. So A union B means we combine A with B. Let me just take you back. I think we had this already. Where was A union B? Already erased. So A union B means we combine the elements with A and B. So we have 1 in A or in B, and then we have 2 in A, so 2, then 3, and then 4, and then 6, and then 8, all the way up to 18. So it will be in the order of even numbers, right? So 2, 8, 6, 8, 10, 12, 14, 16, 18, and then 19 and 20 coming from B. So we're going to intersect this with C. Now where is C? C is having members that. So you can actually list them down there, but I want to list them down. I don't have enough space. So 1, 2, 6, 8. Okay. 1, 2, 1, 2, 6, 8, 9, 11, and 15. That's it. See? So we're trying to find the intersection between these two sets. So what's common? I can see 2 is common. I can see 6 is common. I can see 8 is common. I can see, I think it's only 2, 6, and 8. The reason is simple. Set A union B is more of even numbers and only about 3 odd numbers, 1, 3, and 19. Okay, so the other even numbers like 9, 11, and 15 are not there. Well, I can see 1 is also common. I don't know how I missed it. 1 is there. 1 is there as well. So therefore, it's 1, 2, 6, and 8. And then if you check the third one is having A minus B union C. So A without B union C. So our A is having members like 2, 4, 6, 8. So even numbers from 2 all the way up to 18. And then without B union C. So B union C means you combine the elements in B and C. So I can see in C we have 1, 2. And then in B we've got a 3. And then you can have a 6, 8, 9, 11, 15. And then we can have 19 and 20 coming from our B. So we've combined all the elements there in the two sets. 1, 3, 8, 19, 20 are there. And then 1, 2, 6, 8, 9, 11, 15. Now we're trying to remove these ones from A. Now let's remove, so let's identify the common elements. 2 is common. And then 6 is common. And then 8 is common. Then 9, 11, 15, no. So these are the only common elements. So if you remove them, what's going to remain of A will be 4, 8, no, 8 is common. So 4, so 10 of course, 12, 14, 16, 18, which are not there. These are the only elements of A that are going to remain. If you want, you can interpret it as A intersection B union C complement, meaning that you find the complement of B union C and then you intersect those elements with A. So B union C complement means you remove elements of B union C from the universal set, and what remains should be intersected with B union C, or with A, sorry. Yeah. And then for number 4, which happens to be the last one on this part, is A union B, and then we have a complement. So I think I already explained this one. This is the same as the first one, right? Yeah, I said that is the same as A union B complement. So I think it's not necessary for us to answer it, so feel free to pause the video and try it out, since I showed you how you can go about it. So just find A union B first of all. A union B means you combine the elements of A with B. So A is having 2, 4 up to 18, and then B is having 1, 3, 8. So it's like we're just going to add the B to the A. So the B is having 1, and then A is having 2. The B is having a 3, and then we have 6, 8, 10, 12, 14, 16, 18. The A ends there, but we also have 19 and 20 from B. So we have to find now the complement of this, meaning that we remove these elements from the inverse set. The inverse set is having members from 1 to 20, so we're going to remain with, I can see a 4 and a 5 are missing at that point, so 4, 4 and 5, 7, 9, 11, 13, 15, 17. So these are the elements that are not part of A union B, but are within the inverse set. And you can do a bit of some counting. The members are supposed to be 20. We have got 20 elements in the inverse, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So we are right. That becomes our answer. If you have seen a set being represented on a number line? And do you basically understand what it means when you look at such a set? So here with me I've got a diagram that is demonstrating what we are going to talk about in this video. So there are some cases where it is shaded, some cases the endpoints are not shaded as demonstrated there. So basically we call this set interval notation. So set interval notation basically deals with a study of real numbers. So you need to understand what real numbers are for you to be able to understand the important idea. So we have what we call infinite set. So an infinite set is a set that has got unlimited elements or members. You're not able to list them. A finite set, which we basically represent using what we call the roster form, where you get to list the members of a given set in that form, for example. That is an example of the roster form. Of course, even under roster, you can also represent and also unlimited. For example, I can put dots there. It becomes infinite. But in most of the cases, we get to deal with a study of real numbers. That's when we basically work with set interval notation. So this is called roster form. Now, think of a case where you're trying to think of real numbers between 1 and 2. So if I ask you to list the real numbers between 1 and 2, one thing that you need to understand is there is unlimited numbers between 1 and 2 in terms of real numbers. So a number like 1.1, a number like 1.0, a number like 1.001. Notice that I'm coming up with a lot of numbers that you didn't even think about in terms of the numbers between 1 and 2. So what we are saying is we have unlimited, because somebody may decide to say 1.000, add a lot of zeros, 1. So now let me ask you a very interesting question. What number comes immediately after 1 that lies between 1 and 2? I know some of you may say 1.1, but what if I say 1.01? Again, somebody may say 1.001. Somebody may continue adding zeros before the 1 there. So we basically don't know. That's why we now use set interval notation to represent our understanding of infinite set that deals with real numbers. Okay, so now let's try to understand the notation that we basically work with when dealing with set interval notation. So looking at what we have, okay, so think of a set where we have a set between 1 and 2. Now, the interesting fact about this set is going to be 1 and 2 are not supposed to be part of a set. You think of that. Imagine 1 and 2 are not part of a set. So that would mean we don't have to shade the endpoints just like it is. So this set A is going to be 1 and 2. So now notice the kind of brackets that I'm using. I'm using the curved brackets. Okay, so I'm using the curved brackets. So curved brackets are used to indicate when the endpoints are not shaded or when the end numbers are not part of a set. So in this case, what it means is set A involves or consists of numbers between 1 and 2, where 1 and 2 are not included. Let me decide to change something about it. What if I put such a bracket on that end? So what kind of a bracket would require me to shade at the endpoint where we have a 2? And that indicates or tells us to say set A is made up of numbers after 1, including 2. Now 1 is not a member of set A, yet 2 is a member. That's the difference there. Okay, so we now know what it means when we've shaded and how we basically get to represent that. Now assume they wanted us to find the complement of set A. So that would require me to draw again on top. Now in this case, we'll assume our inverse set consisted of numbers from 0 to 10, where both 0 and 10 are included. So that would mean that we know that a complement of a set is made up of elements outside that given set, but within the inverse set. So what numbers are, or what elements are outside A, but within the range 0 and 10? So we have a 0 this side, and then after 2 we need to make sure we end up where we have what? Where we have a 10. So we've shown the entire universal set. So the complement is going to move from 2 up to 10, and then from 1 up to 0. Now, notice that the endpoints, according to the universal set, we have these brackets, which indicate that 0 and 10 are part of a set. So we'd have to shade the endpoints. Now, the points that are attaching to our set A, we said when we've not shaded the endpoint, for example at 1, we've not shaded that part. That tells us to say 1 is not part of A. So whenever an element is not part of a given set, but it is part of a universal set, it is supposed to be part of a complement. So we would have to shade 1, meaning that 1 is part of a complement since it is not part of A. And then the opposite is true. If you check here, 2 is part of set A, so it cannot be part of its complement. So a complement will not have 2. Now, how do we get to present our answer in this case? So our answer becomes a complement from the left side. 0 is shaded, so say 0. So I'll use this kind of brackets. 0 all the way up to 1. Now notice that 1 is also what? Shaded. Now there is a gap in between the complements, so I'd have to use a union to combine them. And then we're starting from 2. 2 is not shaded, all the way up to 10. 10 is shaded. So basically that's how you present our solution. Okay, that's how we basically get to present our solution, using intervals. Now, with that understanding, we know what a complement is and we know what a set is. So now look at the initial diagram that we had from start. So I want you to pause the video and now try to represent our sets A and B. So looking at set A is moving from -4 up to 2. So looking at -4, the endpoint is shaded. So are we supposed to use this kind of a bracket or a curved? So use this kind of a bracket to show that -4 is part of the set. All the way up to what? All the way up to 2. Now are we shading 2? 2 is not shaded. So what kind of bracket are we going to use? We'll use a curved bracket. That is, this is our set A. So you say A is equal to that. Now our set B is moving from where? Is moving from -1 all the way up to 4. So -1 will be shaded because of what we're able to see, and then 4 will not be shaded because it is not shaded, so we'll use a curved bracket. So I believe we now understand how when we use a curved bracket and when we don't use it. So with that understanding, let's try to find now, for the sake of examples, let's try to find the intersection A and B. Now, unlike the other example that we considered, in this case, let's consider our universal set to be real numbers. So real numbers means we are moving from -infinity to positive infinity, from affinity to infinity. Okay. We'll start first of all by finding the intersection of A and B. So when we are talking about the intersection of A and B on a number line, it is very important, even when they've not drawn for you a number line, I would advise you that you get to basically to do it for yourself. So in this case, assume we are given what I'm from erasing there, and then we drew our number line. Now want to find our intersection. So we can find our intersection by drawing the region that overlaps the two sets. So if I shade this region, this is the region that is overlapping between the two sets. It is the region that is common between A and B, as we can clearly see. Okay. So from here up to that point, that is the only region common between A and B. So we are considering the region in between. So we'll notice first of all we are starting from -1 up to 2. Interesting. Now, how do we know what we're supposed to shade at the endpoints? The first thing I'm going to ask you is, when you look at what we have, consider -1. Is -1 part of A? We can say yes, because it is between -4 and 2, because we know that our set A is moving from -4 all the way up to 2, and then -1 is between -4 and 2. So we can say -1 is part of A. Now, is it part of B? So at the endpoint -1, set B is shaded, so it indicates to say it is also part of B. So since it is part of both A and B, it is part of the intersection since it is common. So we'll use this kind of a bracket. Now, we'll check 2. The first question is 2 part of set A? Set A is moving from -4 to 2. Now at 2, we can clearly see that it is not shaded. So it implies that 2 is not part of set A, since at the endpoint 2, A is not shaded. So it is not part of the set. So therefore, A does not have 2. So 2 is not a member of what? A. What about B? So notice that 2 lies between -1 and 4. So 2 is a member of what? 2 is a member of B. But it is not part of A. So it is not part of the intersection. Why? Because it is not in A. Intersection involves elements that are part of both sets or all the sets indicated. So we'd have to use a curved one, implying that our intersection moves from -1 all the way up to 2, but 2 is not included since it is not common. It is not part of set A. Okay. And assume this kind of a same question, they ask you to find the complement, where they give you A intersection B in brackets, and then they ask you to find the complement of it. So you know that I can even erase. Okay, before we consider such a question, okay, let's consider it. So notice that we found our A intersection B to be from -1 to 2, and then we said our answer was -1 to 2. So -1 is shaded, 2 is not shaded. So if this is our A intersection B, now they want us to find the complement of it. So we'd have to start from here going this side, and from this side going the other side. Now we'll have to observe something. Observe that -1 is shaded. So -1 is part of A intersection B. It cannot be part of the A intersection B complement. So we'll leave it as it is, unshaded. On the other side, we can clearly see to say 2 is not shaded, so we can shade the complement. So the way it is, if you look at the set, if you have set A, whatever is in the A complement is what is outside. It cannot be inside and outside. So that's why we are saying if it is shaded, it cannot be shaded on the other side. So it's like you basically get to do the opposite. So if a set itself is shaded, the complement is not supposed to be shaded, and that's basically what we are observing. The set is not shaded, the complement is shaded. The set was shaded, the complement was not shaded. Now, observe at the endpoints, I'm putting arrows there. Why? Because in this case, we don't know where the universal set is ending. We are using infinity and affinity. Now, in all cases, infinity and affinity should never be part of a set. So therefore, say, this representation or this A intersection B complement going to our left hand side is moving from -1, and -1 is not shaded. So I'll use a curved bracket all the way up to -infinity, and I've said -infinity will never be part of the set. Now we'll use union to combine the other side. The other side is starting from a 2, and we've shaded it. So we'll have to say 2 all the way up to +infinity, because our universal set in this case is a set of real numbers. In the other case, we add our universal set ending up to 10. That's why we had to put 10. In this case, it is a universal set, is the set of real numbers. Okay. So basically, those are basically the simple ideas that I would want you to know. And I think one more thing that I would want to highlight is how we basically gets to handle the union of a set. Okay. So remember our set A moved from -4 to 2, and then we have another one from -1 all the way up to 4. So this part shaded, this part shaded. This is our A, that is our B. How do you get to find A union B first of all? That's the last part of the question we're handling. So the way you get to handle it is, in a case where you have an intersection, there's an overlapping region, just get the endpoints. So in this case, we'll consider from -4 all the way up to 4. Our answer becomes -4 all the way up to 4. Now we'll consider the endpoints. This endpoint is shaded, so we'll use this kind of bracket. That endpoint is not shaded, we'll use a curved, since it is not shaded. That is how we get to under the union of sets on a number line. Now think of a different case where we get to where there is no overlapping. Okay, assume this one is ending here. Maybe for interesting sake, I can even put something like this. So if I give you such sets A and B, do you think there's any intersection there? Notice that -1 is not part of A, and then it is also not part of B. So in this case, there is no intersection. There can only be an intersection if both ends are shaded. That's when you can have an intersection. Now, that is not our interest there. Now, imagine our set B was ending at 2. And then they want us to find the union of two sets. This is what is very important for you to understand how we get to handle that. So our set, there's no intersection here, so we cannot just get endpoints, because that would include the region that is missing, but there's a region that is missing. So in such a case, the region that is missing, we basically get to put a union in between. So our answer will just be set A is moving from -4, where -4 is shaded, up to -1, where -1 is not shaded. So we'll combine that using the union, and then 2 is shaded all the way up to 4. 4 is not shaded. So this is a representation of a case where there's a gap, where there's no intersection, how you get to represent the union. And basically you've noticed this because this is basically what we are using when we are dealing with a case where we are finding the complements of a set, where we say the complement is going this side and the complement is going this side. So we use a union to combine the two sides, and that is basically the main idea that lies behind set interval notation. Here we are taught to write the given intervals in terms of set beta notation. So in case you're new to set beta notation, this is a case where you say x is such that x is whatever, x is a member of what and what, so all that. So it's important to understand that when you see this kind of a bracket, a square bracket, it implies a number is part of a set. Okay? And then when it's like this, then it's open, it means 3 is not part of a set. I don't know why we call it open, but we're supposed to rather say it means 3 is not included. And then the other thing that you need to understand is this is an interval, so it involves real numbers. So it doesn't necessarily mean that we only have numbers 5, 4, -3, up to 3. No, it means we have all the numbers between all the numbers that we might imagine, irrational numbers, they are a part of the set. So for the first one, where we have our A being equal to from -5 to 3, so I'm going to say A is equal to, so x is such that x, maybe let me not start with x. So we are moving from x is such that we have from -5, right? X is such that -5 is less than or equal to, because -5 is included, is less than or equal to x, and then x is less than 3. And then we also know that x is a member of real numbers. Okay. For B, feel free to pause the video and try it out. So we are from 4 to 7, they are all not included. So x is such that 4 is less than x, and then x is less than 7. And then of course don't forget x is a member of real numbers. And then for C, both 0 and 4 are included, So x is such that 0 is less than or equal to x, x is less than or equal to 4. X is also a member of real numbers. And then finally the last one, which is d. Negative 2 is not included, so d, x is such that negative 2 is less than x, x is less than or equal to 6, and then x is a member of real numbers. I think these are the 4 that you need to handle. Very simple, right? Simple and straightforward. Now, when you look at B, B is now involving the set interval notation questions. Okay, now there's one that we need to interpret, set C, which has been given in the set beta notation. So x is such that x is less than or equal to 10, and then x is a member of real numbers. So that means C is negative infinity all the way up to 10. 10 is included, like that. So we're interested in the numbers less than 10. Okay. So now A intersection C complement is the same as A minus C for any information. So let's come up with a number line there, and then want to find A minus C. So we have set A and C. So set A is from negative 7 to 3, and then set C is from negative infinity to 10. So let's say 10 is somewhere there. So if I were to put set A, it's going to be from negative 7 to 3, and then 3 is included, so I'd have to shade inside of 3. Okay. And then this is set A, and then C is from negative infinity to 10. So I can just draw a line. 10 is included, of course, so we can actually shade there. And then this is going towards the negative infinity. Now the question is asking us to find A without C, A minus C. Now, do you think there is any region of A that is without C? I don't think so. There is no region of A that is without C, because as we can see, every part of A is in short, from what we've written here, A is contained in C. Okay, so it's not possible. Another way you can think of this is find C complement. If you're going to go by that method where it says A intersection C complement, remember what we're trying to do here is the fact that we're trying to find this set. So A intersection C complement. So A is from this point to that. And then C complement obviously is going to be, if you check the inverse, it is a set of all real numbers. And so all the way up to negative infinity, it's contained in C. So therefore the only part we can have for C complement is from this point, where 10 won't be included because it's part of C. So C complement will just be from 10. Okay, so C complement will be from 10 all the way up to positive infinity. Now, is there any intersection between that set and A? There is no intersection, so it is still an empty set, whether you go by this method or you go by removing C from A. So if we are to remove C from A, it means you are looking for the common region, which is this region. Now remove it. Let's remove the C part. If you remove it, nothing will remain of A. So A minus C is an empty set for the first one. Let me not erase that. And then we can now look at A minus B, which is the second one. A without B. So A without B. For B, what we have 0 to 8. So our A is from negative 7 to 3. And then our B is going to be from 0 to 8. So I'll start with A. This is our A. and then this is our B. So which parts are shaded? So for B, no part is shaded, and then for A, the part that's shaded is for 3 due to the kind of bracket we have there. So we're trying to find A minus B, or in other terms, A without B. Remember, this is your A. So which part of, so shade the common region. This is a common region. So if you're going to get a region of A without B, it means remove this common region. What's going to remain of A is going to end at this point, at 0, that is. So A is going to be from -7 all the way up to 0. Now the question is, if you check at that point of B, it is not shaded. So it means as we remove B from A, that point is not being removed, so it's remaining shaded. So 0 is part of A without B. Okay, so I'm actually supposed to say A minus B, which you can actually show now on the number line. It's going to be that region up to this point. That is your A minus B. Okay, if you want, you can go by the method of trying to interpret that as A intersection B complement. So that would require you first of all to find B complement, which will be this point going this way, and then that point going that way. So any intersection between that set and set B, or and set A, so it's only going to be this part, obviously, which will still match up with our answer. Okay. We can now move and look at number 3. So if you have to look at number 3 is dealing with A intersection B union C. So when you have such complex questions, I advise taking it step by step. Since A has already been given in the question, let's try to focus on what is in the brackets. So we have B union C complement. Let's come up with a number line first of all. And then what we have there is our B is from 0 to 8, our C. So don't forget that our C was from -infinity all the way up to 10. So our B is from 0 to 8. And then we're trying to find our C. Our C is from -infinity to 10. So let me do this. Let me make that 10. I can put 8 somewhere here. So let me draw a line for C. C is from 10 all the way inside. Okay. So that is for C. And then for B is from 0 to 8. And then the or not part. So our goal is to find B union C complement. So we're going to combine B with C complement. Now C complement, since this is going all the way up to -infinity, the only part that we are left with from the set of real numbers is from this part. We're going to shade because 10 is not shaded, so all the way up to +infinity. That is for C complement. That's the only part of C complement. Now we're going to combine that with B. So if we are to combine, what we're remaining with is B itself and that part. So I can remove the C now. We're not interested in the C. So the union of B and C complement is what has remained. This part plus that part, their part. So if you had to present that in terms of a solution, it would mean it's just as good as 0, 8, union, and then from 10 to +infinity. That's what B union C is actually. And then, so we're trying to find out the intersection with A. So where is A? Now A is from -7 to 3. So from -7 to to 3. So 3 is somewhere here, possibly. So if we are to show A, -7 to 3, so -7 and 3. So that is going to be set A, and then 3 is shaded. Okay, so we're trying to find the intersection between the two sets. So the only region that is common is this part, as we can see. So therefore, since this part is unshaded, the common part will be unshaded. Okay, and then that part will be shaded because that endpoint is shaded. So what is the answer? Now, in terms of writing the answer explicitly, the answer is from 0 all the way up to 3. Okay, that's for number 3. Can move and look at number 4. So let me actually start with the last one, which is easier. So when you have A complement intersection B complement, the Morgan's law tells us that is the same as A union B in brackets and then a complement outside. So if you have to combine A with B, let's first of all put A and B together. So A is from -7 to 3. Okay, and then B is from 0 to 8. So B is from 0 to 8, and then we have -7 to 3. Let me draw the ending part. So -7 is not shaded, 3 is shaded, that is for our A, and then our B, no part is shaded. Now we're trying to find, first of all, what is inside the union of the two sets. So the union means if we combine these two sets, it's going to be from this point. Since there's no gap, since there's an intersection, it means all the way from -7 to 8, that is our union. Now to find the complement, it means, to find the complement of the union, it means what is outside the entire region we have, but within the universal. So it's going to be from that point shaded all the way up to positive infinity. This point equally shaded because this is also not shaded, so all the way up to negative infinity. So that gives us our answer. So what is negative infinity to -7, and then 8 to positive infinity. So our answer therefore is negative infinity to -7, -7 included, union 8, positive infinity. Okay, now we can answer now number 4. Now number 4 is A complement minus B minus C in brackets. Now there's a complement outside, so I have to distribute that complement. So if I was to start with what is in the brackets, A complement, this complement distributed to whatever is in the inside. A complement, the complement of complement will be A. I think before I do that, let me do this. So I'll say A complement, and then this minus can be taken into an intersection. Now when it turns into an intersection, it's supposed to come with a complement that should apply there, because I believe you know that when you say B minus A, it's the same as B intersection A complement. So the minus becomes intersection, the complement applies to the other part. So equally here, this minus will apply as a complement on that region, and then of course there's still a complement outside there. So A complement, we can now distribute the complement. So this will become A, by intersection becomes union, and then this complement will disappear. It will just be B minus C. I think this is easier to simplify, right? Okay, so I can easily simplify this. So it means all we're doing is we're combining A with B without C. So I recommend starting with what is in the brackets, and if you do, b is from 0 to 8, and then c is from negative infinity to 10. Let me actually do this. This is negative 8, no, positive 8, and that's 10. So I have from 10 all the way up to infinity. 10, up to infinity. 10 is included, so that is for C. And then B is from 0 to 8. So when you say B minus C or B without C, what do you mean? So you are trying to remove C from B. Now if you check at B, B is very small. So if you're going to remove C from it, then nothing will remain of it. So I think we're now remaining with an empty set. So this is basically just equal to A. And therefore, your A is just from negative 7 to 3. So from negative 7 to 3. So that becomes the answer. Okay. So if everything we've done is okay, this is the final answer in our simplification. Alright. So let's move on to question 7 now. Alright, so we're on question 7 now. So question 7 is focusing on the aspect of converting recurring decimals to a fraction. So in form of a over b, where both a and b are integers. Okay. So we'll start with the most basic ones to help us understand how we are supposed to go about it. So the very first one, 1.25, how do you take it to a fraction? So you're going to multiply by, in this case, how many decimal places do we have? So we have 1 and 2. So we can multiply by 100 and then divide by 100. So the idea there is, if you multiply both the top part and the denominator by 100, you're not changing anything. Okay. So you're going to have 125 over 100. Think of a common denominator there, or a common factor that we have. Divide by 25, there it's going to be 4 times, that's going to be 5 times, 5 over 4. So if you have a calculator, you can try it out, even just by dividing 4 into 5, it's 1. Remainder 1, you can't put a 10, so 2, remainder 2, and then if you add a 0 there, it's going to be 5 times. So the answer is 5 over 4. So it begins to become interesting when you look at number 2. So number 2 is the case where I have now recurring numbers. So recurring implies not ending. So sometimes it can be denoted as 0.6 recurring. There's no difference. Okay. So how do you go about it? How do you answer such a question? So we're going to handle it this way. So we'll let our x be equal to 0.6 itself, 0.6 recurring. Okay. And then for the next one, since we know that only 6 is recurring once, so since we have 0.66 recurring, so if we're going to multiply by a 10, it means we're going to have 10x on the left, and then on the right, it means the decimal point to move once towards the right, so it becomes 6.6. Now, still, the 6s are going to be recurring, they will not be ending. Okay, now at this point you can subtract. Okay, so 10x minus x, and then 6.6 recurring minus 0.6 recurring, So this is going to be 9x is equal to, now when you have 6.6 recurring being subtracted by 0.6 recurring, you are very confident there that you're going to have this part is going to cancel out, which is actually the main focus, and then you're going to have a 6. So you're going to have 6, x is going to be 6 over 9, and then you can divide by 3 on top to have a 2, on the bottom is going to be a 3. So 2 over 3, you can have a calculator there, try it out. It's going to give you 0.6 recurring. Okay. So we can apply the same ideas to the other questions we have. Now, I'll skip number 3, derivative, because I want you to get one concept here. Okay? So let me answer number 4. So when you look at number 4, what we have is 0.81, 81, 81, 81. So what I'm seeing is, what is repeating is 81, 81, 81, 81. And then this is coming up continuously. Okay? So we can just summarize it as 0.81 recurring. So in such a case, you apply the same concept. You let your x be equal to 0.81 recurring. Now, in this case, it's going to be different because we want to ensure that the entire repeating term crosses to the left-hand side. So for the previous case where we only had the 6 recurring, we will only multiply by 10 because we knew the recurring term would proceed to the other side. Now in the case where we've got 2, you would have to multiply by 100. You have to multiply by 100 so that it can move twice, so that you can end up with 81.81 recurring, right? So multiply by 100 both sides, you're going to have 100x is equal to, so this entire term would have moved to the right, and then the recurring part will still remain. Now, equally, we're going to do the same. We'd have to subtract now. So 100 minus x is going to be 99x, and then 81 recurring minus that's going to just be 81. So we're going to have x is equal to 81 over 9. Okay. Now I believe you understand that 9 times 9 is basically equal to 81 if I'm not mistaken. And then so you can divide both sides, you can divide both the numerator and the denominator by 9. So the top part is going to be 9, and the bottom is going to be 11. So you have a 9 over 11. Okay? So this is how you're supposed to handle it. If you divide 9 by 11 on your calculator, you're going to get 0.81818181. So applying what we've learned so far, feel free to try out number 5. Feel free to try out number 5. Okay? So I'll handle it. Negative 2.71 recurring. So you will apply the same concept. Let our x be equal to what we have, negative 2.71 recurring. Okay, so the entire what you need to ensure is before you do anything, you have to ensure that the recurring part is only equal to, you have to ensure that the recurring part is the only part appearing on the right side of the decimal, right? So what you have is, we can move it by multiplying by 100. Since we only have 2 numbers recurring, we'd have to multiply by 100. So we're going to have 100x again being equal to, so we're going to have negative 271 and then 0.71 recurring. The basic idea is what that number is, the way it's coming out is coming out like this. So after multiplying by 100, the decimal point has moved there. So that's why we're saying 71 recurring. Now if you're going to subtract there, you're going to have 100 minus x is going to be 99x. Now on this side where we've got negatives, now we'd have to be very careful. So you have negative 271.71 recurring minus negative 2.71 recurring. So the recurring parts will subtract, and then you're going to have negative 271, right? Negative 271. Now the fact that you're going to be subtracting, the other one is going to end up as a positive. Okay? So essentially your answer becomes negative 269, right? Negative 269. So negative 269, we have to divide by 99. So do we have any common factor? Can 269 be divided by 9? Not sure. So think of numbers, a common number that you can actually use to divide these two numbers. Well, what about if you try a 3 into 69? Not working. So we can leave it there anyway for now. So 269 divided by 99, it's going to actually come out. So we can leave it there. So if you grab your calculator and try to punch it, you're going to see that you're going to get that number recurring. Now at this point, I think you're now ready to handle these other two. So if you look at 2.2413 recurring, so let's make our x be equal to whatever we have. So our x is equal to 2.2413 recurring. Now for the first part, first of all, we need to ensure that only the recurring part is remaining. So that means the decimal point has to move 1, 2, so that the recurring part can remain on the right. So I have to multiply by 100. 100x is equal to, that's going to be 224. So now only the recurring term has remained. Now the next step again would have to, we can't subtract these two. Why? Because the recurring part won't subtract. So this is a case where you now have to take another extra step by now moving the recurring part towards the left. So I have to multiply how many times? By 100, because there are only two recurring numbers. So it's going to be 100 times 10, same times 100 actually. So I'm going to add two more zeros, that will be 10,000. X is equal to 22413, and then the recurring part will still remain. Now at this point you're able to subtract clearly. So 10,000 minus 100, that's 9,900. X is equal to, and then on the other part 22413 minus 224. So that's 22,189. Okay. You can now divide that by 9,900. If you are going to divide, it's going to give you whatever we had on top. Now, our goal is to ensure that we reduce this to a simpler term. So try dividing by a 9. If a 9 is going to work, then it's going to be better. So 9 has refused. So for now, I'll leave it there. If you have a calculator, you can actually try it out in a better form. Try to use something to help you. Yeah, but what's important is that you've gotten the idea of the steps you need to make when it comes to conversions. So try to apply the same concept to the last one. So for the last one, we have 0.0321 recurring. So here we've got three numbers recurring. So if we're going to make our x be equal to that, you still notice that it's not only the recurring part that's appearing on the right hand side. So we still need to multiply. So this has to move once actually by 10x. So it's going to be 0.321. Decimal point has moved only once. Now the recurring part is the only part appearing on the right, So at this point, how many numbers are recurring? There are 3. So you can multiply by 1,000. So it's going to become 10,000. X is equal to 321 will move, and then it will still remain. Now here when you subtract 10,000 minus a 10, that's going to be what? 9990, right? Is equal to 321. So just divide. So whatever you have is your solution there. That's how easy it is to handle this question. I'm going to explain the concept of irrational numbers, proving that a number is irrational using the contradiction method. So basically, we'll prove that root of 3 is irrational. Okay, so before we could even get to that, I would have to explain basically what it means to be irrational. So irrational, maybe I can start with the opposite, which is rational. What do we mean when we say a number is rational? So a rational number is a number that you're able to express in the form of P over Q or A over B. Now, A and B are both integers, okay? And then in addition to that, A and B are also coprime. So by coprime we mean they only have one as a common factor, okay? So that implies having a number like, for example, if you have a 2 can be expressed in the form of 2 over 1. 2 and 1 have only a common factor of a 1. So you can think of all those. So that is coprime. So these two things are very necessary whenever you express a rational number in the form of A over B. A and B should be integers. Of course, integers we understand. These are negative and positive numbers, of course, all numbers, okay? -2, -1, 0, 1, and 2. But of course, the denominator should never be equal to 0 because it would make the fraction to be undefined. Very necessary. So these three things are essential for a rational number. The numbers expressed in the form of A over B should be integers, they should be coprime, and then B, which is the denominator, should not be equal to 0. So I'm just using A and B. You can use P and Q. You can use any letters of your choice. Okay. So proving by contradiction, since we basically know that root of 3 is irrational, I'm just trying to prove. So go by the opposite. So we'll begin with an assumption, okay? That's what it means proving by contradiction. So we'll say we assume, first of all, the opposite. We assume that root of 3 is rational. So if we assume it is rational, then we understand we're able to express it in the form of what? A over B. So therefore say root of 3 is then can be expressed in the form of P over Q. Of course, where P, Q are integers and coprime. Then we understand that Q should not be equal to 0. That's very essential. Explicitly state that. So at that point, we've made clear now, we've made an assumption that is rational, and we say P and Q are integers and then they are coprime. They've got no common factor other than 1. In the next step, we can square both sides of the equation. So if you do square, what are you going to have? So root of 3 is squared, and then the other side we also square. So what is ending up is now we're seeing as having so 3 square root and the square will cancel out. So we have P squared over Q squared. Crossing and multiplying, you have 3q squared is equal to p squared. Okay, I can move a bit up, just erase that. So how best can we express that again mathematically? So we can divide by 3, so that we now have q squared is equal to p squared divided by 3. That is just after dividing by 3 on both sides. Okay, so I'm somehow maintaining this top part because it will be essential in making the conclusion, but don't mix up the steps. I hope you're taking notes of whatever we've said so far. And then at this point, you have that expression. So this shows that it shows that 3 is a factor. Is a factor of what? Is a factor of p. Okay, so we understand all that. So that is simple and straightforward. Of course, we do understand that q is an integer. So if q is an integer, then it implies that for us to have an integer on the right hand side, p should also be an integer, which is divided by 3, so that it gives you an integer, a single number. Okay, so that's the argument. And then from there, you understand that if you're able to divide a number by something, right? For example, in this case, we're saying p is divisible by 3. If I know a number is divisible by 3, for example, 9 is divisible by 3, so I would understand that I'm able to express 9 in the form of what? The product of 3. That is 3, maybe k. So that 3k, where k is equal to 3, represents 9. So if a number is divided by a certain number, you're able to express it as a product of that number. So we can have p being represented by what? 3k. Now notice that it is p squared, so it will be 3k squared over what? Over 3. So the 3 can be multiplied both sides, it will go on the other side. And then after squaring here, you have 3k squared will be now give you 9k squared. So just replace that there. So you have 9k squared. So we can still get to divide, right? What are we going to divide with? So if you divide by 3 both sides, the 3 will go, 3 into 9 will give us what? Will give us 3. I hope you're taking down your steps. So you can still divide by 3 both sides again, until you remain with a 3 on the other side. And this other side will do what? It will go away. Okay. So at this point where we are, knowing that k is also an integer, it tells us q is also divisible by what? By 3. Now at this point where we are, it now leads us to a contradiction, because q and p are having a common factor of what? Of a 3. Okay, so which is now contradicts our earlier assumption where we said p and q were co-prime. So you can just say therefore p and q are not co-prime, or they have a common factor of a 3, which contradicts our earlier assumption that p and q are what? Co-prime. Therefore root of 3 is irrational. Okay, so hopefully you understand basically all these steps on how you basically get to prove that a number is irrational. In this video, we're just going to prove that root of 2 is irrational. So irrational means it is not rational. So what we just need to understand is rational. So when you say a number is rational, what do you mean? So you mean you're capable of expressing it in the form of a over b. Of course, b should not be equal to 0 because we don't want it to be undefined. So it should be in the form of a over b, and then a and b should be in their common ratio, in their lowest ratio, with an highest common factor over 1. An example is a 2. The number 2 can be expressed in the form of 2 over 1, where 2 and 1 are both integers, and then the highest common factor is a 1. So what is a rational number? So we prove this by contradiction because we can't prove directly. So we'd have to make an assumption to say our number root of 2 is rational. So we'll write that explicitly. We'll assume root of 2 is what? Is rational. That's the first thing we're doing. So since you've taken an assumption, we can, a then statement can come now. Then we know we're able to express now root of 2 in the form of a over b. Okay. So at this point, you are at liberty of squaring both sides. Okay? Because we want to do away with the square root. So we square both sides. So you realize that at the next step, this will go, the root will go, so you just have a 2 there. 2 is equal to a squared over b squared. Okay. So I can now move on. So we can cross and multiply. So if we cross and multiply, what are we going to have? So I have 2b squared is equal to a squared. And then we can divide both sides by 2. So b squared is going to be equal to a squared over 2. So you observe one thing. What are we observing? So we're observing that a squared is divisible by 2. So I can give you an example. If you have 4 squared, and then I tell you to say 4 squared is divisible by 2, then it means even the number itself is divisible by 2. 4 itself is divisible by 2. So that expression we have shows that a squared is divisible. Okay? Is divisible by 2. So hence, a is also divisible by what? Is divisible by 2. So I can finish that part. So when a number is divisible by any number, so in this case 2, you're able to express it in form of a product of that number. So for example, if I know 4 is divisible by 2, I'm able to express 4 in terms of a product of a 2. I can say 2k, where k is equal to 2, which is exactly 2 times 2. So the same assumption is going to work at this point. So we know that a squared is divisible by 2. Now we are interested in a being divisible. A is divisible by 2. So we'll go back to our statement where we had b squared. I'll write my b squared. So I have b squared is equal to, now a is divisible by 2, so we can write it in the form of 2k. So 2k. Now it is what? Squared. Yeah. So specifically, a is divisible by 2. So we'll say let a be equal to 2k. Okay. So we can even state that let a be equal to 2k, since we know that a is divisible by 2. Just like I demonstrated about 4. 4 can be expressed in the form of 2 times 2. Okay. So where there is a squared, we are going to put the 2k. And that's exactly what we've done. So over 2. So I can take away the over 2 by crossing and multiplying so that it goes the other side. So that we can have a 2 on the back on the b squared. So you can simplify there. You have 2b squared is equal to 4k squared. Okay. So we have 2b squared is equal to 4k squared. So you can divide both sides by 2. So b squared becomes equal to 2k squared. Now we can divide both sides again by 2. So we realize that we're going to have b squared over 2 being equal to what? Being equal to k squared. So at this point, since b squared is over 2, we can say b squared is divisible by what? So I can just create some space now. So we can say b squared is divisible by what? by 2. Hence our b is also divisible by what? By the same 2. Okay, can finish that up. So since now remember that there's a point where we had said a was divisible by 2. So what does that tell us? So now we can see that both a and b are divisible by what? So we can say 2 divides both a and b. So which now tells us to say that p, our a and our b have a common factor. A common factor of what? Of 2. So now what does this do? So remember from our assumption, it was very necessary for us to assume that 2 was rational. And then we said, if it is rational, we're able to express it in the form of a over b, where a and b have got no common factors other than 1. Okay? Now, in this case, we can see that a and b have got a common factor of 2. So the way you prove by contradiction is by proving that the numbers or your letters of your choice are going to have a common factor. So that common factor contradicts the assumption. So since a and b have got a common factor of 2, it contradicts our assumption. So since it contradicts our assumption, then it's not true. Then we can say that our root of 2 is what? Our root of 2 is not irrational, or we can just say is irrational. That's basically how you go about this. I took a bit of some time to help you understand the few steps that we get to consider whenever you're proving that the root of 2 is irrational. Or we just get to prove that 4 root of 2 is irrational. So we'll start by an assumption. We'll assume the opposite. So assume that 4 root of 2 is rational. So by rational it means you're able to express it in the form of p over q, where p and q are co-prime factors, integers. So 4 root of 2 is equal to p over q. That's where we start from. So of course we understand p and q are both what? Both integers. So we can divide both sides by 4. So our root of 2 is equal to p, and then we have 4q now. So now notice that root of 2 is irrational. You can also notice that since p over 4q, since p and q are integers, that is a rational number. So if the left hand side is irrational and then the right hand side is rational, so this contradicts our initial starting point. Since the left hand side and the right hand side are not equal, it contradicts our assumption. So we can say, therefore, 4 root of 2 is what? Is irrational, since it has contradicted our assumption. Okay, so answer this question. Given that root of 3 is an irrational number, show that 5 plus 2 root of 3 is an irrational number. So prove this basically by contradiction. Okay, so explicitly state what we've been told. So we've been given that root of 3 is irrational. So root of 3 is irrational. That's the first thing we know. So proving by contradiction, we would have to assume the opposite, okay? So assume the opposite. The opposite of an irrational number is a rational number. So a rational number is a number that you're able to express in the form of a over b, where a and b are integers. So we'll assume. So what are we assuming? So we'll assume that our given number, which is 5 plus 2 root of 3, is rational. So by that, we basically mean 5 plus 2 root of 3 should be in the form of p over q or a over b. You can use any letters of your choice. Of course, where both p and q are members of what? Are integers. Okay. So we understand what integers are, but of course, we should also state explicitly that q should not be equal to 0, because if it is, it makes a fraction to be undefined. Okay, that's where we start from. So our goal is to prove that it is not true, because we understand that root of 3 is what? Is irrational. So our goal is to leave it on one side of the equation. So therefore, on our next step, we'll have 2 root of 3. So a 5 can go the other side, which will now become minus 5. Okay. What can we do on the next stage? So on the next stage, we can basically divide by 2 both sides. So we'll have root of 3 is equal to, common denominator on the left and on the right hand side is q. So if you divide q, you have p, and then you have 5q. Now dividing by 2, you have 2q on the bottom. Now, at this point, your right hand side, which is equal to p minus 5q over 2q, is rational. So why is it rational? Because p and q are what? Are integers from what we saw. So integers, what you need to understand is integers, if you divide them, subtract them, add them, the result will still be integers. So on top we expect to have an integer, and then on the bottom also an integer. So if you divide an integers, they will still give us what? The form of p over q, where they are both integers. So it is rational. But notice that the left hand side, which is equal to root of 3, is what? Is irrational. So our conclusion would be now, since the left hand side, we've seen that it is rational, right hand side is rational, our simple conclusion would be there is a contradiction. There is a contradiction. Therefore, 5 plus 2 root of 3 is an irrational number. So it's that simple. So I hope you now understand what it means to that the number is irrational and how to prove it is irrational.
When you have the root of a squared, basically we do understand that this is the same as what? It is the same as what? A. Because we do understand that a root, the square root, is the same as what? Raising it to the power 1 over 2. So you can clearly see that they're going to give you what? They're going to cancel out, and they will give you A. Okay. Now, apart from that, what else can we talk about? So it is also very important to note that when you have A over B under a root, that is basically the same as what? Having the same root on A as well as on what? On B. That is the basic idea. That is a basic concept that we need to basically get to understand in such a case. So what about if you were given, for example, root of 64? So we're saying root of 64 is the same as root of what? Root of 8 multiplied by 8, because we know that 8 by 8 is 64. Then we can now separate the square root. So root of 8, root of 8. Then think of root of 8. What basically can you multiply for it to be equivalent to 8? We do understand that you can multiply what? 2 and 4, which is going to simplify to what? Root of 2, root of 4. So the root of 4 is known. It is what? It is a 2. So we have 2, then root of 2. So root 2 is what we're calling a surd. We can't simplify it. Okay, what else can we say? So now we do know that the root of 8 is basically equivalent to that. So we can now substitute. So root 2, root of 2, where there is root of 8. Then again we do have another one. So I can also put 2 root of 2 there as well. Basically what will be the result there? So 2 multiplied by 2 is a 4. Then root of 2 multiplied by root of 2 is what? So we said root of 2 is the same as root of 2 times 2, which is going to be what? A root of 4. Root of 4 is a 2, so I have a 2. So we've basically seen that our result is what? Is 8. Okay, so that is what we're trying to say. So now I've got a lot of questions, of course, which may even take us an hour. So watch to the end so that you basically get to understand the different questions that you may be given under surds. So the first question is to simplify. So now let's say you've been given 2 root of 28 minus 3 root of 63 minus 8 the root of 7. So how basically do you get to simplify that? So the basic idea is to make sure that you get to have what? The lowest form that you can simplify. So in this case, if you look at 7, the root of 7 is basically, so 7 is an odd number. And there is no other number, there are no two numbers that you can multiply to give you a 7, apart from 1 and 7. So that is a surd. So we want to make sure that we convert all these numbers to the same form. So 2, we do have the root of 28 on the first part. So we also understand that in terms of 7, the root of 28 is what? Is the same as 4 by 7. Okay. So I can substitute that. Where there is root of 28, I can put root of 4 by 7 there. Minus a 3. What is 63? So I'd want to express it as well in terms of products of what? In terms of products of 7. So what do we know? At least we know that 7 by 10 is what? Is a 70. No, now, so what we have is basically less than that. What if we tried 7 times 9? What is it going to be? So that would mean you are removing 1 7 from the 10 7s that you had multiplied in the first place. So you can subtract a 7 there. We have 63. So 7 times 9 is 63. So where there is 63, we can put 7 multiplied by 9. Minus 8 root of what? Root of 7. Okay. We can now distribute. We said when you have the root of a multiplied by b, this is the same as what? The root of a, root of b. So where we have our root of 4 by 7, it's the same as root of 4, root of what? Root of 7. Equal to on the middle part, where our 7 by 9 is the same as what? Root of 7, root of 9. Then the other part we just have what? A 7. So we've clearly seen that there are some parts that we can simplify there. For example, if you look at the root of the root of 4. The root of 4, root of 9, those we can simplify them. So we have 2 multiplied by, root of 4 is what? It's a 2. So remaining with a surd root of 7 minus the other parts. At least we know that we can determine what? The root of 9. It is a 3. So that 3 there multiplied by the 3 that is coming from the root of 9. Multiplied by the root of 7 minus 8 root of what? 7. So what do you think? What can we do from this stage? 2 by 2 is a 4. Root of 7. 3 by 3 is what? It's a 9. Root of 7. Then we have minus 8 root of what? Root of 7. So at that stage, we are now have a same surd there. What can we do to simplify it? So we have like terms. So at least we know the surd is the same. So we're going to have 4 minus 9 minus 8. I've just corrected the coefficients of the surd.
then we have root of 7. 4 minus 9 is minus 5. Minus 5 minus 8. 5 plus 8 is what? It's basically 13. We maintain the sign. So we have negative what? Negative 13 root of 7 as this most simplified form of that question. Okay, let's move. Now let's say in the second part of the question, we've been given 4 third root of 2 minus 2 third root of what? Third root of 16. How is this one different? How do you get to approach it? Okay, so let me add one more thing there. So minus the third root of what? 54. So let's try to express this in the simplest form. So we've seen that the lowest guiding surd there is a 2. So we want to make sure that even the other 2, we try to express them in what? In terms of the 2 that we have. So I'll maintain the first part. The middle part, how do you express 16 in terms of the products of 2? So 16 is the same as what? 8 multiplied by 2. Okay. Then the other part, the third root of 54. What number can you multiply twice to give you 54? So at least we know that 25 plus 25 is what? It's a 50. So if we try 26, 26 plus 26 is going to be what? 6 plus 6 is 2, so I have 52. How about 27 plus 27? 27 plus 27 is basically going to give us a 54 there. Okay. So it's 27 by 2. Okay. We can now move. So we have 4 third root of 2 minus 2. So where we have a product, we can now distribute the third root there. So I'll say the third root of 8, third root of what? Third root of 2. Just like we said, when you add the root of a plus b, we are saying it's the same as root of a, root of what? B being multiplied together. That is a basic concept there. That's what we're saying. We can move minus the third root of 27 multiplied by the third root of what? The third root of 2. So we've seen that basically we've come up with a common form, which is like the third root of a 2 there. So we have 4 third root of 2. Then the question is, what is the third root of 8? What number can you multiply 3 times to give you 8? So we do understand that it's 2 times 2 times 2 times 2, which is giving you 8 there. So you multiply 2. So we have the minus 2 there. Then the third root of 8 is a 2. The third root tells you what number can you multiply 3 times to give you that. Then we can simplify the third root of 2, so we just write it. Minus, what's the third root of 27? What number can you multiply 3 times by itself to give you 27? Is there any number? 3 by 3 by 3. 3 times 3 is 9. By 3 is going to be what? 27. So I have a 3 there. Okay. Then a third root of 2 remains. So at this stage, we can move. So what is 4 multiplied by third root of 2? So we'll maintain it the way it is. Then this part, negative 2 times negative 2. Negative 2 multiplied by the positive 2 is going to be minus 4. Then we do have a third root of 2 there. Then the other part, negative 3, we'll maintain it the way it is. Negative 3, then the third root of what? A 2. So at this point, we now have the common part of the side at the end there. So we can just correct the like terms. 4 minus 4 minus 3. 4 minus 4 is a 0. So this is like can cancel out to give us a 0. So this will stand out to be the solution. You have what? You have a minus 3 third root of what? Third root of 2. So we've simplified that side. Okay, let's have 4 root of 50 minus 9 root of what? 32. How do you simplify that side? You can feel free to pause the video and try it out just before we continue. Okay, I hope you had time to pause the video. We can now continue. Okay, so we would want to simplify this. So now in this case, if you look at this question, it's different from the questions that we've been looking at, because in these other questions, what we had noticed is we had a guiding small third or a lowest third that was guiding us. But then, in this case, we don't have anything to guide us. But at least we know these can be expressed in form of a product of 2. So 50 is the same as what? 25 multiplied by 2. Then minus 9. 32 is the same as 16 multiplied by 2. Which is already coming out because we know we can simplify the root of 25 and the root of 16. So we have 4. We can split that in the brackets. Root of 25, root of 2, minus 9, root of 16, root of 2. So we have a 4. Root of 25 is a 5. Minus 9. Root of 16 is what? It's a 4. Root of 2. 4 by 5 is what? It's a 20. Root of 2. 9 by 4 is what? It's a 36. 9 times 9 is 18. 18 plus 18 is going to be what? It's going to be 36. So, root of 2. So these are like terms. The sides are the same. So 20 minus 36 is a minus 16. So root of 2. That is a more simplified form of that side. Okay, let's try to move. Now, let's say you've been given 5 root of 12 plus 2 root of 3. How do you get to simplify that one? So basically, these are very easy. So root 12 is the same as what? 3 by 4. So 2 root of 3, that is already in the simplest form. So we have 5 root of 3 root of 4 plus 2 root of what? 3. So I've just split the 2 there. Then we can simplify the root of 4. So root of 4 is a 2. 2 times 5 is going to be a 10. Root of 3 plus 2 root of 3. 10 plus 2 is going to be what? 12. So we have 12 root of 3. So basically think of it in this way. It's like where there is a third there, where you have the root of 3, it's like you have what? You have x. So 10x plus 2x is going to be what? It's going to be 12x. So now, where there is x, know that there is what? A third root. So it's 12 root of what? Root of 3. Okay. I have a very interesting question. 2 root of 8 over a 3 minus 3 root of 18 over 5 minus root of 50 over a 2. So feel free to pause the video and try this one out. Okay, so let's try to just get to simplify it. So we have 2. Root of 8 is the same as what? Is the same as 2 times 4. The middle part, 18 is the same as what? Is the same as 9 times 2. Then 50 is the same as what? Is the same as 25 by 2 over a 2. Okay. So we know 2 root of 2 by 4 is the same as root of 2 root of 4. So we're dividing by 3 minus, in the middle part, root of 9 by 2 is the same as root of 9 root of 2 over 5. Then the other part, root of 25 root of what? Root of 2 over 2. Okay. Let's try to move. So now at this stage we do know that basically there are some parts that are simplified, there that are not sides. Root of 4 can be simplified, root of 9 can be simplified, and root of 25 can also be simplified. So basically this is going to reduce to 2. Root of 4 is what? Is a 2. Then I'll maintain the side there. So root of 2 divided by 3. The middle part is going to be minus. The root of 9 is going to be a 3. So we have, I'll maintain the 3 there. Then I'll multiply by the root of 9, which is a 3. Then I'll maintain the sides over a 5. On our right hand side, the root of 25 is what? Is a 5. So minus 5. Then we'll maintain the root of 2 because we can't simplify it further than that. So we can clearly see that what we have now is we basically just have the root of 2 attached to all these. So 2 times 2 is what? It's a 4. So we have 4 root of 2 over 3. The middle part we have a minus. 3 by 3 is going to be a 9 root of 2 over 5. Then we have minus 5 root of 2 over a 2. At this point, I would want us to basically get to look at the fraction part first of all. The root of 2 is basically the one and the same. So let's look at 4 over 3 as the first part of the fraction, minus 9 over 5, minus 5 over 2. So what is the common denominator there? The common denominator of 5 and 2 is 10. 3 and 5 is 15. So now, think of it in this way. If here you're saying you have 15 there as the common denominator. So what is the common denominator of 15 and 2? It's 30. So it's 30 that is going to accommodate 3, 5, and 2. So I can divide. 3 into 30 is going to be a 10. 10 by 4 is going to be a 40. 5 into the 30 is going to be 6. 6 multiplied by 9 is going to be what? So at least we know that 5 by 6, at least we know that 9 by 5 is 45. So if we're trying to say 9 by 6, you add the 9 to the 45. It's going to be what? So 9 by 6 is going to be 45 plus a 9. So that is going to be a 54. So we have minus 54. 2 into 30 is 15. 15 times 5 is what? 2 into 30 is 15. 15 by 5 is going to be what? So 5 by 5 is going to be, it's going to be a 25. 5 by 1 is 5 plus 2, 75. Is that true? Does that make sense? Because if you think about it, 15 can go into 64 times. So 60 plus 15 is going to be 75. So it's okay. So 40 minus 54 is going to give us what? For the first part, 40 minus 54 is going to be a minus 14. So 14 plus 75 is going to be what? So that is going to be 9, 8. So we have minus 89. So we're going to have a minus 89 over what? Over 30. So that is what we've simplified for the fractions. Is there the highest common factor between these guys? So we have a side attached to that, root of 2. So that is the most simplified form of this side. Okay. Then let's move. Let's say you have 3 multiplied by the third root of 54 over 2 plus 5 third root of what? 16 divided by a 3. So feel free to pause the video and try this one out. Okay, so we basically understand that we would want to express a 54 in terms of a product. So 54 is the same as what? 27 by 2. So we have the third root of 27 by 2 over what? Over a2 plus. So the third root of 16 is the same as what? Is the same as 8 multiplied by 2 over what? Over a 3. So at least we do understand this time around that. So what 3 is basically not a power. It's basically part of the root. It's the third root. So 3. So we're going to have the root of what? The third root of 27. Then the third root of what? The third root of 2. So we've talked about that rule of a surd. That allows us to distribute the surd or the square root or any root, third root, fourth root, you just get to distribute it the way it is. So on the other part, equally, the 3 is not a power to 5, it's just a third root. So plus 5. So the third root of what? Third root of 8, as well as the third root of what? The third root of 2, divided by what? Divided by a 3 there. Okay, so we now have 3 over 2. The third root of 27 is going to be what? The third root of 27 is going to be a 3. Because you're trying to think of a number that you can multiply 3 times to give you what? 27. So it's what? It's a 3. The third root of 2, you can't simplify it. So we just write it there. Plus 5. The third root of 8 on the other side is going to be what? It's a 2. You can multiply it 3 times to give you what? That. Okay. So in the other part, we have the third root of 2, which we can simplify, over what? A 3. At this point, you have 3 over 2. Sorry, the numerator there, I can multiply my 3 and what? My 3. That is going to give me a 9. Then the third root of what? 2 over what? 2. Plus. Then we have 5 by 2, giving us a 10. Then the third root of what? 2 over what? Over 3. So we've seen that we've now attained an equivalent surd on both sides. So we basically just have to focus on the addition of the fractions. 9 over 2 plus 10 over 3. The common denominator there is going to be a 6. 2 into a 6 is going to be 3. 3 by 9 is going to be what? It's going to be 27. 3 into the 6 is going to be 2. Multiplied by the 10 is going to be a 20. 20 plus 27 is 47. So we have 47 over 6. So 47 over 6 attached to what? The third root of what? 2. So what becomes your simplified form of the surd? Okay, let's try to move then. Simplify this one. You have a product of 2 root of 3 open brackets 5 root of 2 plus 4 root of 10. So feel free to pause the video and get to work on that question. Okay, so what basically we're supposed to do there? So we need to multiply what we have outside with what is inside there. 2 the square root of 3 multiplied by 5 root of 2. So I'm going to show the multiplication there. So the normal way we get to distribute there, if you have x being multiplied by maybe let's say y plus z, that is equivalent to xy plus what? Xz. So you just get to do the multiplication there. And what if I attached a 4 there and a 2 there and maybe a 3 there? What would happen there? That would mean that I'll multiply 4 times 2 to give me 8, x times y to be xy, 4 times 3 is going to be a 12, then x by z is going to be xz. So the same is going to apply to what we have. So even as I get to multiply, first of all, I'll start with the numbers there. So 2 times 5 is going to be a 10. The square root of 3 multiplied by root of 2 is going to be what? So root of the 2, or I can start with the 3 itself. Root of 3, root of 2, plus. I go to the other part. 2 multiplied by 4 is going to be 8. So again, I'll multiply the root of 3 multiplied by what? The root of 10. Okay. What do we have? So we have 10 root of what? Root of 3 root of 2 plus 8. So root of 10 is the same as what? Root of 5 by what? By a 2. Okay. Can I simplify it further there? So root of 5 by root of 2. So we have 10 root of 2 root of 3 plus 8. Then I have root of 3 root of 2 root of 5. So we can't simplify this one beyond that. We can't go beyond what has been given there. So if we can't do away with the root of 5, there is no way we can add these because they are unlike terms. So we can just simplify it the way it is. Root 2 times 3 is going to be what? It's going to be root of 6 plus 3 by 2 is going to be 6 by 5, just root of 30. Yeah, so that is okay, ending at that point. Alright. Let's look at another question where we have 2 root of x minus 3 root of y squared. So that means that you have 2 root of x minus 3 root of y multiplied by 2 root of x minus 3 root of y. So let's try to do a multiplication there. This by that is going to be a 4. 2 times 2 is a 4. Root of x by root of x. So x times x is x squared. I just want to show you there. So if you have the root of 2 by root of 2, this is the same as 2. Okay. How? So there are two ways in which I can prove that. I can show you that the root of 2 is the same as 2 to the power 1 over 2 multiplied by 2 to the power 1 over 2. So according to indices, we are told if the base is the same, maintain the base, then add the powers. So half plus half is going to be a 1. So that is 1. 2 to the power 1, which is just a 2. The other way in which you can think about this, how do you get to prove it? So it can be root of 2 by root of 2 is the same as root of 2 times 2, which is the root of 4. What is the square root of 4? It's a 2. Okay, so whichever is works for you. So the root of x by the root of x is just going to be x. Then 2, this same part, multiplied by the other parts. 2 times 2 is going to be a 6. So what is attached to a negative? So it's going to be minus 6. Root of x multiplied by the root of y. So we have root of x, root of y. Then I can go for the other parts now. The negative 3. Negative 3 by 2 there is going to be minus 6. Then we'll maintain what we have, root of x, then root of what? Y. Then the last part, this one, multiplied by that. Negative 3 by negative 3 is going to be positive 9. Root of y by root of y is basically just going to be a y. Okay. So root of y by root of y is just square root of y squared, which is just y. At this point, we have 4x, the middle part, they're like terms. Okay. So 6 plus 6 is going to be a minus 12. The root of x multiplied by the root of y is the same as what? It's the same as root of xy. Then plus 9y. So we've simplified this side. Okay. Okay, I still have some couple of questions that I want us to look at. Okay, so we've been given a product of 3 root of x plus 5 root of y multiplied by 3 root of x minus 5 root of what? Root of y. So how do we get to look at this? So basically what has been given here is like, it's just multiplying the side by its conjugate. So what is a conjugate? So a conjugate is when you have a plus the root of b, its conjugate is what? It's a minus root of b. So basically there is a special identity that we're going to see. Let's try to do the multiplication. So 3 by 3 there is going to be a 9. Root of x by root of x. So we have the square root of x multiplied by x is the same as root of x squared. So the root of x squared is what? X. So we have x. Moving there, looking at 3 root of x multiplied by the other part, 3 times 5 is going to be minus 15. Then root of x by root of y is going to be the root of what? Xy. Then we'll move to the other part. 5 times this is going to be what? 15. Then root of what? Xy. 5 by the 5 at the ends is going to be a minus 25. Then root of y by the root of y is just going to be what? A y. So basically we are going to notice that whenever you multiply a surd by its conjugate, the middle part basically turns out to be a 0. So you just have 9x minus 25y. So in every time you're just given a product of a surd by its conjugate, just multiply the like parts. So it only requires you to multiply this part by that part, and also this part with that part. So which would be 3 by 3, 9. Root of x by root of x, which is x. 5 times 5 is a minus 25. Root of y by root of y is just a y, which is simplifies to that. Okay, another question. Root of x plus root of y squared. What is it? What is it equivalent to? So in terms of expansion, it's like we have the root of x plus the root of y being multiplied by the root of x plus the root of y. What do we get to do there? Okay, so root of x multiplied by the root of x is going to be what? So that is going to be equivalent to x. Root of x by the root of y is going to be what? That is going to be the root of xy. Then this by that. The root of y by the root of x is still going to be the root of xy. Then the root of y by the root of y is going to be a y. I'm sure I've proven that several times. I've shown you. Root of x by root of x is the same as x. Okay. X squared root of x squared is just x. We've shown that already. So that's where the x and the y are coming from. So we now have x plus y. The root of xy is coming twice. So consider 1 to be there. So it's like you're going to have a 2 root of what? Root of xy. So we've simplified. Okay. So on the part of simplifying, we have one more that we can look at. Let's say they give you the root of 32 minus the root of 0.5 minus the root of what? 8. So you can try that one out before you get to see the solution. I just hope you had enough time to pause the video and you've tried it out. So basically, you would want to make sure that you don't have decimals. So we have root of 82 minus the root of 0.5 is the same as 1 over 2. Then root of 8. So for your own information, the root of a over b is the same as what? Root of a over the root of b. So just as you distribute with multiplication, when you say the root of ab is equivalent to the root of a by the root of b, even for division, the same is applicable. Okay. So 32 in terms of 2 is what? Is the same as root of 16 multiplied by what? Multiplied by 2 minus the root of 1 over 2 is the same as root of what? Root of 1 over the root of 2. Then the root of 8 is the same as what? So the root of 8 is the same as 4 by 2. 4 times 2 is 8. So we can distribute the square root there. So we have the root of 16 multiplied by the root of 2. The root of 1 is just the 1. So it's 1 over the root of 2. Minus root of 4. Then root of what? Root of 2. At this point, we can now distribute what? The root. The root of 16 is going to be a 4.
So we have 4 root of 2 minus 1 over root of 2. The root of 4 is going to be a 2. Then root of 2. So we have the common denominator there, which is what? A root of 2. We can multiply. We can divide. Like there you have a 1. 1 into the root of 2 is going to be root of 2. So now we multiply the denominator there. The root of 2 multiplied by what is the top pair. So we're going to have 4. Root of 2 by root of 2 is going to be what? A 2 minus. Divide the root of 2 by root of 2 is a 1. So we have a 1 in between. Divide the 1 into the root of 2 is going to be 2. So we are going to have a product of 1 into the root of 2 is root of 2. Root of 2 multiplied by negative 2 root of 2. So it's like we have a 1 there. 1 times the minus 2 is going to be a minus 2. Root of 2 by root of 2 is going to be a 2. So we have 4 by 2, which is going to be 8 minus 1 minus 4 over the root of 2. 8 minus 4. Okay, 1 plus 4 is 5. So we have 8 minus 5 over the root of 2. 8 minus 5 is going to be what? 8 minus 5 is going to be what? So we have 3 over root of what? 2. Okay. So we are done with the issue of simplifying. Now let's try to look at a different form of the question where they are requiring you to express it in a different form, and also the idea of rationalizing the denominators. Okay. So you've been given root of 3 plus 1 over root of 3 minus a 1 plus root of 3 minus 1. So now the question says express this in the form of what? A plus b root of what? 3, where a and b are rational numbers. So it's like they only want you to remain with one part of a surd, which is just going to be like the root of 3. They don't want a and b to be surds. They want them to be rational. So what do you get to do there? How do you get to approach such a question? Okay, so before we get to do anything, we need to first of all get to add what we've been given, so that we have a common denominator even as we get to rationalize it. So what common denominator do we have in this case? Okay, so we have 1, we have a 1 there. So what we have there becomes our common denominator. So we have root of 3 minus a 1. So divide that into this part, is going to be a 1. Multiply by the numerator is going to be maintained. Then for the middle part, 1 into the root of 3 minus 1 is going to be the root of 3 minus 1. So multiply by the numerator. So we're going to have a product of root of 3 by root of 3 minus 1. Minus, so we have a 1 there. 1 into that is still going to be that. So for the numerator we have a 1. Multiply by the root of 3 minus what? Minus 1. What do we get to have at that point? So maintain root of 3 plus 1. Then for the middle part, root of 3 by root of 3 in the brackets is going to be what? It's going to be a 3. Root of 3 by a negative 1 is going to be minus root of 3. The other part, negative 1 by the root of 3 is going to be minus root of 3. Negative 1 by negative 1 is going to be a positive 1. This is all supposed to be divided by what? Divided by the same expression that we have on the denominator there, which is the root of 3 minus what? 1. So we have root of 3 and a minus root of 3. These are like terms, so at least we know they can cancel out. So we have 1 plus 3, which is basically a 4, minus, so we have this plus that is a 4 plus a 1. It's going to be what? It's going to be a 5. So 5, we are also remaining with that, minus root of what? 3 over root of 3 minus 1. So I'll repeat that. So I was saying this part can cancel out with that part. They are subtracting. Then 1 plus 3 is a 4, plus a 1, 5, minus the root of 3 that had remained. Remember, we had 2 of these, or in other terms, we can write it to be, we have root of 3 plus 4 there, then minus 3 minus this part, they are like terms, so it's the same as minus 2 root of 3 plus 1. So it's basically going to still reduce to what we have. 4 plus 1 is going to be a 5. 4 plus 1 is a 5. This and that. 1 minus 2 is a minus. So that's where that is coming from. So now at this point, it is easier to take that to the form of a plus the root of what? 3. It's easier because we can clearly see what we can do. So we can multiply by what we call the conjugate. So now the question is, what is a conjugate? So the conjugate is supposed to help us do away with what? Do away with the surd on the denominator part. So how do we get to look at such a question? Okay. So I'll do this. So we have 5 minus root of 3. Then we have negative 1 plus root of 3. Then I can change the sign in between the denominator. So it's going to be negative 1 minus root of 3. Even the numerator, we do what? We do the same. Okay, so we said, of course we did say, okay, so 5 by negative 1 is going to be what? 5 by negative 1 is going to be a minus 5. 5 by a negative 3 is going to be what? It's going to be minus 5 root of 3. Then the other part, negative root of 3 multiplied by negative 1. So negative by negative is going to be a positive. So we have positive root of 3. Then again, the negative root of 3 by the negative root of 3 is going to be what? So that is going to be a positive 3. I'm sure you now know the laws, so you understand where that is coming from. Okay, so now for the denominator part, we do have a surd multiplying by its conjugate. So we say just multiply the like parts. Negative 1 by negative 1 is going to be a positive 1. Root of 3 by root of negative 3 is going to be a minus 3. That's what we have. So like terms, 3 minus 5. 3 minus 5 is what? Negative what? Negative 2. Negative 5 root of 3 plus root of 3. So it's like negative 5 plus 1, which is a minus 4 root of 3. Over what? 1 minus 3 is a negative 2. We can divide by the negative 2 throughout. So we have 2. Oh, negative 2 divided by negative 2 is a 1. Sorry. Negative 4 by negative 2 is going to be a positive 2. Then root of what? 3. So we've already expressed our question, or our form that we were given in the form of a plus what? B root of what? 3. So that is how you approach such questions. Okay. Moving on to the other part of the question, we need to now understand how we get to rationalize what? How we get to rationalize the denominators. So basically, we've actually applied that in the previous question. Okay, so let's try to rationalize the denominator in the following questions. So now, let's say you've been given 2 root of 3 minus root of 2 divided by what? 4 root of 3. How do you get to rationalize the denominator, and what does it mean to rationalize the denominator? So by rationalizing the denominator, it means that they don't want to see a surd on the denominator part. They don't want to see a surd. Okay, so we can, in this case, what we're going to do is we can just multiply by what? We can just multiply by what is on the denominator itself. So 4 by root of 3. So whatever you multiply the denominator, it should also be multiplied by what? The numerator. Okay, so let's try to do our multiplication there. So 2 root of 3 multiplied by 4 root of 3. 2 times 4 is going to be what? 8. Root of 3 by root of 3 is going to be a 3. Then we have this other part, negative root of 2 by 4 root of 3. So we have a minus 4. Root of 2 by root of 3 is going to be root of 6. Over 4 times 4 on the denominator part is going to be 16. Root of 3 by root of 3 is going to be a 3. 8 by 3 on the numerator. 8 by 3 is going to give us what? 24. Minus 4 root of what? Root of 6. 16 by 3 is going to be what? 16 by 2 is 32. Plus 16 is going to be what? 48. Okay, we want to reduce that. So we now have 24 over 48 minus 4 over what? 48 root of what? Root of 6. So 24 into 48 is what? It's twice. So it's 1 over 2. So we have 1 over 2. 4 into 48 is going to be a 1 there, a 2 there. So it's like 12 times. So we have minus 1 over 12. Root of what? Root of 6. So in other terms, what we have is 1 over 2 minus root of 6 over 12. So we've rationalized the denominator. Even ending at this point, there's no harm to that, unless they specifically specify that they want it in the form of a plus root b, then root of maybe c. Unless they want it in that form, that's when you can go as further as we've done in this class. So basically, rationalizing the denominator doesn't want us to have a denominator to be part of what? To contain a surd. Okay. We do have another question. X divided by x plus what? The root of y. So we don't want to see the surd. We don't want to see that root on the y. How do you get to do away with it? Okay, so multiply by x minus root of y. We just change the sign. So we are multiplying by what you call the conjugate. Just change the sign of the denominator. Sign in between the denominator there. So x times x on the numerator is going to be x squared. X times the root of y is going to be what? We're going to have minus x root of y. Denominator part, x times x is x squared. Root of y by the root of y is going to be what? It's going to be minus y. Okay. So basically, we've simplified this. Okay. So this is fine. So we've rationalized what? We've rationalized the denominator because we can't see anything there. We can't see any surd on the denominator part. And that is basically the main idea of you rationalizing what? The denominator. Okay, so if you want, you can simplify it, but we've already rationalized what? The denominator. Now let's look at some more advanced questions. Let's say you've been given the root of 2, the root of 7, plus the root of 3, divided by 3 root of 7, minus the root of 3. How basically do you get to simplify that question? How do you get to rationalize the denominator? So we'll change the sign in between. Let's change the sign in between the denominator. So we'll say 3 root of 7 plus the root of what? 3. So whatever you do to the denominator should be done to the numerator as well. So I'll start. Root of 2 root of 7 by that. 2 times 3 is going to be what? It's going to be a 6. Root of 7 by root of 7. So we've talked about this. Okay. So we have a 7. Then again, the 2 multiplied by the 1 that is there. It's a 2. Root of 7 by 3 is going to be root of 3 times 7. Then again we move to this part. So we are doing the normal multiplication from algebra. So if you have a plus b being multiplied by c plus d, that is basically what you're doing. So it requires you first of all to multiply the first part with the other two parts, then again you multiply the other one with the two parts as well. So we've already done our multiplication by the 2 root of 7, which is this part. We've now gone to the root of 3. So root of 3 by that is going to be plus 3, then root of 3 by what? 7. Then root of 3 by root of 3 is going to be what? A 3 over. So the good part about the conjugate on the side itself, it only requires you to multiply the matching parts, because the middle part of the summation basically gets to have opposite signs, and they get to do what? They get to subtract. Okay. So 3 by 3 is a 9. Root of 7 by root of 7 is going to be a 7. Root of 3 by root of 3 is going to be a 3. 6 by 7 is what? At least we know that 6 by 6 is 36. 6 multiplied by 6 is 36. So how do you get to multiply 6 by 7? So you add a 6 to 36. So 36 plus 6 is going to be what? Get a 4 from the 6, you remain with a 2. To make it 40 plus 2, 42. So 6 by 7 is 42. 3 by 7 in the brackets is what? Root of what? Root of 21. Even there it's going to be 21 plus what? 3. 9 multiplied by 7 is what? We know 9 by 5 is 45. So plus 18. 8 plus 5 is what? So get it 2 from the 5, make it a 10. Then you remain with what? 13. 4 plus 1, that is going to be a 63. So we have 63 minus 3. So basically at this stage we've even rationalized the denominator because you can't see a surd. So it's just a matter of now you getting to simplify what you have. So 42 plus 3 is what? 45. 2 plus 3 is what? It's a 5. So we maintain the 21 there. 63 minus 3 is what? A 60. Okay. So we've rationalized our denominator. So we can even simplify it by dividing by what? So if you look at the numerator there, you can factorize the 5, right? So 5 into 45 is 9 times. Plus root of 21 over 60. So I'm sure we can divide the 5 into the 60. How many times? That is like 12 times. So we have 9 plus root of 21 over what? Over 12. So you can end there. So you can go beyond if the question is requesting you to express your solution in the form of a plus b root of what? 21. Would have divided by the 12. So if you want, you can do that. So you have 9 over 12 plus root of 21 over what? 12. Divide the 9. 9 by 3 is what? It's going to be a 3 over 4 plus root of 21 over what? 12. Which is very much okay. We now have x minus root of x squared minus a 9 divided by x plus root of x squared minus 9. So feel free to pause the video and try out this interesting question. Rationalize the denominator. We don't want to see a root to be part of the denominator. How do you get to approach this question? I'm hoping you've paused the video and you've tried it out. Okay, let's try. Let's get to do this. What are we supposed to do here? What do we get to do? So we're basically going to have, for the denominator we change the sign in between, so we're going to have x minus the root of x squared minus 9, then the numerator as well. Okay, so I'll start with the numerator. X times x is x squared. Then what is in the root there multiplied by what is in the root there? They are basically identical. So just like we said, if the root of x by the root of x is equivalent to x. So even there what we have is basically going to be the same. It's basically going to be the same there. Whatever is in the brackets is going to stand. So now remember what we're doing is, we've said x times x is that, but before it gets to even multiplier, so x by that is x squared. So now how about the x again multiplied by what is there? It's going to be minus x root of x squared minus what? Minus 9. Then this part, negative of it by the x again, is going to be minus x again root of x squared minus what? 9. Now this multiplied by itself is going to be a positive. So like I was showing, the root of x by root of x is x. So that multiplied by itself, the root is going to go away. So we're just going to remain with what? X squared minus 9. This is all going to be divided by what? The product of the surds and the conjugate. So for that, what did we say? We said just multiply the like parts. X times x is x squared. The root of that by the root of that is going to be minus. So we have x squared minus 9. Okay. So we have x squared plus x squared. Then minus x is going to be a minus what? A minus 2x. Then we'll maintain the what? The radical there. X squared minus 9. Then minus a 9 over what? So for our denominator we have x squared. So distribute the negative. So we have minus x squared plus a 9. X squared plus x squared is going to be 2x squared minus 2x root of x squared minus 9 minus 9 over a positive 9. Okay. So we've actually rationalized what? We've rationalized our denominator because we can't see any radical being part of what? The denominator there. So that's how you get to approach such a question. Okay. Now let's say you have been given 1 over root of 2 plus a 1 root of 3 minus 1. Okay. So you've been asked to rationalize the denominator as well. So before we get to do that, we'd want to make sure that we get to simplify what we have. Root of 2 by root of 3 is going to be root of 6. It's 2 by 3. Root of 2 by a 1 is going to be minus root of 2. Root of 2 by root of 3, sorry, we've done that already. 1 by root of 3 is going to be root of 3. 1 by negative 1 is going to be minus 1. What do we have? So we now have a 1 over root of 6. Then now we have a minus root of 2 plus a root of 3 minus 1. So I'll do that again. We have 1 divided by root of 2 plus 1 divided by or multiplied by root of 3 minus a 1. So our goal is to rationalize the denominator to make sure that there is no side that is appearing on the denominator. So we have to first of all to multiply or simplify it. So now we are saying we have the root of 2. So I have root of 2 plus 1 multiplied by root of 3 minus a 1. Okay. Root of 2 by root of 3, root of 2, root of 3, Root of 2 by a minus 1 is going to be a minus root of 2. 3 by a 1 is going to be plus root of what? 3. 1 times 1 is going to be a minus 1. Okay. So that is what we have at that stage. So basically, how do we get to simplify it? How do we get to simplify it at that stage? Is there anything that we can do to make it better? So we can see at least that we have part of it that looks common. So I can get my first part and basically gets to factorize the common part. So if I can look at this part, I can clearly see that I can factorize out my what? My root of 2. So I'll put it outside. Then what is going to remain in the brackets is what? For the first part, root of 3 is going to remain. Then minus what? Minus a 1. Then the other part we have plus. We have plus root of 3 minus a 1. So is there anything that we can do to simplify it further than that? So that at least we're clearly able to see what we can do in terms of our multiplication, even as we get to do away with the surds. So we now have 1 over root of 3 minus 1 attached to root of 2 plus root of 3 minus 1 multiplied by what? We now need to understand. We need now to realize, think of something that we can multiply this so that we get to do away with what? We get to do away with what we have. Okay. So now consider this to be in brackets for one reason. So then I'll change the sign in between. So I can say root of 3 minus 1 attached to root of 2. The sign in between can become a negative. Then we'll have root of 3 minus a 1. We do the same to the numerator. So I don't have enough space here. So we have root of 3 minus 1 attached to root of 2 minus root of 3 minus 1. So on the numerator that is going to stand out, we have root of 3 minus 1, root of 2 minus root of 3 minus a 1. Denominator part. This times that is going to have root of 3 minus 1 squared. Root of 2 times root of 2 is going to be what? It's going to be a 2. So we have a 2 attached to that. Then this times that is going to be a minus root of 3 minus 1 also squared. Okay. We need to simplify this now. So we've seen that what we have in the brackets is common. So we have root of 3 minus 1 times root of 3 minus 1. So what is that if you get to multiply? Root of 3 by root of 3 is what? It's a 9. Right? It's a 9. Sorry. Root of 3 by root of 3 is a 3. Root of 3 by a minus 1 is going to be a minus what? It's going to be a minus root of what? 3. Then negative 1 by that again, it's going to be minus root of 3. 1 times 1 is going to be a 1. So we have 3 minus 2 root of 3 plus a 1. Then this is going to simplify to 4 minus 2 root of what? 3. Okay, you can move. So I can move this down. Okay. So now, how do we get to simplify this. How do you get to make it look better? Okay. So now we have root of 3 minus 1, root of 2 minus root of 3 minus 1 over. So now where we have the squared part, I can put that. So I have 2 multiplied by 4 minus 2 root of 3 minus, so I can distribute the negative to that. So we're going to have a minus 4 plus 2 root of what? 3. So that is going to become 8. That is going to become what? A 4. Then I can remove it 2. Is there anything that we can do there? At least we have like terms. 8 minus 4 is going to be a 4. So we have a 4. Minus 4 plus a 2 is going to be a minus 2 root of 3. That's what we have down. I can indicate it. So we have a 4 minus 2 root of what? Root of 3. At this stage, at least we are clearly able to see that we can simplify that. So we can multiply by 4, changing the sign. So 4 times that, we're going to have 4 root of 2 root of 3 minus 1 minus 4 times that, then we've multiplied by the 4. We can now multiply by the 2 root of 3, multiply by that, multiply by the first part. We're going to have 2 root of 6 open brackets root of 3 minus 1. Then the last part, root of 3 minus 1 multiplied by the 2 there. So outside the brackets we're going to have a minus 2 root of 3 open brackets root of 3 minus 1. All this to be divided by what? Our denominator is going to have a 4 by 4 to be a 16. 4 times that is going to be 8 root of 3. So basically that's a conjugate. We can just remove the middle part. This times what is going to be a minus 4 root of what? Sorry, 4 by 3. So 4 by 3 is 12. 16 by 12 is going to be a 4. So at that point you can basically even get to just simplify the numerator part and get to divide by the 4. So we've already rationalized the denominator because we can't see any radical attached to the denominator. Okay, so basically these are the things that you basically have to understand under Surds. Surds are very, very simple. I just hope that you've made it to the end of the video and you've understood and you'll not have any challenges with what? The Surds. Thank you very much for watching.
Okay, so we're now on this question. This question is just going to simplify whatever we have. So the very first part says root of 86 but root of 64. So these ones you can actually simplify. The root of 86 is a 6, root of 64 is 8, 8 plus 6 is 14. So we're done with the first one. Second one, 7 root of 3 plus root of 12. Okay, so maintain this. Now when you look at 12, 12 is a product of 4 and 3, right? So you can distribute the square root. You're going to have 7 root of 3. So you're going to have root of 4 multiplied by root of 3. 7 root of 3. So root of 4 is going to be a 2. So you now have common, these now become like terms. 2 plus 7 is 9. So 9 root of 3. That's how you handle Surds. So there are two steps, there are two things we've learned here. when you've got a number under a square root, you can actually express it in terms of its product, which we have, and then you can actually distribute the square root, which we have, and then simplify what you can, and then we can simplify root of 3. Okay, so these are what we call surds now. So we're now on the third one. Feel free to pause the video and try it out. Root of 20 plus 2 root of 45 minus root of 80. Root of 20 is already a product of what? I think that is a 4 and a 5. And then 45 is a product of 9 and 5. So 9 times 5. And then 80 can be a product of what in terms of 5. So if you try to divide 80 by 5, that's 16. So 16 times 5. So this is easy to actually figure out. So you can distribute the square root now. So you're going to have root of 4, root of 5, plus 2, root of 9, root of 5, minus root of 16, root of 5. So root of 4 is going to be a 2, root 5, and then root of 9 is going to be a 3, and then root of 16 is going to be a 4. So this is why it's important to write things clearly, because I was almost thinking I wrote a 3 there, so that's a 5. So 2 root of 5 plus 6 root of 5 minus 4 root of 5. 2 plus 6 is 8 minus 4, that's a 4 root 5. We've simplified from that complex expression to something as simple as that. Okay, so these are the surds we're talking about now. Now we are on number 4. 3 root of 27 minus 48 plus 2 root of 75. Let's think of the products we can have. 27 can be divided by what? 9 times 9 times 3 is what? Because it's going to be 18 plus 9. That's 27, right? 9 times 3. So 3, I can just go direct, so that's going to be root of 9 times root of 3. I've already shown you that you can actually express it in terms of a product and then separate them. And then minus. Now think of a 48. I think I can think of 48, I can think of 8 as a factor. How many times can you divide 48 by 8? That's 6. So 8 times 6. Now that one can't give us any form of factors, but we can go on and try to split it anyway. So 8 times 6, 8 can be expressed as 4 times 2. The 6 can be expressed as 3 times 2. So a 2 times 2 part can give us 4, so we can express that 4 times 4 times 3. Okay, so 4 times 4 can be expressed as 16. So I think 16 is a better option. So 16 times 3 is 48 plus 2. And then for 75, I can think of, I think 15 should be a factor, because I know 60 can be divided by 15 how many times? That's 4 times. Now if you add a 15, it's going to be 75, so it's like 5 times. So that's going to be 15 times 5. Now 15 times 5, 15, we don't have any factor here, so 15 times 5, 15 is the same as 5 times 3 times 5. 5 times 5 is 25, so I think this is better. So 25 times 3. Okay. So 3, root of 9 is going to be a 3. Root of 16 is going to be a 4. and then root of 25 is going to be a 5, root of 3 will just remain root of 3. So we have 9 root of 3 minus 4 root of 3 plus 10 root of 3. 9 minus 4 is going to be a 5 plus a 10. That's going to be 9 minus 4, 5, 10, 15 root of 3. Okay, we just have two more now. Root of 72 minus 8 root of 3 plus 3 root of 48. Can you think of any factor of 72? I think 2 itself is a very good factor. Divides 2, you know, in 70 divided by 2, I think that's going to give us 55. Now plus an extra 2, so that's 56. 56 times 2, 56 times 2 is 72. Okay, and then minus 8 root of 3, then plus 3 root of 48. 48 we already saw at 16 times 3. So root of 86 times 2. Root of 86 is 6, so 6 root of 2 minus 8 root of 3. 16 root of 16 is a 4 root of 3. So we're going to have 6 root of 2 minus 8 root of 3 plus 12 root of 3. 6 root of 2. 8, negative 8 plus 12, that is like 12 minus 8, that's a 4. Okay, you can't simplify it beyond that point. Root of 2 and root of 3 are not like terms. And then finally the last one. Feel free to pause the video and try it out. So 3 root of 28 divided by 2 root of 175. Okay. 28 can be divided by 14, right? I think that's going to be like 7 times 4. So 28 is the same as 7 times 4 times. And then 175. Can you think of any factor of 175? If you can think of 25, try 25. 25 into 100 is 4 times. 25 into 75, that should be 3 times. So that means if you try 25 times 7, it's going to give you that. So you have 3. So I'm going to have on top root of 7. In fact, I can just go by 7 times 4. I can just express it in terms of 4 times 7. So the root of 4 is a 2, and then root of 7. On the bottom, you have 2. Root of 25 is a 5, and then root of 7. Root of 7 can actually just divide. 3 times 2 is 6. 2 times 5 is 10. I think in other terms, you can just divide this as well. I can see 2 is common there. So 3 over 5. So that's how you handle Surds, and we are done. Alright, so we'll continue now on D. So here we're going to rationalize the denominator. Okay, so starting with the very first one, for 1 we have 3 over root 5. So the denominator, of course, you understand this, the part of the fraction which is like down, right? And then by rationalizing, you mean you don't want to have a surd or a square root there, okay? Because the definition of a rational number is it's a number you're able to express in the form of a over b. So these surds, the root of 5, they are not rationals. So you want to rationalize by dealing away with that. Okay. So what we usually do is we multiply by what we call the conjugate. Now in a case where you have such an expression, just multiply by the root of the denominator itself. So root of 5, that's going to give us on top it will be 3 root 5. On the bottom, root of 5 by root of 5 is going to give us a 5. The idea is if you have 5 raised to the power half, multiply by 5 raised to the power half, maintain the base, add the powers, it will be a 1. So in other terms, we understand that the square root is the same as the power half. So that's why it is just 5 there. So if you look at this expression, what we have in this case is our denominator is now rationalized because you're able to express 5 in the form of a over b. Okay, so we can move to part 2. So for part 2 we have 2 over 3 minus root 3. So this is a case where we multiply by what you call the conjugate. So the conjugate means you change the sign in between. So we're going to have 3 plus root of 3, of course, of the denominator. Multiply that with both the numerator and the denominator. So for the top part, 2 times 3 will be 6. 2 times root of 3 will just be 2 root of 3. Now on the denominator, I'll do everything and then I'll show you what basically happens. 3 multiplied by that part, to be 3 times 3 will be 9 plus 3 root 3. And then if we get this part now, negative root of 3 multiply that term. So we're going to get a 3 root 3 and then a minus 3, because root of 3 by root of 3 it's going to just be a 3. I already explained what happened there. So therefore you can clearly see that this in between is going to subtract. So every time you're multiplying a surd, we'll see this even under complex numbers, by its conjugate, just multiply the like parts, which is 3 times 3 and 9, and that times that negative 3, because this will always be cancelling out. Okay, I just need to show you for the very first one, and then the others I won't be showing that because it's not necessary. So we're going to remain with 9 minus 3, which is going to give us a 6, and then you can actually divide by 6 if you want. First one is going to be 1, the other one is going to be root of 3 over 3 as your solution. Okay, so this is basically how you handle part 2. Now, applying what we've learned, feel free to pause the video and try out the remaining questions. So part 3, what we have is we have 3 root of 2 divided by 2 plus root of 5. Okay, so here what we want to do, we still want to rationalize the denominator. So multiply by the conjugate of this, the denominator, which is going to be changing the sign in between, giving us that. So we do the same to the numerator as well. So for the top part, this times that would give us what? 3 times 2 is going to be a 6, so 6 root 2. And then again, the same expression against that. So we're going to have, there's like a 1 there that you can't see. So 1 times 3 is just going to be a minus 3 because there's a negative there. So a minus 3 and then root of 2 by root of 5 divided by. So this is where we're now multiplying the surd with its conjugate. So just multiply the like parts. 2 times 2, that would give us a 4. And then root of 5 by minus root of 5 is just going to be minus 5. You end up with 6 root of 2 and then minus 3 root of 10, that is 2 times 5, over, so we're going to have a negative 1 on the bottom. So negative 1, we can divide the entire expression by negative 1. So you can just end up with a positive 3 root of 10 minus 6 root of 2. Okay, so we've rationalized the denominator. So the same concepts will continue to apply as we proceed. On number 4, we have root of 3 minus root of 7 over root of 3 plus root of 7. This is going to be equal to, so we have to multiply by the conjugate of the denominator because we want to rationalize the denominator. So we're going to have root of 3, can change the sign in between. We do the same to the numerator. So root of 3 times root of 3, so let's multiply this part to that part. So root of 3 by root of 3 is going to be a 3. Root of 3 by 7 is going to be a negative because this part is having a negative, so negative root of 3, root of 7, and then this part times this, again to be root of 3, root of 7, and then this part times that will be positive 7 over. On the bottom, this is now the conjugates, so let's just basically multiply the like parts. Root of 3 by root of 3 is going to be a 3, root of 7 by root of 7 is going to be a minus 7. So you're going to have 3 minus 2 because these are like terms, so they're coming twice. Root of 3, root of 7, we can actually combine that if you want, so to make it root of 21 of or 3 plus 7 can actually, so we've got a plus 7 there. For the denominator, 3 minus 7 is going to be a negative 4. 7 plus 3 gives us a 10, so we have 10 minus 2 root of 21 over negative 4, which we can divide for both parts, and then you end up with root of 21, so that is over 2, and then minus, so the 2 there it's 1, 2 there it's like 2, and then 2 there it's 5, 2 there it's 2, so you're going to have negative 5 over 2, which you can actually combine if you want. So we can see the denominator is just a 2, so we've rationalized the denominator. And then we are now on number 5. So x minus y divided by root of x minus root of y. So we're rationalizing the denominator, multiply by the conjugate by changing the sign in between, and then you end up with root of x plus root of y. So what do we have now? So x times that would be x root of x, again that would be x root of y, and then we'll now take this negative y, so that would be negative y root of x, again negative y root of y, and then the denominator, just multiply the like parts. Root of x by x is x, that would be minus y. So at least we can see the denominator is now rationalized, right? So any like terms we have, I can't see any like terms for the top part, because even if we have root of x, there's still x minus y, so we can actually just factorize. So let's get this part and that part, so x minus y, and then we can remain with root of x outside, and then the other part we have that and that, so again we'll factorize the, so let's just call it plus, and then we have x minus y root of y over, we have x minus y. Okay, can you simplify it beyond this point? So for the top part, if you want, you can factorize the x minus y, and then we can remain with root of x plus root of y. So if I to multiply, we're going to get back whatever we have. And in the denominator we have x minus y as well. So I think this can divide, and then at the end of it all, we're just going to be with root of x plus root of y. I don't know how true that is, but that's where we've ended up finding ourselves. Yeah. For the last one, we have h over root of x plus h minus root of x. This is h, so equally we change the sign in between, so it becomes positive root of x. We'll do the same for the top part. So after we multiply, we're going to have for the top part h, and then we have root of x plus h plus root of x. For the bottom, this part times that part will be x plus h, and this part times that part will be minus x. So you end up with this one that will subtract, so you just remain with h can divide. So ultimately your answer remains root of x plus h plus root of x. Okay. So I think even the previous one we can do better than what we did. So we had so many unnecessary steps. So x minus y over root of x minus root of y multiplied by the conjugate, which is root of x plus root of y. So root of x plus root of y. So let's not try to change anything about the top part. Let's leave it x minus y multiplied by root of x plus root of y, and then x times x. So root of x by root of x will be x, and then that will be minus y. So this can just divide again, and then you remain with root of, I think we did repetition, right? Okay. Question E is based on the same concept of rationalizing the denominator and simplifying the expressions. So we only have 3 here. So 4 over root 2 plus root of 8. So let's rationalize the denominator. So we only have that part, so I have to multiply by root of 2. So 4 root of 2, and then root of 2 by root of 2, and then plus root of 8. So what are you going to end up with? We end up with 4 root 2 plus root of 8, and then that will be a 2. So 2 there it's a 1, 2 there it's going to be a 2. So we have 2 root of 2 plus, now root of 8 can be expressed as a product of 2 and 4. So that will be root of 2 times 4, which we can separate as root 2 root 4. Now root 4 we know it's going to be a 2. Root of 4 is going to be a 2. So let me just show that maybe. So we're going to have 2 root 2 plus square root of 4 is a 2. So 2 root 2, and then we end up with 4 root of 2. So we've simplified, we've rationalized the denominator for the first one, and then we've simplified it. Pause the video and apply the same concept to this one. So equally we have 8 over 3 plus root of 5. We can rationalize the denominator by multiplying by the conjugate of the denominator, and then plus root of 45. So for the top part we're going to have 8 times 3 is 24. 8 times that is going to be 8 root of 5. Denominator 3 times 3 is 9. This times that is the minus 5. So 24, 9 minus 5 is a 4. So 4 there, it's going to be what? 6. 4 there, it's going to be 2. So you're going to have, wait. We've got a 4 here. 4 there, it's 1. 4 there, it's 6. 4 there is 2. So I have 6 minus 2 root of 5. Yeah. And then plus root of 45 it is. Okay, so root of 45 can be expressed as a product of 9 and 5. So that will be root of 9 root of 5. So that will be 6 minus 2 root of 5 plus 3 root of 5, which gives us 6. 3 minus 2 is a 1, so that will just be plus root of 5. I think that's the expression we have. 6 plus root of 5. Now on the third part, we have root of 3 minus root of 7 over root of 3 plus root of 7 plus root of 21. So all the same, we have to multiply by the conjugate. So the conjugate of the denominator in this case becomes root of 3 minus root of 7, root of 3 minus root of 7, and then plus the root of 21 there. For the top part, this times that will be 3. This times that will come twice. So I think you saw that from the previous question, because this times this and this times that is the same. So it's going to be twice. So it's going to be minus 2 root of 7 root of 3, and then minus 7 over root of 3 by root of 3 is 3 plus minus 7 plus root of 21. So we have 3, and then you have minus 2 root of 21. 3 times 7 times 3 is 21. So minus 7. 3 minus 7 is the minus 4 again, plus root of 21. Can you think of any way that we can simplify this? Divide by the minus 4. The first part is going to be minus 3 over 4. Second part is going to be positive 2 over 4, which is just going to be half. So root of 21 over 2. And then minus, so it's going to become positive 7 over 4 plus root of 21. So like terms, 7 over 4 minus 3 over 4. 7 minus 3 is going to be a 4. So 4 over 4. And then you have root of 21 over 2 plus root of 21, which would give us what? So that would be a 1, first of all. 1 plus. So common denominator 2. So we have root of 21 plus 2 root of 21 over 2. So that's a 1 plus 3 root of 21 over 2. So this is the answer. We've simplified all these. In this tutorial, we're just going to talk about the basics of complex numbers. So I'll start with explaining what complex numbers are, and I'll move to other concepts as well. So one thing that you need to know is that I squared is equal to negative 1. So a set of complex numbers is a set of all the numbers that exist, including the imaginary ones. So it consists of a set of all real numbers plus imaginary numbers. So the form of a complex number, the symbol can be C, a C kind of like that, yeah? That's a symbol. Well, a complex number is any number that you're able to express in the form of A plus IB, okay? So this is what you need to know. So there are cases B may be equal to 0. So for all the real numbers that you know, for example, let me show you that the number 4 is also a complex number, in that you're able to express it as 4 plus I0. So it is still a complex number. So all the numbers that you know that exist are complex numbers. So complex number is the biggest set of numbers. Okay. Now that you know what a complex number is, you need to know that when you look at the form of a complex number, which we are calling A plus IB, the A part is called the real part because it does exist, and then the I part is called the imaginary part. Okay. So you and I know that you can't find the square root of a negative. Okay? It's quite impossible. Well, under complex numbers, that's not the case. So I'll show you what I mean by that. So let's move. So I want you to know, for all the questions we're going to look at, that I squared is equal to negative 1. If you try to make I, if you try to find I, you find the square root on both sides, you're going to find that I is basically equal to the root of a negative 1. Okay, so two things that we know so far. You can express a complex number in the form of a plus ib. Now you now know that your I is basically equal to root of negative 1, and then I squared is equal to negative 1. Okay, so let's move on. So using this concept that we know so far, how would you simplify things like I to the power 3, I to the power 4, I to the power 25, I to the power 100, and so on and so forth? How would you simplify that? Okay, so let me give you an example on how you can handle such questions. Of course, later on I'm going to give you several questions that you can look at, but let me give you an example, starting with the basic ones we have. Let me also include I to the power 5, okay, and I to the power 6 for basic understanding. So I to the power 3 can be expressed as the product of I times I squared. So we know that I squared is equal to negative 1, so we can substitute where there's I squared, we're going to put negative 1. So essentially we can see that I to the power 3 is the same as negative I. So simplify the first one. Pause the video and try out I to the power 4. Now I to the power 4 can be expressed as I to the power 2 multiplied by I to the power 2. Or I can decide just so that as we proceed we can see it's the same as the power 2. So therefore I squared is the same as negative 1. Negative 1 to the power 2 is going to be a positive 1. So I to the power 4 is the same as a 1. Let's look at I to the power 5. I to the power 5 is the same as I to the power 4 and I. So it's better to deal with even numbers. So each time you've got an odd number, pull out an I, and then you remain with an even part. So the even part can be expressed as I to the power 2, and then you can pull out the 2 again, multiplied by I. Now I squared is negative 1 squared multiplied by I. You know that I squared, negative 1 squared is a positive 1. So the answer is essentially going to be I. What if we tried I to the power 6? How different would it be? It would even be easier. I to the power 6 would be expressed as I to the power, so 2, and then raised to the power 3. Now you're going to have negative 1 to the power 3. Now what happens if you multiply a negative number by odd number times? So in this case it's going to be a negative 1. Okay, so each time you've got a negative being raised to an even power, if it's 100 or 1000, it's going to be a positive 1. If you're going to have it as 101, which is an odd number, it's going to be a negative. And I think that's one thing that's very important when it comes to simplifying all these. So we're now doing the last two. So we have I to the power 25. We can put an I so that we can remain with an even power. So we have I, and then that can be as, can have I squared inside, and then you can pour out 12. 12 times 2 is 24. So we know that what we have in the brackets is a negative 1, and then raise the power up 12, which is an even power, so it's going to be a positive, so it remains I to the power 100 is an even number, an even power, so it's going to be I squared directly. I squared raised to the power 50. 50 is an even number, so negative 1 to the power 50 is going to be a positive 1. So clearly you now know how to simplify these complex numbers faster and simpler. Okay, now let's look at the addition, subtraction, multiplication, and addition of complex numbers. Division, everything is going to be covered just right here. Okay, now consider a case where you're trying to add complex numbers 2 plus 4i plus 6 plus 2i. So one thing that you need to know is this is the same case. Even when they say let your a be equal to 2 plus 4i, and then they say let your b be equal to 6 plus 2i, and then they ask you to find a plus b, it's the same question. Whether it's given like that or given in this other form, it's still the same. So how do you handle it? How do you handle such a question? So for addition and subtraction, correct the like terms. So in this case, the real part we have 2 and 6, so 2 plus 6, and then the imaginary part we have 4i plus 2i. So therefore we have 8 plus 6i. 2 plus 6 is 8, 4 plus 2 is 6i. So that's how you add complex numbers. Let me change a few things so that I can have negatives as well, and then we see how we can add them. So let our a be equal to negative 3 minus 2i, and then let our b, of course, let's have negative 2, and then plus 4i. How do you add those complex numbers? So we're going to have negative 3 minus 2i, and then plus negative 2 plus 4i. Okay. So all the same, we have to correct the like terms. So for the real part, we have negative 3, and then plus negative 2. It will remain negative 2, and then minus 2i plus 4i. So for the real part, this is going to be a negative 5. Negative 2 plus 4i, that's the same as 4 minus 2, which is going to be plus 2i. So that's how you add complex numbers. So we've looked at the addition part. Let's look at the subtraction. What happens if we were trying to find the difference? How different would we handle it? So if we're going to subtract, if we're told to find a minus b, this is basically how you would handle it. It's going to be equal to that, because what you're doing is subtracting. So therefore we're going to have negative 3 minus 2i. So distribute the negative there. You have to be very careful. So that's going to be a positive 2i. No, just positive 2, and then that's going to be a minus 4i. So after you've distributed the negative, you now have to correct the like terms. So we have negative 3 plus 2, and then we have negative 2i plus or minus 4i. So you're going to have a negative 1 if you look at that, and then you're going to have a negative 6i after you look at, okay? So that's what we have there, negative 1 minus 6i. So we've looked at both addition and subtraction. Same concept applies, just collect the like terms, know how to distribute the negative, and so on and so forth. And then I can just give you one practice question actually, yeah, on the subtraction aspect. So consider a case where we have 2 plus 3i, and then 5 minus 2i. So I'll actually use the same examples for, let's say I have 4 minus 2. I'll use the same examples for multiplication and division. How do you handle this question when you're told to subtract? Let's say you are to be given b minus a. So it means start with b, which would mean 4 minus 2i, and then subtract a, which is a plus 3i. So all the same, how is it a plus 3i? It's 2 plus 3i. Okay, so we're going to have 4 minus 2i, and then we distribute the negative, so we have minus 2 minus 3i after we've distributed the negative. The like terms, we have 4 minus 2, which is essentially a 2. Then negative 2i and minus 3i, that's going to be a minus 5i. So that's how you subtract and add complex numbers. The addition and subtraction deals with the like terms. Like terms, yeah. Okay, now this part becomes important. The I squared being equal to negative 1 becomes important when you begin looking at multiplication and division, as you'll see. Let's start with multiplication. So let's say we want you to find the product of a and b, or ab. How do you go about it? Or if you just put the brackets 2 plus 3i multiplied by 4 minus 2i. How do you handle it? So the same way you know how to multiply. So I'll first of all pick the 2 and then multiply the other bracket. So 2 times 4 minus 2i, and then we have to multiply by the 3 now, 3i. So plus 3i, and then multiply by 4 minus 2i as well. So let's do it the same way we multiply quadratics. Okay, so 2 times 4 is going to be 8 minus 4i. 3i multiplied by that, we're going to have 12i minus 6. Now I times I is going to be I squared. 8. So we can see that these are like terms. Negative 4 plus 12 is going to be a plus 8i. And then negative 6i squared. So negative 6. Now I squared, we know it's already equal to negative 1. Now this is where I'm saying that's important. So we've just distributed, and then you're going to have 8. Negative 6 times negative 1 is going to be a plus 6. Now don't forget about the 8i that's there. So I've already corrected the like terms in advance. Okay. because this is going to give us 8 plus 8i and then plus 6. So collecting like terms, we have 8 plus 6 and then plus 8i. 8 plus 6 is going to be a 14 plus 8i. So that's how you multiply complex numbers. The same way you know how to multiply different things in the bracket, that's the same way you're supposed to handle it under this part. Okay, now how would we handle it if we had maybe negatives or something? Same way. So even if we say let our a be equal to 1 minus I, and then maybe b to be negative 2 minus maybe I, how do you expect it to come out? So you would basically see that 1 minus I multiplied by negative 2 minus I. So let's start with 1, multiply that, it's going to be negative 2 minus I, multiplied by negative I, it's going to be minus 2. In fact, it's going to become positive now because of a negative. So a negative I, multiply that bracket, so that is going to be plus 2I and then plus I squared because of a negative times negative. So I have negative 2 minus, now negative I plus 2I is just essentially I squared is negative 1, so I have negative 3 plus I. Okay, that's how funny complex numbers are in themselves. Now let's look at division. Let's look at division and see what we're going to have. Consider a case where they want you to find A divided by B. How do you go about it? So how would that look like? That would appear to be 2 plus 3i divided by 4 minus 2i, right? So we are dividing here. What does it mean? We're dividing multiplied by the conjugate. So 4 plus 2i, and then multiplied by 4 plus 2i, right? That's what we're doing there. How do we go about it? So it's going to be a bit tricky. There's nothing tricky. Now there's one concept that I've not explained. So this part, we call it the conjugate. Okay, so each time you're dividing, multiply by what you call the conjugate. So the conjugate implies you change the sign of the middle part, so it's the imaginary part if you want, but anyway it works. So just change the sign in between. So that's what we've done. There are some cases where this question may be asked differently. They may give you such a question, or they may give you any kind of an expression in terms of a fraction and then ask you to express it in the form of a plus ib, where a and b are real numbers. So you actually get to approach it in the same manner. Okay, so let's go on and multiply this. So for the top part, we'll multiply. That's why we had to learn multiplication before looking at the division, because it's involved in division. So 2 times whatever we have there. So 2 times 4 is going to be 8 plus 4i. We've multiplied by 2. Let's now multiply by the 3i. 3i times 4 is going to be 12i. 3i times 2i is going to be 6i squared. Divided by... Now, this is where it's interesting. Now, multiplying a complex number with its conjugate. 4 times 4 is 16. Right? Now, 4 multiplied by 2i is going to be 8i. Now, the negative 2i plus multiplied by 4 is going to be a minus 8i. Negative 2i times that is going to be a minus 4i squared. So, this always happens when you are multiplying a complex number by its conjugate. The middle part is always going to cancel out. So, essentially, what's important is just to multiply the like parts. Multiply the real part by the real part. So 4 times 4 and negative 2i by 2i. Each time you're multiplying a complex number by its conjugate, don't waste time. So you're just going to have 16 minus 4i squared. Now I squared, we know it's a negative 1. So this is where that is very important. So by the way, this part is a 0. Okay, just in case you're wondering why it's cancelled. So we have... So where we have I squared on the 6i squared on top, we can put a negative 1 as well. So we have 8, 4 plus 12 is 16i, and then minus 6 over 16 plus a 4. So what do we have? 8 minus 6 is a 2, so 2 plus 16i over 20, which we can now simplify beyond that point and say divide by 20. So I'm going to have 2 over 20 plus 16i over 20. So that's 1 over 10 plus 4i over 5. So you've expressed it in the form of a plus ib. So that's how you divide complex numbers. Very easy to underwrite. Let me give you one more and see what we're going to have. Now this one is going to be a derivative move. Let's have 4 plus 6i. So let's find b over a. So our b is 4 plus 6i, and then our a is 2 plus 3i. So you can somehow see it's like b is like twice that of a, right? From what you're seeing. So to divide, multiply by the conjugate of the denominator. The conjugate of the denominator in this case is changing the sign, 2 minus 3i. Do the same to the numerator. Okay? So let's see what we can have. Start with 4. 4 multiply everything on top. 4 times 2 is 8. That's going to be 12i after multiplying by negative 3. 6i times that is going to be a 12i. Surprisingly. Yeah, and then 6i times that is going to be a minus 18i squared over 2 times 2 is going to be a 4. I said for the conjugate part only multiply the like parts, and then 3 times negative 3 is going to be a minus 9, and then I squared. So you have 8. This part is eliminated as well. You're going to have 8 minus 18. Now I squared is negative 1 over 4 minus 9. I squared is negative 1 as well. So you're going to have 8 plus 18 over 4 plus 9. 18 plus 8 is a 26. 4 plus 9 is a 13, which is essentially twice. So you can actually see that the division of complex numbers is actually true, proven by the example we've looked at, right? So now looking at our basics of complex numbers so far, we've looked at the most important aspects of it: addition, subtraction, division, multiplication. I've also given you the form of the complex number to be a plus ib. Now let's look at the part of it that involves sketching. How do you graph a complex number? So it's as simple as you knowing the fact that the y-axis is the imaginary part, and then the x is the real part. So this is going to be the I, and then that's the real part. Okay? So if I'm going to have a complex number 2 plus 3i, so I need to know that this is 1, that's 2, that's 3. So 1, 2, 3. So of course this side negative 1, negative 2, negative 3. All the same here, negative 1, negative 2, negative 3. Pay attention there. Okay? So the same way we know the x-axis, the x or y plane. So 1, 2, 3, 4. So if we are going to have a complex number 2 plus 3i, it's going to be 2. So the real part is on the x-axis, so that will be a 2, and then the 3i, that's on the y-axis, that part. So it is going to be there. So that complex number there we have, that's the way you can actually present it on the, that's how you can basically show it on the sketch. Okay, but it's better to show it this way. Draw something like this, just to show where they're coming from, and then that's a 2 plus 3i. Okay, so basically that's how the complex numbers come out when it comes to the aspect of you sketching them. Of course, I didn't mention there can be complex numbers which is just like 6i. It's a complex number on its own, So that would require just it can just exist on, like 6i would mean it's just on the y-axis, right? Yeah, if it's just a 6, it's just a number like that. So equally, if it's a negative, if you have a negative 2 plus 2i, for example, so that would mean on the real part you're going on the negative aspect of it, and then of course positive 2. So that's where the complex numbers would exist. Okay, so that's negative 2 plus 2i. I think it's very easy when it comes to the sketching of complex numbers. I think all you just need is just the issue of knowing that when it comes to the x-axis, it's the real part. When it comes to the y-axis, it's now the one that involves the imaginary part of the complex number. Okay, so I've given you an idea on how you could actually sketch a complex number, right? So that's where we're going to end with introduction to the basics of complex numbers. So in the next series, we're going to, in fact, before you look out for the other part, there's going to be a link in the description below to the video about the practice questions, okay, about what we've talked about so far. And then you can look at a video which is more advanced concepts of complex numbers later on. Alright, so look at a few set of questions that are falling under complex numbers. And I think just know that I squared is equal to negative 1. So which tells us that if you're trying to make I the subject, finding the square root of both sides, your I is going to become root of negative 1. So that's very important. It's going to help us as we proceed. So let's start. So basic subtraction rules apply. We'll understand how we get to divide and multiply as well. But let's first of all start with the first one, which is asking us to kind of like subtract. So we are subtracting two different complex numbers. Okay, so distribute the sign that's in between. We have 2 plus 3i, so let's multiply everything there by a negative. So we have plus 7 minus 6i. So 2 and 7 are like terms, that gives us a 9. 3 minus 6 is going to be a minus 3i. So that is our answer for the first one. And then for the second one, we have negative 2 plus 3i. In fact, that's like the third one. So let me go to the second one. Second one, we apply the same concept. Addition, only look at the like terms, obviously. So 3 plus 4i, and then plus, we have 6 minus 5i. So even after distributing the positive, nothing changes. So 3 plus 6 is a 9. 4 minus 5 is a negative 1. So negative 1i, we can just say negative I. Simple, right? Alright, number 3. We have now multiplication starting. So negative 2 plus 3i squared. So squared means that's just coming twice. That's what it means. So let's actually try to multiply now. Negative 2 by the other bracket. So negative 2 times negative 2, positive 4. And then minus 2 multiplied by 3i. So let me just go direct. So negative 2 multiplied by 3i would be negative 6i. 3i times that will also be negative 6i. And then 3i times that would be 9 plus 9. And then I will become I squared since there are 2. So we have 4 minus 12i, and then plus 9. So now I said I squared is equal to negative 1. So going to put a negative 1 there. So we end up with a 4 minus 9 minus 12i. That gives us negative 5 minus 12i. So you've seen that under multiplication, what becomes important is I squared being equal to a negative 1. Let's proceed and look at number 4 now. Still dealing with multiplication. Here we have 2 plus I multiplied by negative 1 plus 2i, and then 4 minus 3i. So we can only do it 2 by 2. So let's start with the first part. So I'll start with 2. 2 times whatever is in the other bracket. So 2 times -1, so that will be -2 plus 4i, and then we can now move to I and multiply whatever is in the other bracket. So that will be -i for the first part, and then that will be plus 2i squared. Okay, that's what we have after multiplying the first two brackets, and then we are remaining with the 3i there. 4 minus 3i, that is. So we have -2 now. 4i minus I, that's going to be a 3i. And then the I squared there is going to be a -1, so it's going to give us a -2, right? So that will be now 4 minus 3i. So that will give us -4 plus 3i. And then 4 minus 3i. At this point, you can do the needful. -4 times 4 is -16. -4 times 3 is going to be a positive 12i. 3i times 4, that's going to be a positive 12i as well. And then that's going to be a -9i squared. So we have -16 plus 24i. And then that's going to be a negative, which will now give us a positive 9. 9 minus 16 is what? -7, right? So we've dealt with subtraction and additions which are the same, multiplication, now division. So whenever you're dividing complex numbers, just like Surds, we can apply the concept of like rationalizing, but instead what we call it is we are multiplying by the conjugate. Whenever you're dividing, multiply by the conjugate. So change the sign in between. So for the first one, so the conjugate is going to be 1 plus 2i. Do the same to the numerator. So 2 times 1 is going to be a 2 times the other part, 4i, -3i by 1, -3i by 2i, that's going to be -6i squared over. So equal here for multiplications with a conjugate, just multiply the like parts, the real parts together and the imaginary parts together. So 1 times 1 is a 1, and then -2 by +2 is a -4, and then it will become I squared. So for the top part, we're going to have 2. 4 minus 3 is going to be a 1, so it's just going to be like an I, and then I squared is a -1. By the -6 it becomes +6 over, this is also a -1. By the -4 it becomes a positive, so 1 plus 4. And then you have, don't forget, so 2 plus 6 is 8 plus I over 5. So we've obviously simplified. Now we need to take it in the form of a plus abi. So it's going to be 8 over 5 and then plus I over 5, which we can actually ideally just say 1 over 5 and then I. Then for the last one, we're applying concepts of multiplication and division. So I have -2 plus 3i and then all squared divided by 1 plus 2i. So let's start first of all with multiplication. So -2 plus 3i. The fact that it's squared means it's coming twice. So what are we going to have? So we're going to have 4. -2 times 3i is going to be a -6i. And then that will be again -6i. And then that will be 9i squared over 1 plus 2i. That's going to give us 4 minus 12i, and then 9i squared is going to be a -9 over 1 plus 2i. 4 minus 9 is going to be a -5 minus 12i over 1 plus 2i. At this point, we can now divide by multiplying by the conjugate, which implies we change the sign of the denominator in between. So we do the same to the numerator. 1 times -5, obviously, is going to be a -5. Negative 5 times negative 2 will be plus 10 I, and then negative 12 by that is going to just be negative 12I, and then negative 12 by negative 2, that will be positive 24I squared. For the denominator, we're going to have a 1, and then a negative 4I squared, that is. So at this point we have negative 5 minus 2I minus 24 over 1 plus 4. So I have negative 29 minus 2I over 5, negative 29 over 5, negative 2 over 5I. So that's it for 8A. B, we are still now applying the concepts of knowing that I squared is equal to negative 1. Don't forget that. So for the first one, we have I to the power 11. So we have to put it in as a product of I times an even power, right? So what is I times I to the power 10? Okay. So now why that? Because I know the one that's an even power, I can express it in terms of I to the power 2. So the I to the power 10 is the same as I to the power 2. Now raised to the power 5. 5 times 2 is a 10. So now we know that I squared is a negative 1, so we'll substitute. Now the fact that we are raising it to an odd power, it means it's going to give us a negative 1. So we're going to end up with negative I as our answer for the very first one. Okay. If you raise the negative number to an even power, let's say 4, it gives you a positive 1. Try that on your calculator. You can even actually try it in practice. You see 1, 1. Okay. Let's try to look at another one. The second one is I to the power 61, which we can also say that's I times I to the power 60. Now we can pour out, we know I 60, we can say I to the power 2. Now that will be half of 60 is what? 30. 30 times 2 is 60, so we now have I. Now to the power 30. Now 30 is an even number. It's divisible by 2, so we are going to get a positive I in this case. So that's it for the first two. Apply now the concepts we've learned so far to deal with the other expressions that are coming here. So don't forget our I squared is equal to negative 1. Now this one is already in terms of an even power. So I to the power 102. So you can just substitute just I squared. So now 2 into 102. I think into 100 is 50, so it's going to be a 51. 51 times 2 is 102. So now negative 1 is the same as I squared. Now 51 is an odd number, so this is going to be a negative 1 remaining as an answer. And then for 4, we have I to the power 250. 250 is an even power, right? So let's pull out the 2. Now, of course, you know the half of a 250 is a 125, right? 1.5 times 2 is a 250. So 1.5 is an odd number, so it's negative 1 to the power 125, which will still also remain a negative 1. Now we are now on number 5. That's I to the power 900. Is 900 an odd power? An even? So it's even. So that's negative 1 to the power, not negative 1. I squared. So, but the half of 900 is 450. 450 is still an even power. So this is negative 1 to 450. So this will become a positive answer. And then the last one, which is I to the power 64,002. And then, so that's an even power. So what's the half of that? So divide by 2 throughout. That's going to be like a 3, a 2, 0, 0, 1. Now I think that's an odd power, right? Because you're ending with a 1. So that's going to be a negative 1. So this is how easy it is to simplify these ones, even though they look complicated. It's just a matter of you knowing that this is equal to that, and then knowing how to just, like, you know, express all these in the form of even powers. So we're now on C. For C, we are told, given that Z1 is equal to that, okay, 3 minus 2i, and then Z2 is equal to negative 1 plus I, Z3 is equal to 3 plus 2i. For the first one, we have to find 2Z1 minus 5 Z3 over... So whenever you see a bar on any letter, just know that they're asking for the conjugate. So therefore for this one, we just substitute 2Z1, we're going to have 3 minus 2i, and then minus 5. Now Z3 is 3 plus 2i, divided by the conjugate of Z3, so that's going to be 3 minus 2i. So what we have? So we have 6 minus 4i minus 15 minus 10i over 3 minus 2i. And then for the top part, 6 minus 15 is going to be what? 6 minus 15, that's the difference of a 9. That's going to be negative 9. Negative 9 minus 14i over 3 minus 2i. So I can take this back now to the top part. So at the point we had negative 9 minus 14i over 3 minus 2i. At this point we can multiply by the conjugate of the denominator because they want us to express it in the form of a plus bi. So that would be, the conjugate is 3 plus 2i, that's us changing the sign in between. So we end up with negative 9 times 3, that's negative 27. Negative 9 times 2, that's going to be a minus 18i. Negative 14 times 3, that's a 42. So minus 42, negative 42i. And then 14 times 2 is a minus 28. That will be I squared over 3 times 3 is a 9. That's a minus 4i squared. So it's 3 times 3, negative 2i times 2i. So like terms. So we have negative 27. 18 plus 42, add the 8 to the 2 to give us a 1050, so that's going to be a 60. So minus 60 I, and then that will be plus 28 because I squared is a negative 1 over 9 plus 4 because I squared is equal to a negative 1. 28 minus 27 is a 1 minus 60i over 9 plus 4 is a 13, right? So we have 1 over 13 minus 60i. So if all our calculations are okay, then this is where we should end in terms of our simplification. I think one thing that is important to understand is every time you're given this kind of expression, just substitute. Know that when there's a bar on a complex number, it means you're dealing with a conjugate. And then when you want to express it in the form of a plus abi, make sure you multiply by the conjugate as we did from that step. So applying the principles we've talked about now, try to answer the last two. So for the second one, we have Z2 like that with a bar, so that's a conjugate, and then over Z3. So the conjugate of Z2 is going to be negative 1 minus I and then z1 is 3 minus 2i of z3, which is just 3 plus 2i. Now obviously at the end of it all we're going to end up multiplying by what we call a conjugate, right? But let's try to simplify what we have. Negative 1 by negative 3 is negative 3. That will be plus 2i, negative 3i, plus 2i squared over 3 plus 2i. This is going to be equal to negative 3 minus I minus 2 over 3 plus 2i, negative 5 minus I over 3 plus 2i. Can multiply by the conjugate of a denominator. So at that point, negative 5 times 3, negative 15, negative 5 times that is going to be positive 10i, and then negative I times that is going to be minus 3i, negative I times that is going to be positive 2i squared over 3 times 3 is a 9, 2i times that is going to be minus 4i squared. So you end up with negative 15 plus 7i minus 2 over 9 plus 4. So that's going to be equal to negative 17 plus 7i over 13 over 13. So I think that's it for that one as well. And then for the last one, we have this 2 squared over z1 with a bar. So that's the conjugate. So z2 is negative 1 plus I squared, meaning that it's coming twice. The denominator is the conjugate of z1, so that's going to be 3 plus 2i. We change the sign in between to find the conjugate. Negative 1 times negative 1 is a positive 1. Negative 1 times I is a negative I, so it's going to come twice. And then I times I is going to be I squared over 3 plus 2i. I squared is a negative 1, so you're going to end up with a negative 2i remaining, because this is going to subtract with the one that's already there. So that's a 1 minus 2i minus a 1 over 3 plus 2i. So negative 2i over 3 plus 2i. Multiply by the conjugate, 3 minus 2i, 3 minus 2i. The top part you're going to get a negative 6i plus a 4i squared over 9 minus 4i squared. So we have negative 6i, negative 6i, and then that will be a minus, because I squared is a negative 1, so minus 4 over 9 plus 4 as well. I squared is a negative 1, so end up with a negative 6 over 13 I minus a 1. No, how is it a minus 1? Minus a 4 over 13. So we've expressed all these in the form of the addition of a plus bi. So is one part of these a and b should be real numbers, which we have.
Let's say you have been given 2 plus 3i minus negative 7 plus 6i. So in case you're meeting complex numbers for the first time, make sure you watch our introductory video on complex numbers to understand what complex numbers are. So basically, complex number, basically you need to understand that I is basically equal to the root of negative 1 and I squared is equal to negative 1. So We need to understand that. Okay. So now let's get started. So by subtraction and addition, you get to look up the like terms. So just as we get to do it under normal algebra, so we have 2 plus 3i. I'll then distribute the negative. So negative 7 will become positive 7. The 6i will become a negative 6i. At this point, we correct the like terms. 2 plus 7 is a 9. 3 minus the 6 is a negative 3i. So we simplify that. Okay. Let's move. Now let's say you've been given negative 2 plus 3i. Then this is what? It is squared. How do you get to simplify that? So we basically understand that when something is squared, we have negative 2 plus 3i. Again, negative 2 plus 3i. What happens there? So negative 2 by negative 2 is going to be a 4. Negative 2 by 3i is going to be minus 6i. 3i by the negative 2 is also going to be minus 6i. Then negative or positive 3i by positive 3i, we're going to have a 9i squared. So we have 4 minus 12i. Because the middle part, these are like terms. 6 plus 6 is a 12. So I squared, we said I squared is equivalent to what? A negative 1. So you can put a negative 1 there. So we have 4. 9 by negative 1 is a minus 9. Minus 12i. What can we do there? So 4 minus 9 is what? Is a minus 5. Minus 12i. So we've simplified that. We've expressed it in the form of a plus b high. Okay. So let's look at more computations. Let's say we've been given 4 plus I root of 3 plus negative 6 minus 2. That is minus 2i root of 3. How do you get to approach that question? So equally, we are just doing addition. That's why we have 4 plus I root of 3. So we maintain what is in the brackets, minus 6 minus 2i, because positive doesn't change anything. We are adding. What are the like terms? So we have 4 minus 6, which is a negative 2. Then we have high and a negative 2 high. So I is attached to a 1 there. So 1 minus 2 is going to be a minus. So we have a minus I root of what? Root of 3. So we've expressed it in the form of a plus ib. Let's look at a different form of the question. Now in this question, let's say we've been given 2 minus 3i divided by what? Divided by 1 minus 2i. So here we want to express this in the form of a plus ib. What we need to understand is this is division. And whenever you're dividing complex numbers, you have to multiply by the conjugate of the denominator. So if you have a complex number in the form a plus ib, its conjugate is going to be shown by a bar on top, which is going to be, you change the sign of what? The imaginary part. So if you look at the denominator, what is its conjugate? It's 1 plus what? 2i. You change the sign. So you even multiply it with the numerator. That's how you get to divide complex numbers. So multiplying what we have for the numerator, 2 multiplied by the high, we have a 2i. 2 multiplied by the 2i there, we have a 4i. Then we go to the negative 3 by the high, it's going to be minus 3i squared. Negative 3 by 2 is going to be a minus 6i squared. Over what? So we have to divide by 1 times 1 is a 1. 1 times 2i is going to be what? It's going to be plus 2i. Negative 2 by a 1 is going to be minus 2i. Negative 2 by positive 2i is going to be negative 4 I squared. So the basic idea is whenever you're multiplying a complex number by its conjugate, it's just advisable to multiply the like parts. So 1 times 1, which is a 1. Negative 2 by 2 is going to be a minus 2 I squared. Or sorry, a minus 4 I squared. Because the middle part is always going to cancel out. 2i minus 2i will go. So what is going to remain at that stage? So what has remained is we have 2i plus 4i, that is 6i. So where there is I squared is equivalent to a negative 1. So we have minus 3, negative 1, minus 6, negative 1. Over what? Over 1 minus 4. So where there is I squared, we'll put a negative 1. So we have 6i, that is a positive 3, that is a positive 6. Then we have 1 plus a 4. So we have 6 plus 3 is a 9, plus 6i over 5. So at that stage, if you divide by 5, you have 9 over 5 plus 6 over 5i, which is in the form of what? A plus ib. Okay. So we still have some more questions to look at as we practice simplification or simplifying of complex numbers. Now, let's say we have 2i, 2 plus I, multiplying by negative 1 plus 2i. Then we have 4 minus 3i. How do you get to simplify that? So 2 by negative 1 is going to be what? It's going to be minus 2. 2 multiplied by 2i is going to be a 4i. Negative I by negative 1 is going to be minus I multiplied by 2i is going to be 2i squared. Then in the other brackets, we'll maintain what we have. So the like terms there, we have negative 2. 4i minus I is 3i. 2i squared is the same as 2 multiplied by a negative 1, because we basically understand that I squared is equal to negative 1. So negative 2 minus 2, we're going to have a minus 4 plus 3i. Then in the other brackets we have what? We have a 4 minus what? Minus 3i. How do we get to simplify it? So we have negative 4 by 4, a minus 16. Negative 4 by negative 3i is going to be a 12i. 3i by 4 is going to be positive 12i. 3i multiplied by the negative 3i is going to be a minus 9i squared. Okay. So at this stage we can simplify. We have a minus 16. 12i plus 12i is 24i minus 9i squared. So I squared we said is a negative 1. So we have a minus 9 multiplied by a negative 1. So we have negative 16 plus 9 plus 24i. 9, 16, subtract 9. What are you going to have? So from your 16, remove 6. You're going to remain with a 10. Then you still need to remove 3, so you remain with a negative 7. So we have negative 7 plus 24i as our form in the form of a plus ib of that complex number. So what are we trying to say? In summary, what we're trying to say is whenever you have two different complex numbers, you get to add them. Okay? Whenever you have two complex numbers that you're getting to add, it's just basically easy to understand that just go for the like terms, okay, for the addition. That is the way complex numbers are, for both addition and subtraction. For division, the basic idea is if you have a plus ib being divided by x plus iy, what you're supposed to do is you need to multiply by the conjugate of what? The denominator. And we're saying the conjugate, you basically have to change what? You have to change the sign in between. Okay. So the conjugate should also be multiplied by the numerator. And as you get to deal with your multiplication, it is very important to note that I squared is basically equivalent to what? It's basically equivalent to a negative 1. Okay. Now, let's say you've been given negative 2 plus 3i squared over what? 1 plus 2i. We need to express this in the form of a plus ib. So feel free to pause the video and try that question out. Okay. So this is basically equivalent to negative 2 plus 3i multiplied by negative 2 plus 3i. That's what it means when it says squared over 1 plus 2i. So I would want first of all to simplify what is on the numerator before we get to divide. So negative 2 by negative 2, we're going to have a positive 4. The same negative 2 multiplied by the 3i is going to be a minus what? Minus 6i. 3 multiplied by the negative, that is also going to be minus 6i. 3 multiplied by the 3i is going to be 9i squared over what? 1 plus 2i. Okay. So 4 minus 12i, because 6 and 6 are like terms, they are all attached to I. Then plus 9, we'll put a negative there. So let me write that better. We don't have enough space there. Write it on top. So we have 4 minus 12i plus 9. Where there is I squared. I squared is equivalent to what? Negative 1 divided by 1 plus 2i. Any more like terms that we have? So we have 4, 9. So 4, 9 by negative 1 is a minus 9, minus 12i over 1 plus 2i. So I've just multiplied the negative by the 9 and I've moved it there, so that we correct the like terms. 4 minus 9 is a minus 5, minus 12i over what? 1 plus 2i. At this stage, we can now divide by multiplying by the conjugate of what? The denominator. So the conjugate in this case is changing the sign of the imaginary part, which is what? Giving us a minus 2i. So we do the same to the numerator. So what are we going to have? So negative 5 multiplied by the 1 is a negative 5. Negative 5 multiplied by the negative 2i is going to be 10. 10i. Negative 12 multiplied by 1 is a minus 12i. Negative 12 multiplied by a minus 2 is going to be a positive 24. Then it will be I squared over what? So for the conjugate, I said multiply the real parts by the real parts. 1 times 1 is a 1. 2i by a minus 2i is going to be a minus 4i squared. Okay. So negative 5. 10 minus 12 is a minus 2i. So these are the like terms. They are like terms because they are all attached to I. The other part, 24i squared, is 24 by a negative, because I squared is equal to negative 1. On the denominator, we have 1 minus I squared is negative 1. So I've substituted at every point where we had I squared, I've put a negative 1. So we have negative 5 minus 2i minus 24 over what? 1. Negative 4 by negative 1, you're going to have what? We're going to have a positive 4. So negative 5 minus 24 is going to be a minus 29 minus 2i over 5. So you can divide by 5, so that we have negative 29 over 5 minus 2I over 5. So we've basically expressed it in the form of a plus ib, where a and b are rational numbers. Okay, I've got some more interesting questions. What if I gave you 5 plus 3i multiplied by 5 minus 3i? What would you do? So 5 times 5 is 25. 5 again multiplied by 3i is a minus 15i. 3i multiplied by 5, that is positive 15i. 3i again multiplied by the negative 3i is going to be a minus 9i squared. Okay, so we have 25. Negative 15 plus 15 is a 0. Where is I squared, we put a negative 1. Okay. So what basically do we have? So we have 25 plus 9. 25 plus 9 is what? That is going to be a 34. Okay. So now, if we express it in the form of a plus high b, so a basic idea is that if you look at what we were actually multiplying there, we are multiplying a complex number by its conjugate. So we don't expect to have the high somewhere. We're just going to have what? A real number. And that's what we have. Okay. How about this question? How would you simplify it? You have root of 2 over 2 plus root of 2 over 2i, then squared. How is it different? A combination of sides with complex numbers. How do you get to simplify that question? So now what we have requires us to multiply the two. So we have a product of that. So we have root of 2 over 2 plus root of 2 over 2i multiplied by root of 2 over 2. So that's what it means when they say squared. We multiply itself. So I'll start this by that. Root of 2 by root of 2. So there's a tutorial where we talked about surds. And we said when you have the root of 2 by root of 2, it is the same as 2 to the power 1, which is just a 2. So what do we have there? In other terms, root of 2 times multiplied by root of 2 is the same as 2 times 2, which is root of 4, giving you 2. So whenever you're multiplying identical things under the square root, you have the exact result itself. So root of 2 by root of 2 is going to give us a 2. 2 times 2 is going to give us a 4. Okay. Then again, this very part multiplied by the other part, we are going to have the exact same result, except it is going to be attached to an I there. So put I. I'll move to the other part. I'll go to the other part. This one multiplied by that. So the numbers are going to be the same. It's to be 2 over 4. But there's an I attached there, so it will be high. Then again, this very part by that part, the numbers will still be the same. Now it will be I squared. Okay. So at this stage, what we get to have? So we now have 2 over 4 is the same as 1 over 2. So 1 over 2 plus 1 over 2 is going to be what? Or 2 plus 2 is a 4. 4 over 4. So we just have, we're going to have what? Just I. Then the other part, we have 2 over 4. 2 over 4 is the same as 1 over 2. Then we have I squared. I squared is the same as what? Is the same as negative 1. Okay. So we have 1 over 2 plus I. 1 over 2 by I is going to be 1 over 2 by negative 1 is going to be 1 over 2. So 1 over 2 minus 1 over 2 plus I. Basically we have what? We have I. So our final answer is I for that question that we had. Okay. Now try out this one. Try out this simple one. Given 2 plus 3i divided by 3i. You can also try out this one. 1 plus I root of 2 over root of 3 minus 2i. And you can also try out 1 plus 2i over 1 minus I plus 1 minus 2i over 1 plus 3i. So try out these questions before we get to move to solving the equations under complex numbers. Feel free to pause the video and try them out. Okay, I'll just hope that you had time to pause and try the questions out. So for the first one, as you might guess, what are we dealing with there? We're dealing with division. And what do we get to do for division? How do we get to approach a question? So it would require us to do what? It would require us to multiply by what? By the conjugate. So we can multiply by negative 3. Negative 3i, negative 3i. Because it's like we have an imaginary real number 0 plus 3i. So its conjugate requires us to change the sign of the imaginary part, and that's why we have a negative 3i. So multiply that on top. 2 being multiplied by negative 3 is going to be minus 6i. 3i multiplied by negative 3i is going to be a minus 9i squared. The denominator part, 3 times 3 is a minus 9, then I squared. So this can simplify to negative 6i. I squared is the same as negative 1. Negative 1 by negative 9 is going to give us a positive 9. The denominator, negative I squared, is the same as negative 1. Negative 1 multiplied by negative 9 is going to be a positive 9. So at this stage, we can simplify this to negative 6i over 9 plus 9 over 9. The highest common factor between 6 and 9 is a 3. So we have a minus 2 over 3i plus 1. So we've expressed our complex number in the form of what? A plus ib for the first part. Okay, moving on to the second one. For the second one, we have 1 plus I root of 2 over root of 3 minus 2i. So this one just basically is asking us to divide. So by division, we said you multiply by what? By the conjugate. So we change the sign of imaginary parts. So since it's a negative, it becomes a positive. So 1 times what? We have root of 3. 1 times 2i, we have 2i. Then I'll move to the next part. Negative I root of 2 by root of 3. We're going to have I root of 2 times 3 is 6. Then this by that. We're going to have I times I is going to give us I squared. Root of 2 by 2, we're going to have 2 root of 2 there. Okay. Over what? So root of 3 by root of 3, we have what? A 3. Negative 2i by positive 2i, we have a minus 4 I squared. Okay. Any like terms there? So root of 3 plus 2i. Then what else do we have? We also have I root of 6. Then where there's I squared, we can put what? A negative 1. So we have minus 2 root of 2 over 3. Where there's an I squared, we can put what? A negative 1. So negative 1 by negative 4, we're going to have a positive 4. So at that stage, we now have root of 3 plus 2i plus I root of 6 minus 2 root of 2 over what? Over a 7. Okay. What do we get to do at that stage? So we have root of 3 minus 2 root of 2 plus 2i. So I can factorize the I there. So I have 2 root of 6, then I'll put I outside. Over what? We have 3 plus 4, which is a 7, so we can divide by 7. So over 7 over 7. So we've now expressed that in the form of a plus what? IB. Okay, then for the other question that you are supposed to try out, we have 1 plus 2i divided by 1 minus I plus 1 minus 2i over 1 plus 3i. How do you get to simplify that? Okay, so you're dealing with addition here of fractions, and it is a requirement that whenever you're dealing with additions of fractions, you need to come up with a common what? You need to come up with a common denominator. So what is the common denominator there? We have 1 minus I, then you have 1 plus 3i. So you just multiply them. So now, divide this into that. You are going to remain with the other part. So you are going to multiply 1 plus 2i on your numerator, multiply by the opposite one, which is 1 plus 3i. Plus, the other part, the same thing is going to happen. You are going to multiply the 1 minus 2i. 1 minus 2i multiply by the opposite denominator, which is 1 minus I. Okay. What do we have then? We can begin multiplying. 1 times 1 plus 3i, we have 1 plus 3i. 2i by 1, it's 2i. 2i by 3i, we have 6i squared. So I've multiplied the first two there. The other parts, we have 1 multiplied by what is in the upper bracket, 1 minus I, so it's going to be 1 minus I. Negative 2 multiplied by a 1 is going to be minus 2i. Negative 2 by a negative I is going to be a positive 2i squared. This is all supposed to be divided by what? 1 multiplied by 1, it's a 1. 1 by 3i's, it's 3i. Negative I by 1 is a minus I. Negative I by 3i is going to be a minus 3. I times I is I squared. Okay. At this stage, we need to note that negative I squared is basically equivalent to what? So I squared is basically equal to a negative 1. So we have like terms there. So I can say we have 1 plus 5i. Where there is I squared, I'll put a negative 1. So we have 6 by negative 1 is a minus 6. So we have 1 minus I, the other part there. So we have 1. Then negative I minus 2i is a minus 3i. So where there is I squared, we put a negative. So 2i squared is going to be a minus 2. This is all divided by what? 1. 3i minus I is a positive 2i. I squared is a negative 1. Negative 1 by negative 3, we have a positive 3. Like terms on the numerator, 1 minus 6 plus 1. So 1 plus 6, 1 minus 6 is negative 5. Negative 5 plus 1 is a minus 4. Minus 2, we have a minus 6. Okay. Is that okay? So minus 6. 5i subtract 3i, we have what? We have 2i over 1 plus 3 is a 4. So we have 4 plus 2i. At this stage, we've not yet taken it to that form. So we can now multiply by what? The conjugate. So the conjugate of a denominator is 4 minus 2i. We've just changed the sign of what? The imaginary part. By the way, a complex number is also made up of what we call the real part and the imaginary part, just in case you didn't take time to watch our video explaining the concept of complex numbers. So x is referred to as the real part, then the part attached to I is said to be imaginary. And this is basically what makes complex numbers different from a set of real numbers, because it includes numbers that are imaginary. The root of -1, for example, that is imaginary. Okay. So what do we have? -6 multiplied by 4 is going to give us what? 6 by 2 is 12 by 4, or by 2, 24. So I have a minus 24. -6 by a minus 2i, we're going to have a positive 12i. Then 2i plus 4 multiplied by 4 is going to be 8i. 2i by -2i is going to be minus 4i squared, over, for our denominator we have 4 being multiplied by 4, 16. 2i by -2i, we have a minus 4i squared. Okay. So what do we have? We have a minus 24. 12 plus 8 is 20. I squared is equivalent to a -1. So there we have a -1 by -4, give us a 4. On the denominator part, we have what? 16 minus 4i squared. I squared is -1. -1 by -4 will give us a positive 4. So we now have -24 plus 4 is a minus 20 plus 20i divided by what? 20. Divide by 20, you have -1 plus I. Okay. So we've expressed our solution in the form of a plus ib in this case. Okay. Now let's get to look at some of the things that we get to simplify. So we are asked to express the following in the form of a plus ib. The first one, I cubed. The second one, 1 over I to the power 5. Then the other one, I to the power 15. And the last one, I to the power 1200. So before we get to look at that, let's try to simplify what we have first of all. So I to the power 3. For us to simplify this, we need to understand that I squared, we've said it is equivalent to a -1. Okay. So I3 in terms of multiplying I squared is the same as I multiplied by what? I squared. I squared by I is I cubed. So we do know that I squared is basically equivalent to a -1. So we can say we have I multiplied by -1. So therefore I cubed is the same as what? I. We've simplified the first one. Okay. Feel free to pause the video and try out the second one. We have 1 plus 1 over I to the power what? I to the power 5. Okay. What basically do we have there? How do we get to look at that question? So I to the power 5 is the same as what? So in terms of 2, I5 basically involves us multiplying I to the power 2 multiplied by I to the power 2, which is going to give us I to the power 4 multiplied by I. So I to the power 2, we know it is what? We basically know it is -1. So -1 times -1 multiplied by I. So we have a positive I. So I to the power 5, it gives us that. It gives us what? It's giving us a I. Is that true? I to the power 2 multiplied by I to the power 2. Remember, we are saying I squared is equivalent to -1. So how many i's do we have in this case? Okay. So I squared is equal to -1. So if we have I to the power 4, it is also going to be -1 to the power excuse me. That is going to be the same as to the power 2. Okay, let me simplify this. What I'm trying to say is, when you have I to the power 4, this is the same as I squared to the power 2, which gives us what? We know that I squared is basically what? Is basically a negative 1, right? So -1. So we are going to have a positive value there. So therefore, I to the power 5 is the same as negative. So I to the power 2 multiplied by I to the power 2 multiplied by I. I to the power 2 is -1. I to the power 2 is -1 multiplied by I. So we have a positive what? I. So I to the power 5 is the same as I. So we have 1 over I there. Okay. So you can divide that into the 1 by multiplying by what? Negative I. So that you express it in the form of L plus IB. So we are going to have negative I over negative I squared. So we have negative I over I squared is the same as what? Is the same as -1. Okay. So what do we get to have there? Remember, all the numerator there is supposed to be a negative. So we have negative I over 1, which is just negative I. So we've simplified. That is the same as negative what? I there. Feel free to pause the video and try out C, which is I to the power 15. Then the last one, on the part of simplifying, that we would want us to have a look at is I to the power 1002. Okay, so I to the power 15, you would want to express the I in terms of even powers. So it's the same as I to the power 14 multiplied by I. But we do understand that I to the power 14 is the same as I squared to the power what? 7. Because 7 times 2 is going to give us a 14. So I squared is equivalent to a -1. So I have -1 raised to the power 7 multiplied by I. So now what is the basic idea there? We do understand that whenever you multiply a negative number, let's say -1 times -1, that is what? That is going to be a positive 1. Now, whenever you multiply it odd times, for example, 3 times, 5 times, it's going to give you a negative value. So I to the power 7, or -1 to the power 7, I can write it also as -1 to the power 6 multiplied by -1, which is going to give us -1 raised to the power to an even power 6 is going to be a positive 1 by -1, which is going to be a -1. So whenever you get to raise a -1 to an odd number, it's going to be a negative. So -1 to the power 7 is negative multiplied by I. So I15 is the same as negative what? Negative I there. Okay. That is what we're trying to say. So remember when we said a case where I talked about I to the power 5, we had I to the power 4, so it was a different case. How do you get to simplify I to the power 200, 1002? So what number can you multiply twice to give you that? So I'll think of I, then I'll put a 2 inside. So 1002 divided by 1002 divided by a 2. So it's 501. So you can multiply 501 times to give you that. So that is the same as what? So I squared is the same as -1. So we've raised it to power 501. So 501 is what? Is it an odd number or an even number? It is basically what? It is basically, we can clearly see that what we have is what? It's not an even number. It's what? It's an odd number or an odd power. So how do we get to simplify that? So remember where we have put so we have 501. So where we've put that, the -1, we are multiplying it 501 times. 501 times is an odd number, which tells us to say that we need to expect a negative what? A negative value. Okay. That is the way we get to look at these questions. Okay. Let's try to look at different forms of questions now. So now in this case we are expected to solve some of these equations here. Okay. So if you are tired, take a break, take a chill, and come back, pause the video, feel free to relax and then get to continue. It's very, very important that you get to watch this video until the end because these are very, very important things. Okay. So now let's say you've been given 3 plus 5i is equivalent to a plus bi multiplied by 1 plus I. In this question we are taught to find the value of a and b if these two are equal. So on the left we'll maintain what we have. Then on the right hand side we need to expand that. A times 1 is what? It's a. A by the I is going to be ai. Bi by 1 is going to be bi. Bi multiplied by the I is going to be bi squared. 3 plus 5i is equal to. So we want to first of all get to substitute. Where there is I squared we put a -1. So -1 by b is going to be what? A minus b. So I've corrected the real parts. Then the imaginary parts we have a plus ib. So I can factorize out the I. So I have a plus b. Then I put the I outside since it's common. Okay. So what do we have? So we can now equate the two. A plus a minus b should be equivalent to the real part there, which is a 3. Then a plus b on the other side should be equivalent to a 5 as the imaginary part. So looking at the first equation, if I get to make a the subject, we're going to have 3 plus what? Plus b. Getting that and substituting in the second equation, where there's a, I get to put 3 plus b. We have 3 plus b. So where there's a, I've substituted that. Then plus b being equal to 5. So we have b plus b is going to give us 2b. Then the 3 can go the other side, so that we subtract from 5. 5 minus 3 is going to give us what? A 2. Therefore our b is equal to a 1 there. We found the value of b. We can also find the value of a. So therefore our value of a is going to be 3. Our b is 1. So we have a 4. So we found the value of a and b in this kind of an equation. So in a case where they give you something like that, what is very important to notice, equate the real parts and also the imaginary parts, equate them together, come up with two simultaneous equations when you get to determine the values of a and b respectively. Okay, let's look at one more. Basically, we can look at two more. Now let's say you've been given 6 plus 3i being equivalent to 4I minus 30 multiplied by x plus yi. On the left, on the left answer, we just have that. On the right, we have 4I. 30 by x is minus 30x. Negative 30 by the y is a minus 30yi. We can correct the right terms. On the left hand side, this is imaginary. So let me start first of all with the real part, which is minus 30x. For the imaginary part, we have 4 minus 30y. Then I can factorize what? The common part I. Then I can come up with two equations. First equation, connecting the real parts, is going to be minus 30x being equal to 6. Then the other part is going to be 4 minus 30y being equal to what? To 3. So we've come up with two equations here. So if you make x a subject in this equation, x is going to be 6 over 30, which is going to be negative what? 1 over 5, because 30 divided by 6 is going to give you 5. So since we have we've already found the value of x here, then the good part about this equation is x is the only thing attached to the real part. Then the I is only attached to the 30. The y is only attached to the imaginary part. So in the other equation, negative 30y is equal to 3 minus 4. So which is going to be negative 30 being equal to 3 minus 4 is okay, let me write that better. So we have negative 30 y, negative 1. Y is going to be 1 over what? 30. So we found the values of x and y in that equation. Now feel free to try out this one. Let's say you've been given, for the same equation, you've been given a to the power 3, a plus I to the power 3 being equal to 18 plus 26i. How do you get to look at this question? So a times a is going to be what? So that is the same as a plus I squared, then a plus I. Then we have 18 plus 26i there. So a times a is a squared. A times I is going to be ai. So what I'm doing, first of all, I've put that, I've wrote it twice separately, so that I try to expand it. So a times a is a squared. A times I is ai. I times a is also going to be ai. Then I times I is going to be I squared. So I've simplified, I've expanded the a plus I squared. Then that should be multiplied by the other part, which is just a plus I. And this should be equivalent to the right hand side, which is 18 plus what? 26i. What do we have? So we have a squared plus 2ai. I squared is the same as negative 1, so I'll put a minus 1. So I have a plus I there, being equal to 18 plus what? Plus 26i. Let's get to multiply now. A multiplied by a squared is going to be what? A to the power 3. A multiplied by 2ai is going to be 2a squared I. Then a multiplied by 1 is going to be minus a. Okay. So we can now move to the I. I multiplied by a squared is going to be, so let me just write that better. So a by, that is minus a. So I by a squared is going to be a squared I. Then I by 2a, so the middle part by that is going to be 2a I squared. Then I by negative 1 is going to be a minus I. being equal to 18 plus 26i. So what do we have? We have a to the power 3 plus, what other real part do we have? We have minus a. Okay, so we have minus a. Then the imaginary parts, we have 2a squared plus a squared I. What do we have for that? So those are like terms. They can give us what? They can give us 3a squared I. Then for the imaginary part again, we also have 2ai what? 2a I squared. So I squared is the same as negative 1, so you can put a negative 1 there, minus I, being equal to 18 plus 26i. So we've noticed something there. So the 2ai squared doesn't belong to the imaginary part. It's basically supposed to be attached to the real part. So we have a to the power 3 minus a. So then that part is going to be minus 2a. So I've added it to the real part. So for the imaginary, we are now remaining with 3a squared I minus I should be equivalent to 18 plus 26i. Okay. We can now come up with equations here. So for the real part, we have this part. Okay. So we have a to the power 3 minus a minus 2a. So a minus 2a, that is something determinable. It's minus 3a. Then this should be equivalent to what? To 18. From the other side, then for the imaginary part, we have, if we factorize the I there, you're going to have 3a squared minus 1. So we have 3a squared minus 1 is equal to 26. Okay. So what are we supposed to do now? Our goal is very simple here. Our mission is very, very simple. To just find the value of a. So 3a squared is going to be 26 plus what? Plus a 1 there. We have 3a squared being equal to 27. 27 divided by 3, our a squared is going to be equivalent to what? To 9. So therefore a is either equal to negative 3 or positive 3. We can try this out in the other equation. So what happens if you put negative 3 cubed minus 3, put minus 3. So negative 3 to the power 3 is going to be a minus 27. Then if you put a value there, that is going to be a 9. Negative 27 plus 9 is going to be, is supposed to give us what? And a minus 18, which doesn't match up. What about if you try the positive value there? Try out the positive value, positive 3, positive 3. So you are going to have 27 minus a 9, which is basically equivalent to 18. So the only value that is satisfying the equation is what? The positive one. So you can forget about the negative one. And therefore, our value of a has been determined to be a positive 3 in that equation. Okay. One more. xyi is equivalent to 3x minus y plus 12i. How do you get to simplify that? So our goal is to simplify it. How do you get to simplify it? We need to find the values of x and y. So on the left hand side, we can clearly see that we only have the imaginary part. On the right hand side, what do we have? 3x minus y. That is already the real part. The 12i is the imaginary part. So I'll equate the imaginary part, which is xy, being equal to 12. That is the imaginary part because it is attached to I. For the real part, this side will have a 0. That is our assumption. We have what? We have a 0. So therefore equate 3x minus y being equal to what? 0. So in that equation, you can make y to be the subject. 3x is going to be equal to y. So we've made y to be the subject, and we can get that value and plug in there. So where there is our y, we'll put what? 3x should be equal to 12. So we're going to have 3 what? 3x squared being equal to 12. And divide by 3, your x squared is equal to 4. So value of x is either negative 2 or positive 2, because the root of 4 basically is plus or minus of it. So we have two values of x. Then we can find the values of y. So y is going to be equal to 3x. So for the first value of x, we are going to have negative 6. Then if you get to plug in the positive value, you have a positive 6. So we've solved this equation. Okay, let's try to look at this interesting question. We've moved away from the equations now. Now let's say we have 5 minus 2i over z. Then that should be equivalent to 2 plus what? 2 plus I. Find z in the form of a plus ib. Find z in the form, so we need to find our z in the form of a plus what? ib. How do we get to do it? So we want to make z the subject of the formula, so you cross and multiply. So we're going to have our z being multiplied by 2 plus I should be equal to 5 minus what? 2i. So our z is equivalent to 5 minus 2i over what? Over 2 plus I. And at this stage, we've seen that it has basically gone back to the form of the question that we've been looking at, which just requires you to multiply by the conjugate 2 minus I, 2 minus what? I. So when you look at the question, whether you've not seen it somewhere, whether you've seen it or you've not seen it, don't be intimidated by the question. Okay, approach it, solve it, it's solvable. That's the good part about math. So 5 multiplied by 2, we have a 10. 5 by I is going to be minus 5i. Negative 2 by 2 is going to be a minus 4i. The negative 2i by negative I is going to be a plus 2i squared. Over what? 2 times 2 is a 4. I times negative I is minus I squared. So we have 10 minus 9i. 2i squared is the same as minus 2 over 4 minus I squared is the same as 4. I squared is the same as negative 1. Okay. So even there on the numerator part, 2i squared has become minus 2 because I squared is negative 1. So the same is going to apply to the denominator. 4 minus I squared becomes 4 plus 1 because I squared is equivalent to a negative 1. So we have 8 minus 9i over 5. So we have 8 over 5 minus 9 over 5i. So we've simplified that. We've expressed our z in the form of a plus ib. Okay. We have another interesting question, which is basically the last question in this video. We've been given that our z1 is equivalent to 3 minus 2i. Then we've been told our z2 is equivalent to negative 1 plus I. Then we've also been told that our z3 is basically equivalent to 3 plus, so 3 plus 2i. Okay, so perform each of the following operations. So we need to express our solutions in the form of a plus ib. The first question requires us to simplify this. So there's a bar on top of a z there. So a bar on a complex number indicates us it's a conjugate that you're interested in. So we've already been given our z1. We've already been given our z3. So let's find the conjugate that we're supposed to put on the denominator. So the conjugate of z3 requires us to change the sign, right? So the sign is supposed to change. So it's going to be 3 minus 2i. So we can then substitute in the equation. So I have a z1. I'll put 3 minus 2i. Then where there's z3, I'll put 3 plus 2i over, we are dividing by what? The conjugate z3. So we have 3 minus 2i. So these things is just a matter of you understanding what the symbols represent. Then you're home and dry. So let's try to expand what we have. 2 times 3 is going to give us what? A 6. 2 by negative 2i is going to be a minus 4i. Negative 5 by 3 is going to be a minus 15. Negative 5 by 2i is going to be a minus 10i. Over what? Over 3 minus 2i. So where are we now? 6 minus 15. 6 minus 15 is what? Negative 9. So I have negative 9. Negative 4 minus 10 is a minus 14i. Over what? Over 3 minus 2i. At this stage, this is easy. It only requires you to multiply by the conjugate for you to be able to express it in the form of a plus what? ib. So multiply by 3 plus 2i, which is the conjugate of what? The denominator there. So what do we have? Negative 9 multiplied by 3 is a minus 27. Negative 9 by 2 is going to be a minus 18i. Negative 14 I multiplied by 3. So 14 by 3 is basically a 42. So I have minus 42i. Then negative 14 by 2 is going to be minus 28i squared. Over that, 3 by 3, we have a 9 minus 4 I squared. 3 by 3 is 9. Negative 2i plus multiplied by 2i is going to be that. So we have negative 27. Then 18 plus 42 is what? 18 plus 42. So that is a 60. So minus 60i. Then where there is I squared, we're going to put a negative 1. So we have a positive 28. Over what? 9 plus 4. Because I squared is negative 1, so it will become a positive. So 28 minus 27 is a 1. Minus 60i over 9 plus 4 is going to be a 13. So I have 1 over 13 minus 60 over 13i. So we've expressed that in the form of a plus what? A plus ib. So the basic idea is for you to understand what the given symbols are representing. So I've got 2 more. Let's say you have z2, that's z1 over what? Over z3. What are you supposed to do there? So that symbol there with a bar z2 means that it's a conjugate. So what's a conjugate of z2? It's negative 1 minus I. Then z1 is 3 minus 2i. Then on the bottom part, z3, which is 3 plus 2i. So what do we want to do at this stage? We're trying to divide and multiply on top. So on the numerator, negative 1 multiplied by 3 is a minus 3. Negative 1 multiplied by negative 2 is a positive 2. negative I by 3 is a minus 3i. Negative I by negative 2i is going to be a positive 2i squared over 3 plus 2i. At this stage, we have 2i squared is going to be minus 2. So minus 3 minus 2. 2 minus 3 is going to be minus I over 3 plus 2i. That is going to be minus 5 minus I over 3 plus 2i. At that stage, how do we get to simplify that? We need to multiply by the conjugate of what? The denominator, which is going to be 3 minus 2i, 3 minus 2i. Negative 5 multiplied by 3 is going to be a minus 15. Negative 5 multiplied by negative 2i is going to be plus 10i. Negative I by 3 is going to be minus 3i. Negative I by minus 2i is going to be positive 2i squared over 3 by 3 is 9. 2i by 2i is going to be, so that is like 2 times negative 2 is minus 4. Then I what? Squared. So we have negative 15. 2i squared is going to give us minus 2 because I squared is negative 1. 10i minus 3i, that is going to give us a 7i. On the bottom we have 9 plus 4 because I squared is negative 1. So we have negative 17 plus 7i over 13. So I have negative 17 over 13 plus 7i over what? 13. So we simplify this one as well in the form of a plus ib. For the last one, we've been given z2 squared over z1 conjugates. Okay. So for our z2, we have negative 1 plus I squared. Our z1, the conjugate is what? You change the sign in between it to become positive. Try to expand the numerator there. Negative 1 multiplied by negative 1 is going to be a 1. Negative 1 by I is going to be what? So what I'm doing is this. So that is going to be a 1, a minus I plus I squared. So we have 1 minus 2I minus 1. Okay, I squared is negative 1. So 1 minus 1 is basically going to give us what? 0. So we are just going to remain with a 2i over 3 plus 2i. Then at that stage you can multiply by the conjugate, which is 3 minus 2i. 3 minus what? 2i. So 2 by 3, we have a 6i. 2 by a 2, that is going to be a minus 4i squared. Then on the denominator part, what do we have? 3 by 3 is a 9. 3 by 2i is going to be a minus 6i. 2i by 3 is going to be a 6i. Then we have a minus 4i squared. So we have 6i plus 4 because I squared is negative 1. So we have 9 plus 4 because I squared is what? Negative 1. So we basically have six I plus 4 divided by 13. So I have 6i over 13, 4 over what? 13. So we've simplified our complex numbers. So this marks the end of our tutorial. Just a few tips just before you go. Reminder, you need to understand that basically your I squared is equal to negative 1. And your I is therefore the root of negative 1. Okay. Whenever they ask you to simplify, basically note that if you're given you I to the power 200, for example, just express it in the form of I squared, so that it will be I to the power 200. If it is raised to an even number, it's going to be a positive 1, because I squared is negative 1. Okay. If it is raised to an odd power, it's supposed to be what? It's supposed to be a negative. So now let's say you have I201. That is going to be I200 multiplied by I. So that you simplify your I200, which is 2 to the power 100 multiplied by I. And since you know that your I to the power 2 is negative 1, which is going to give you a 1, so you have a 1 multiplied by I, giving you answer as I there, which is equivalent to the root of negative 1. Then the other thing to note is, when you're looking at the equations, where they get to give you unknowns on one side, all it requires you to do is basically gets to equate the real parts on one side to the other parts, and the imaginary parts as well. You'll be able to find the unknowns in such a case. Then whenever you see a bar on a complex number, it tells you that it's a conjugate. So given that the original complex number is a plus ib, its conjugate is going to be a minus ib. Okay? Then in a case where you are adding and subtracting, just go by the like terms. For division, when you have a plus ib being divided by x plus iy, it just requires you to multiply by the conjugate of the denominator. Okay. You just change the sign of the imaginary part.
Alright, so let's talk about the concept of binary operations. Let me try to hammer this within 5 minutes. Okay, so binary first of all means 2. So binary operation is going to be performing an operation on 2 things. Okay, so if I'm going to say A plus B, addition is an example of a binary operation. It can only be performed on 2 things. Okay, even if you're going to add 3 numbers, it's a must. You just have to do, first of all, start with a 2, or you can start with the other 2 and then basically get to add the result. Let's say a B plus C is Y, so you have to first of all find B plus C, and then that's when you get to find. So it's a binary operation on 2. Okay, so now what exactly is a binary operation under mathematics? When do you say something is a binary operation? So I like giving an example using this set 0 and 1, and then we can now focus on the positive, or that's the addition, the subtraction, the multiplication, and the division. Let's try to identify which ones are binary operations on this set. So for something to be a binary operation on a given set, for addition to be a binary operation on a given set, what it implies is whatever operation you're going to perform, the results should always be contained within the given set. What does that mean in action? So if we look at the 2 numbers we have here, does it mean if I say 0 plus 1, and I think this is the only operation we can have on two different things. Yeah, so 0 plus 1 is definitely going to be a 1, and they are not 2 numbers. Of course, you can't repeat, you can't add a number with itself. It's a binary operation. It's going to be on 2 different numbers. So every addition you're going to perform within that set is giving you a 1. So the result is within the set. So the fact that the result is within the set it implies addition is a binary operation on that set. How about subtraction? Is it? So, of course, I know if I'm going to focus on 1 minus 0, it's going to be a 1. Now, what if I said 0 minus 1? It's also it's still subtraction on that set, but it's giving me a negative 1. So the negative 1 is not within the set, so subtraction is disqualified. And of course, from that you can see that just because there is a single result that defends, it's not enough. What we do is instead we look for the negative aspects. Is there anything that can disqualify it? And of course there is. Now, what if we look at multiplication? 0 times 1, 1 times 0, that's a 0, that's a 0. So 0 is within the set. So multiplication in this case is a binary operation. Division, 0 divided by 1 is a 1. 1 divided by 0 is undefined. So it's definitely not a binary operation on that set. Okay? So I think I've now introduced you to the idea, to the concept of binary operations. And then let me try to make it a bit more interesting and remove a 0 and focus on 1, 2, maybe a 3. Maybe a 3. So definitely for this one, it's going to be a bit odd. Maybe let me remove a 3. Let me remove a 3. Is addition a binary operation on that set? 1 plus 2 is a 3. It's not. Is subtraction? 1 minus 2 is going to be a negative 1, not. Multiplication 1 times 2 is a 2, 2 times 1 is a 2. So it is still a binary operation because of the possible operations you can perform will still give you an answer contained in that set. Division, 1 divided by 2 is of course 0.5, which is not in the set. Okay, so that's a basic introduction to what a binary operation is. Now, how do we apply this now in action? How do we apply this in action? So, whether you see A star B, which is usually the common notation used, or you see something like this, whatever symbol they are going to use, it all means the same. In some books, we can even go as far as even using a triangle, trying to give you different kinds of binary operations. So I can start with the simplest one we can have a look at, where we can say 2a minus b, and then that one, let's say maybe we can call it a squared plus b squared minus ab, and then for the x and the y, maybe let's try to call it 2x plus y, something like that. So these are examples of binary operations. Okay, now how do you simplify things like 2 star 3? Okay, what does that mean? So what that means is you have to substitute in the equation. Okay, so if you look at the first part, 2 star 3, so if you're going to write what you have, 2 star 3, you can see that a is matching up with 2, 3 is matching up with b, so it implies where there is a, you're going to put a 2. So how is that going to come out? So you're going to have where there is a, we're going to put a 2, and then minus where there is b, we're going to put a 3. So we're going to have 4 minus 3, which is equal to 1. That's how you perform binary operations. I know some of you have not gotten it yet. So again, if we continue pushing that, you'll still see that a is still matching up with 2, right? So if I'm going to go on the second one, feel free to pause the video and try it out. So 2 star 3, so where there's a, I'm going to put 2. So I'm going to have 2 squared. Where there's b, I'm going to put a 3. So 3 squared minus now ab. A is 2, b is a 3. So we have 4 plus 9 minus 6. 9 plus 4 is going to be a 13. Minus a 6 is going to be a 7, I believe. So 7. So that's the result we have there. So binary operations are very simple, right? Very, very simple. So all the same, if we drop it down, you see that x matches up with 2, so it will be 2 times 2, and then for the y it's a 3. So that's a 4 plus 3, that's also a 7. That's how we perform binary operations. Now, the other important concept now that I want you to really pay attention is, what if I said 2 star 3 star 1? So it can't, the question, there's no way the question can come out like that. So you are always going to either put the brackets on 2 star 3 or 3 star 1, because I said the binary operation is always supposed to be performed on 2. So the brackets dictates which one to start with. So if we're going to have 2 star 3, it means first of all, let's first of all simplify that. So I'll use the first 2 to explain this concept. So let's start with the first one. So when we have 2 star 3, it implies we're going to put 2 star 3 first of all, since they're the ones in the brackets. We'll first of all perform a binary operation on that. So for the very first one, it implies where there's a, we're going to put a 2, and then where there's a b, we're going to put a 3. So that's going to be a 4 minus a 3, that's going to be a 1. So now in the brackets we found a 1. So what that means is it has simplified to 1 star the one that was already there. So what that means again is we're supposed to go back again. We'll now update our results. We're now going to use 1 star 1. Now where is a, we're definitely going to put 1s on both. So it will be 2 times 1 minus a 1. So that will be a 1. So that's the answer for the final, for the first one. How does this look for the second one? Same procedure, we have to first of all start with what's in the brackets, 2 star 3. So where is a, we're going to put 2, so it will be 2 squared. Where is b, we're going to put a 3, and then minus ab, so 2 times 3. 2 squared is a 4 plus 3 squared, which is a 9. 9 plus 4 is a 13, minus a 5, which is definitely 8. So found 8. So this simplifies to what we've got in the brackets is 8, now to be star 1. So we can now erase that and proceed now. On the next stage, we'll update our values. We'll have 8 star 1. So we have 8 squared plus 1 squared minus 8 times 1. So that will be 64 plus 1, 65 minus 8. So 64, of course, minus 8 is going to be 56 plus a 1, 57. Good, right? So that's what we have for that one. So we now know how to simplify the binary operations. Now there are questions that will ask you. The other questions you can expect under binary operations are questions like, is it commutative? Is it associative? These are the two common questions they ask. So what does that even mean? So commutativeness focuses on the idea that, is it true that for every number, if you say a star b and b star a, are they going to give you the same result? If you are going to swap a and b, are they going to give you the same result? That's what the argument is for commutativeness. So we'll start with that. So let's start with the first one. Is it commutative? Is it commutative? So we already have a star b. Let me try to find b star a. So b star a would imply, we'll take it as though the same way we're taking the numbers. So where there's a, we're going to, in short, we're swapping. So where there's a, we're going to have b. So 2b minus a. Now the question is 2a minus b equal to 2b minus a? Clearly, they are not the same. Clearly not the same. So they are not equal. So there is no way that binary operation is going to be commutative. So it's not commutative. Not commutative. Okay? Take note of that. So it's not enough just because you've tried 2 star 3 and then 3 star 2, just because they are giving you the same result and then you feel convinced. You have to try using the letters, because there are going to be numbers that are going to deny that fact. Now for the next one, what if we said b plus a? What do we expect? So we're going to have now b squared plus a squared minus ba. Now this one is a bit interesting. Is a squared plus b squared minus ab equal to b squared plus a squared minus ba? Well, let's be careful with mathematics. So let me try to arrange the right hand side in form of the first part. I know a squared plus b squared can be written as a squared plus b squared. I'm still right. I've just swapped them. And then ba can be written as ab if I want to. So you see that these are actually the same, right? So in such a case, we can say this is commutative. It doesn't matter what you start with, you still get the same result, whether you start with a b or with an a. So what's the concept of commutativeness under binary operations? Now the other concept that's also essential is the concept of associativeness. So what should we know about associativeness? So associativeness focuses on the idea of you dealing with three. If you're going to have A star B star C, does it matter what really you start with? If you start with B star C, or you decide to start with the first part A star B and then star C, does it affect the result? If it's going to be the same, if they're going to be the same, then you're going to conclude, of course, it's going to be associative. That's associativeness. So let me try to let's try to test for the two we have to help us understand how we test associativeness. So for A star B we already have it. So of course we are supposed to try if A star B and then star C is going to be equal to A and then star B star C. Does it matter what you really start with? So we already have A star B. It's equal to what? So let's try to find A star B star C. So A star B star C. So A star B, don't forget it's equal to what? So that is equal to 2A minus B. Okay, so that's what we're having. Now star C. What does that really mean? So what that really means is we are still substituting in that very binary operation. So it's like where there's A, we're going to put 2A minus B, and then where there's B, we're going to put a C. So where there's A, let's put 2A minus B. So put 2A minus B, and then where there's B, we're going to put a C since they are matching like this. So C, we're going to put on B. Okay, so that's what we have for that part. So we found A star B star C. It's 2A minus B minus C. Let's move on. Let's try to find now, for the other part, we're supposed to find B star C as the first one. So let's find it. So B star C in the same binary operation, it means where there's A, we're going to put a B, where there's B, we're going to put a C. So don't forget that's an A. That's an A. So we're going to have 2B minus C. Now we can straight away find A star B star C. Now where is B star C? Don't forget that we found 2B minus C. So that's 2B minus C. So if we're going to find A star B star C, B star C is 2B minus C. So if we're going to go back to that same binary operation, it means where there is A, we're going to put A. Where there is B, we're going to put 2B minus C. So where there is A, it will remain A. Where there is B, we're going to put 2B minus C. So we found both the left and the right hand side. We can simplify them so that we see. So 2A minus 2B plus a C. Well, that one is going to be 4A minus 2B minus C. Now the question is that part equal to this part? Clearly not. So we can see that it's not associative since they're not equal. Now let's try to apply the same concept to this next one. Let's try to apply the same concept to this next one. Okay, so for simplicity's sake, I can put a star there since I don't want to edit the other side. Well, it doesn't matter anyway. So let's start with the left hand side. Left hand side we have A star B star C, right? Now we already have A star B in the question, so we can go straight. So A star B star C. So for A star B star C, or A star B, this one, this part, it's equal to that. So that is equal to A squared plus B squared minus AB. Now we're trying to find that with star C. So it means where there's A, we're going to put this. Where there's B, we're going to put C, since that's where they're matching up. This is matching up with that, and then this is matching up with B. So let's go on. Let's see what we can have now. So where there's A, we're going to put this. So we're going to have A squared plus B squared minus AB squared. Where there's B, we're going to put C, so it will be C squared and then minus AB. So A is again this. Now B is C, so we're going to put first of all C, and then I'll put A in the brackets. A squared plus B squared minus AB. Okay, so for the sake of simplicity, let me try to leave it there for now. And then for the other one, what we have is A star B and then star C. So let's try to find first of all B star C since we don't have it. So B star C is going to be B star C. So where there's A, we're going to have a B in that. So we're going to have B squared plus C squared minus BC. We found B star C. Now we have to find A star this. So where there's A, it will remain an A. So we're going to have A squared. Now where there's B, we're going to have B squared plus C squared minus BC. So that is squared, and then we have minus AB. So our A remains A, and then our B is B squared plus C squared minus BC. Now the question at hand is, are these two going to be the same? Are they the same? That's the argument we have here. Are they the same? So let's try to observe. We can actually try to go beyond and just try to simplify what we have and ultimately see the outcome. Okay, so if I'm going to look at the first part, clearly this part, where can I see that being duplicated? I don't see it duplicated anywhere. Where can I see C squared duplicated in the result? I don't see it anywhere. Where can I see that duplicated again? I can't see it. So I think these are not the same. You can try simplifying, maybe you may find a different answer, but I don't think they're the same. So the idea anyway is that for associativeness, the results should be the same if you're going to perform the A star B star C. Okay, so this is just a short video that I just wanted to introduce you to binary operations, and of course there are many more practice questions that I've answered on this topic that you can actually get to watch and deepen your understanding of the topic. So thank you very much for taking time to watch. I hope this was a quick recap and a quick just dive into binary operations within a single video. Okay, so under a question under binary operations, so the operation star is actually on A and B, where it is equal to A squared plus 2B. So I'll write that. So A star B is equal to A squared plus 2B. So now the first part of the question is asking us to to find -1 star 3. So how easy can we handle that? So it's just as simple as it is. A matches up with -1, B matches up with 3. So where there is A, we'll put -1. So -1 squared plus where there is B, we are putting a 3. So what is the result? So we have 1 plus 6, giving us 7. Then the other part of saying we'd have to find 3 star -1, which is equal to, so we have 3 squared plus 2, and then our B is -1. So plug in -1. So then we have 3 squared is a 9, and then 2 times -1 is a -2, giving us the answer of 7. So what are we trying to say? So the way binary operations work is make sure you're matching up. Whatever comes first, in this case it matters, okay? Because if you check A, it is A. So if you are given 3 to be A, where there is A, you put what? Your 3, as we can see. So we found in both cases, for both -1 and they are both giving us what? 7. Now, do we have to conclude from that point to say, since -1 star 3 and 3 star -1 are giving us 7, does it mean that it's commutative, or would have to go beyond that? So that's exactly why I came up with this question. So let's try to answer the question. Now the question was now asking us to determine whether the binary operation is commutative or not. Okay, so commutative talks about the aspect of it doesn't matter what you start with, you basically get the same result. Now we cannot base our solution on the same -1 star 3 and 3 star -1 just because they're giving us 7. So we'd have to use the equation itself. A star B is equal to A squared plus 2B. So now the question under discussion is it also going to give us the same result if we started with B? That's the aspect of commutativeness. So it will be now B squared plus 2A. So if you observe the right hand side, are these the same? Do you feel A squared plus 2B is equal to B squared plus 2A? They are obviously not the same. So that's why if you can try even others, you find that it will not work out. Okay, if you try different numbers other than 3 and -1, which gave us a 7. What if we decided to try maybe let's say 3 and 2? So if you try 3 and 2, for the first one, if you start with 3 and 2, you have 3 squared and 2, and then if you start with 2 and 3, is the answer the same? 3 squared is 9 plus 4, 13. One on the bottom, we've got 4. 4 plus 6, 10. So they're not the same actually. So it was only by coincidence that 3 star -1 and -1 star 3 were giving us 7. So never should you base your conclusion on the aspect of using numbers. Use the letters as they are given. So since this is true, since they are not equal, it's not commutative. Now the last part of the question was asking us now determine whether it is associative or not. So we have A star B being equal to A squared plus 2B. So how do you find associativeness? How do you basically get to deal with it? So this is an aspect where now you have more than 3. So A star B in brackets, and then let's say star C. For it to be associative, even A star B star C should also be the same. So of course I did explain earlier to say if you look at these, they tell you what you're supposed to start with. A binary operation is always supposed to start with 2 things. So looking at the first one, which is already A star B, and then we have a C. So notice that A star B has already been given. It is equal to that. Okay. So that's what we have. That is equal to A squared plus 2B. So we are now performing a binary operation against C. So this is now denoting representing the first part A, and then our B is being denoted by C. So substitute in the equation. So where is A, we're going to put A squared plus 2B squared plus C. Where is B now? B is matching up with C. So we have 2C. Now we can now handle the other part, the right hand side, which is now A star B star C. Okay, so we need to find B star C since it's not given. So if we actually substitute B star C directly there, we're going to have B squared plus 2C. So that is what is denoting what? B star C. So substitute. So the first part is A, which is A itself. So it will just remain A squared. And then where there is B now, we are putting B star C, which is equal to B squared plus 2C. So the question at hand is, are these matching up? Are they the same? So clearly we can see that they are not basically the same. So since this is also not true, the binary operation is not associative.
Alright, so let's now look at the part concerned with the binary operations. So we have to determine whether each of the following is a binary operation on the set of integers. So what really is a binary operation? So a binary operation, I will try to explain it using this set. Let's say we have 0 and 1. Let's say they ask you a question to say, is addition a binary operation on that set? So the most important question that you need to know is, or the most important part or concept that you need to understand under binary operations is that an expression is only a binary operation if all the results that you can have are going to be within that given set. So if you talk about addition, are there any possibilities of you adding numbers that are going to break the rule here? So let's try out. So if we're going to talk about addition as a binary operation, obviously what we have is A star B, and then we are told that it's A plus B. So is this a binary operation on this set? Is it that all the results that we're going to perform are going to be within the set? So obviously here we just have 0 and 1. 0 plus 1 is just going to be a 1. 1 itself is within the set. So the fact that all the results, all the possible additions or combinations are going to be within the set qualifies it to be a binary operation. Okay? Well, you notice that multiplication in this case may not be a binary operation because you can't divide 1 by 0, right? Okay? In fact, not multiplication exactly, but division is not a binary operation. But multiplication is. 0 times 1 is a 0 within the set. Okay? You can look at other questions like 0, 1, and 2. Here you see that addition is not a binary operation in that 1 plus 2 gives us a 3, which is not within the set. Now, if we look at what we have here, we are told on a set of integers. What are integers? Integers are negative and positive counting numbers. I think that's the simplest definition I can give, which may not be mathematically correct. So we have 0, 1, 2, 3, and then negative 1, negative 2. So we don't have decimals here. We don't have fractions. Fractions, decimals, complex numbers, they are not integers. Integers are just these all numbers. Now including that they are negatives. I think that's what I can say. Natural numbers including their negatives, including 0, they are integers. So is it true that if you look at an expression like the first one, whatever numbers you're going to put as A and B, you are still going to get an integer? That's in short rephrasing the question we have at hand. So if you're going to have A plus A star B, which is A minus 2B, well, this is an integer, that's an integer. So does multiplication by a 2 change an integer into a different number? No. If you multiply an integer by 2, it's going to be an integer. If you subtract integers, they're still going to give you integers. You can try that. 1 minus 2 is a 1, right? So those are still going to give you integers. 1 minus 2 is a negative 1, which is an integer. 3 minus 4 is a negative 1, which is an integer. So in short, I can't think of any possibility of any two numbers that are going to distort this. So therefore
The first one is a binary operation. Okay, there may be some cases where they may need you to use proofs to indicate, but it's not necessary within the context of this question, so just try to disqualify. So A star B is root of A plus B. Now if you think of this now, is it true that if you try to find the square root of an integer, it will still be an integer? Well, I don't think so, because whenever I look at a square root, I know there's a restriction. I can't find the square root of a negative number. So I can think of integers that are going to give me a negative result. For example, I can say negative 2 plus 1. Those are integers. They're going to give me a negative 1. So this disqualifies. So you can even give an example. So there are some results or addition of integers. Their square root is not an integer. Root of negative 1 is not an integer. So this would only be a binary operation, I think, if it was a set of complex numbers, because this is a complex number. Okay. So this is not a binary operation. And then A star B, A minus B squared. Now if you look at this one, is it true that, well, it is true that if you subtract two integers, they are going to give you an integer. Now is it true that if you square it, it's still going to be an integer? Well, the funny part is yes, it is. Think of negative 2 plus 3, 2. So for this one, it stands. There is no disqualification. And then the last one, A squared. So if you square an integer, it's going to give you an integer. You subtract integers, they're still going to give you integers. So this also qualifies. If you can think of any way of disqualifying any of these ones that I've approved of, give us a comment, we see. And then we are on question 10, which is also dealing with the binary operations. So here we are told to let star be a binary operation on a set of real numbers. A, B, and C all are real numbers, given the operation is defined by that. Is it commutative? So commutative is the first part of the question. So I'll start with A. We have A star B is equal to A plus B minus AB. So to determine whether something is commutative or not, it means A star B should be equal to B star A, meaning that it doesn't matter what you start with. So we already have A star B, so let's try B star A. So B star A is going to be, so it means, what it means for a binary operation is if you're going to have 2 star 3, it means where there's A put a 2, where there's B put a 3. So apply the same concept here. So since we're having B star A, B star A, so it's like we're now going to swap them. So where there's A in that expression, we're going to put a B. So we're going to have B plus A minus B times A. Now, if we are going to rearrange this, this is going to be A plus B and B plus A are the same. BA is the same as AB. So the question is, are they equal? They are equal. So what you can say is A star B is equal to B star A. So therefore, it is what? Commutative. That's for a first part. Now, associativeness deals with a different concept. But maybe before that, let me handle the other part of the question, which is B. So for B, we are told A star B is going to be 3A plus B. So the fact that this we just have like a, so we're going to this one is predictable. So where there's B, we're going to put A, just exchange them. So B plus A and A plus B are the same. So equally these are equal, as we can see. So this is still a binary. This is commutative, by the way. So some of you may be like, is it always the case? Well, there might be cases where it's going to refuse. For example, when I told you, let's say if this was A minus B, you can't say, if we say B star A, it's going to be equal. No, it's not going to be equal, obviously, you know that. B minus A. So B minus A is by no means equal to A minus B, you know that. These are different, right? So in such a case, we would say it's not commutative. Okay. So now, is the binary operation associative? So associative is in a case where you have 3, for example. Does it matter what you start with? That's the question. Does it matter what you start with? Obviously, you know that binary operation starts with 2. You can only perform a binary operation on 2 things. Okay, so does it matter what you start with? That's what associative focuses on. So is A star B star C? Of course, it implies you start with what is in the brackets. Is it going to be equal to a case where you decide to start with B with C instead? Are they going to be equal? That's associativeness. So we have A star B for the first one. Maybe let me leave this part for expressions' sake. So if you look at A star B is equal to A plus B minus AB, and then if you try to look at star C, so let's actually make it appear in that form. So we do have A star B. So now let's say we are now going to have A star B with star C. So it means now where there is your A, you're going to put what is in the brackets. Okay, so where is the equation itself? So the equation itself is E. So our A is now A star B. Now so A star B, we know it is equal to this. So where there is A, we're going to put A star B. So where there is A, so let's put A plus B minus AB. So I've only substituted where there is A there, because we have said A is represented by A star B in this expression. Now we have plus B itself minus, again we have AB there, so our A is represented by A star B, which is equal to the whole thing again. So I can pour out the B and multiply by the A, which is represented by the A star B itself. This is how fun it is. So you're going to have A plus B minus AB, and then plus B. Okay, so I think let me just leave it there. So minus B minus B, A plus. Okay, so in short, I will not change anything. Let me just leave it there. Now, what if I start? What if I now decide to start with the other part? Let me move this a bit. What if I decide to move the other part, which is A star B star C, right? So that one requires me first of all to find B star C. So if I'm going to find B star C, it means I'm going to make my A be the B, and so that's going to be now be BC. So I'm going to have now B plus C minus BC. Okay, now to find finally A star B star C, it now means in this case what's happening is where there is A, we're going to have A is maintained, and then where there is B, we're going to put B star C. So where there is A, let's maintain. Now where there is B, we'll put B star C, which is equal to this. So that would be B plus C minus BC, and then we can now go back to minus A. A will be the same. Now B again is equal to B plus C minus BC. So the question at hand is what we have the same? Do they appear to be the same? Check. Here we have A plus B, we have A plus B. Here we have minus AB, we have minus BC, which are already contradicting. And then here we have, what do we have here? Okay, let's try to expand them. We see what's going to happen. Let's try to expand them instead. So here we have A plus B minus AB plus B. So if you distribute the B there, you're going to have minus AB minus b squared, then minus ab squared. So it's going to be positive actually, plus b squared, right? Now for the one that is down, we have a plus b plus c minus bc minus a. No, not minus a. So minus ab minus ac plus abc. I think there's one thing that we didn't do for the other one. Where did you consider c? I think I can't see a case where we considered c. I think all we did was, I think there was a mistake on the previous one, because instead of putting c instead where there's, because we said this and c, but instead I think we had put a b. So where there's, I think this part was supposed to be a c, equally that part is supposed to be a c. Okay, so c and then c because of the b and the b. Okay, so I think we made a mistake on the first one, so you can actually review there. So we're going to have now a plus b minus ab. Okay, and then plus c minus ca minus bc. I think let me be putting them in the order so that we can, so that's going to be minus ac minus bc plus abc. Okay, so for this part, a star b star c, for our a we maintain. Now where is b, we had put b star c, which was obviously this part, b plus c minus bc. Okay, which is okay. So let's try to cancel out what's common to see if we are right. So a is common, b is common, minus ab is there, and then minus ac is there, abc is there. What else is remaining? Minus bc is there, and then c is there. I think these are the same, so you can see clearly they've come out to be identical, so it means it is associative, right? Okay, so I'm going to answer a question from 2022, Math 1120. So we have x star y is equal to 2x plus y squared. That's what we have. Where x and y are integers, of course. Show that the binary operation is, show that it is a binary operation on a set of integers. Of course, I already explained that. So if you multiply that integer by 2, it will still be an integer. If you square an integer, it will still be an integer. So you add integers, you still get an integer. So it is a binary operation. Now I'm more interested in commutativeness and associativeness. So what does commutative mean? So commutative means if you commute them or if you exchange them. Is it true that 2 plus 3 is equal to 3 plus 2? That's what commutativeness means. Now we avoid using numbers, we use letters. So we've been given x star y. So what if we say y star now x now? Is it also going to give you the same result? That's what commutativeness means. So we'll try that. So in this case now, just like we were substituting, it will be the same. So my x in this case becomes y, so it will be 2y, and now my x is y, so it will be x squared. So now the question that stands is, if you compare the two, what is on the right hand side? Are they the same or they are different? So you can clearly see to the 2x plus y squared is not equal to 2y plus x squared. The result is definitely different. Very, very different. Okay? So we'll conclude to say since x star y is not equal to the other one and the like, so x is not equal to, it is therefore not commutative. Therefore, binary operation is not commutative due to that very fact. Some of you are wondering, is it possible then to have it be commutative? Yes, of course. You can consider a case where you have this as a binary operation, x squared plus y squared. In such a case, even if you do try to exchange, you still have what? You still have the same result. It will be y squared plus x squared. Now you understand that if you compare these two, they are the same. Even if we've started with y squared plus x, the fact is they are the same because x squared is matching up, y squared is matching up. So the result is obviously going to be the same. So in such a case, we can say it's commutative. Now the cases that are strange is consider a case where you have something like a minus b and then squared. Let's say you have a star b. Is that commutative or not commutative as a binary operation? So if I would have to start now b star a, it will be b minus a squared. Now the question that you can ask yourself is it the same or they're different? Now this is where you'd have to be very careful. So consider a case where a and b were maybe 4 minus 2 squared and then 2 minus 4 squared. Is the result the same or they're different? They are basically the same, right? Now we want to prove using letters. So if you expand the top part there, you have a squared minus 2ab plus b squared. On the bottom you have b squared minus 2ab plus a squared. So you realize that they are basically one and the same. Wow. A squared is there, a squared is there. Negative 2ab is there, negative 2ab. B squared is there. So in this case, even if it looks different in the brackets, the result is basically the same. So this is commutative as well. Now let me go back to the question that was there in the exam, and then now answer the part for associativeness. So what does it mean when you say it is associative? So is this binary operation associative? So associativeness means if you look at a binary operation and then you've got three numbers, consider a case where you have x star y and then you have star z. You've got three things there. Now is it true that even if you decide to start with, I'm sure we did under set theory, we talked about associativeness, we talked about three things. So if now I decided to start with y and z, would I get the same result? That's what associativeness means. So I'll start with the left hand side. Now notice that x star y has already been given, right? So that's what we've been given in the question. So now we just have to now find it against z. So I'll just say on my next step, x star y star z is equal to, so notice that this what is in the brackets has already been given. It is, that's why I decided just to pick up from x, y, z because I know x, y has already been given. So if I look at that, that is basically what is the result was in there, right? And then my z is just z. So it tells me the first thing is matching up with x. The second part is matching up with y, which is now a z in this case. So where there's x, I'll put what is in the brackets, which is 2x plus y squared. That's why I have to be now smart. And then plus y squared. Y squared is representing what is on the right, which is z. So it will just be z squared. So we've simplified that. Going now on the next step, looking at the other side. The other side is now telling us to start with y star z. So of course, if you find y star z, it just tells you where there's x, put y. Where there's z, put what? Where there's y, put z. So because it's saying y star z, so that's what we're just trying to do there. Y star z. The answer will be 2y plus z squared. So on your last step now, where you're saying x star y star z. So y star z has already been found. The one that is showing on the top right corner there. Now it's telling us to start with x. So x is matching up with x. So I'll say 2x will be as it is. And then where there's y now, that's where we are putting y star z, which is 2y plus z squared, the power 2. Now if you compare these two, are they the same or they are different? Clearly you're able to see that there's a very big difference there. So since this is not true, it is not associative on the given binary operation. Okay, hopefully you now are okay with the idea of dealing with associativeness and commutativeness under this topic.